let's move on to our second scheme. So our second scheme, if we go back to the earlier slide, we said that we can either store pointers in the instruction queue and have pointers in the reorder buffer, or we can just store the values. And if you go read the original reservation station paper by Tamasulo, he actually stores the values in the reservation station, or we're calling an instruction queue, and the reorder buffer. OK, so a couple things change when you do this. One structure is missing. First of all, there is no physical register file. We removed that. We're going to store in-flight instructions in a merged reorder buffer physical register file effectively. Second thing that's changed here is we no longer have a free list. And we'll see in a minute why we don't need the free list. But instead, we're basically just going to use different reorder buffer entries to keep track of our free list. And we're going to have to modify a bunch of stuff here. We're going to actually keep values in our reorder buffer instead of a pointer. Our renaming table is going to be modified. Our instruction queue is now going to be able to keep track of actual data values. And our physical register file, as I said before, has gotten merged into our reorder buffer. For completeness here, let's take a look at the where things get read and written in the pipeline. And one notable change I wanted to say here is the architectural register file, which in previous architectures was only written. We didn't do reading of it except on rollback. We now actually read from it because we might need to go find some canonical state there in this architecture. So we add an R there to denote that. OK, so let's look at how we have to modify the reorder buffer. Still looks like our reorder buffer from before. We need to know, for the same reason in the pointer-based design, we still need to know the architectural register number for the particular instruction. So this is when we go to write to the architectural register file, where do we write to it? Because we did renaming, so we have more physical registers. We can't just have an identity map there anymore. And now, we got rid of a lot of that other complexity we had, but we added a bunch more bits to go do this. We now actually can store values in our reorder buffer. So what this is instead of values waiting in the physical register file to be committed, they're just going to stick around in the reorder buffer entry, which is interesting. And so it's going to stick around in here while it's waiting, while it's pending. And then it's actually going to write to the architectural register file when it gets committed. OK, so we also modify the instruction queue. So this is going to tell us where to go get the values when we're going to go execute. It's also going to store the values now. So what's interesting about this is if you go back and look at the Tamasulo algorithm paper, they broadcast commits that are happening. And those commits end up in the reservation station of the actual value. So we're actually going to store in these two source operands here the values if we get a instruction which commits. If the instruction is pending, if it's in flight, we can't go and just get the value because the value doesn't exist. It's being calculated. And we have this dependent instruction sitting here waiting for something. So instead, if it's pending, our source field, we're not going to store the value in here, but we're going to store a identifier into the reorder buffer. And that what it's going to do is it's going to name the exact instruction that has to complete in order for this value to be ready to execute. So if you think about this from sort of the Tamasulo's algorithm perspective, there's these sort of broadcasts coming back. And what this is going to allow us to do is say, oh, there's a broadcast reorder buffer entry 7 just committed. Or actually, we probably don't even need that. We probably just need it to stop being pending. We just need to get it to be finished, because then it'll be deposited in the reorder buffer. We can go pick that value out at that point and store it here. And then we can basically have the other instructions that are renaming and executing, which go and blow away that value. But because we stored the value here, we have the most up-to-date value for that register. And we know it's no longer pending, and it's valid, and it's ready to go, at least this one. And we might have to wait for both these to get ready in order for an instruction to leave the instruction queue. OK, so the rename table also changes a little bit. Not as much as the other one, the other structures. It's still indexed by the register. We're looking for register 2, we'll say. It'll tell us where to go look for that. There's a couple different places where it's going to tell us to go look for it. It's going to tell us either it's in flight, and it's going to put the identifier into the reorder buffer. So it's going to say when that value gets into the reorder buffer and the instruction transitions to finish, but maybe not yet committed, it's going to tell us where to go get it. And that's important for subsequent instructions that are going to read the rename table to go find the value. Or it's possible that the most up-to-date value is actually in the architectural register file, and we need to go look there. So let's say the reorder buffer, you haven't written, let's say, to register 2 in a very long time. And lots of other instructions execute. And the reorder buffer gets filled up with other things for other instructions for different destination registers. It's very possible that the canonical place to go look for the value is in the architectural register file. And we need to track that. So we sort of have 2 bits here that sort of just say where to go look for it. Either it's in the architectural register file, or whether it's in flight. And then if it's in flight, we have to go look down here. And if it's in flight, that means that, and if p is, let's say, 1, it's actually in flight. And if it's 0, well, it's sitting in the reorder buffer waiting to retire. This is just going to tell us where to go find the actual value for subsequent instructions that want to go read the rename table to go find the value. OK, well, we'll move on. And we'll look at the eye chart here again. And what's interesting about this is we no longer have a free list. We got rid of that structure, so we don't have to worry. Our renaming table, instead of having actual physical registers, it's going to have reorder buffer entries. We'll call that a physical register. We've basically merged our physical registers and our reorder buffer together. And similar sorts of analogs happen to when something becomes free, but it looks a little bit different. So when something becomes free, we're going to actually change the valid bit in the rename table to a 0. And that's effectively the same thing as becoming free. And there's analogs there between these 2 designs. They're almost exactly the same from that perspective, from a logical perspective. But when you become free, you basically can remove it from the table. So how do we do the mapping from the architectural register to physical register? Yeah, it could be random. In this design, it's a little bit different because you're basically going to be pulling out of the reorder buffer in order to some extent. You're going to, your physical register number is going to be your reorder buffer entry slot number. And because we want to retire in order, we're basically going to allocate from that in order. So it's not really random. It's just sort of the next reorder buffer entry. let's see. What other points I want to make here? Actually, OK, I want to make a point. It's around, OK, so I think what I said was a little bit confusing. So I want to clarify this. When do you deallocate a reorder buffer entry? Because it's a little bit different than deallocating a physical register entry. You apply the same algorithm we applied before. When you go to actually commit the instruction to the architectural register file, that's when it's becoming free. It's basically stopping being used here. That's a little bit different than the, there's analogs to before, but we're effectively moving it out of the reorder buffer into the architectural register file. And at that point, it becomes free. So I want to actually strike what I had just said before about it's exactly the same. It's different, but subtly, that when you go to write, when you go to actually commit the instruction, you're moving it to the architectural register file, and you effectively deallocated that reorder buffer entry, and you've updated the rename table. So that's subtle. That's actually subtle there. So we're actually, when it commits, it stops being used, which is different than a later instruction actually writing that. So that is quite a bit different. Sorry about that. Let's move on to memory disambiguation. So this is kind of the analog of read after write hazards through the memory system. Whoops. OK, we have a basic instruction sequence here. We have a store followed by a load. When can we execute the load? Well, that's a tough one. If the load's not dependent on the store, we can just go execute it out of order. We can potentially even execute the load before the store in an out-of-order machine. If the load's dependent on the store, so if, let's say, register 2 is equal to register 4, then we're going to have a problem. So how do we go about trying to solve this? Up until this point, in our pipes, we've said, OK, loads and stores are in order, because that can solve these problems. So let's say we just execute all loads and stores in order, and we can still allow other instructions to move around it. So it's out of order relative to other instructions, but we have in order memory instructions. And that's going to guarantee that we're not going to have any problems. But we're leaving performance on the table here. We could go faster. We could actually execute loads and stores out of order if R2 and R4 are different. But we're probably going to need some extra structure to do that. OK, so let's take a look at a conservative out-of-order load example. So our conservative one, let's split the store into two sort of subparts: an address computation and the actual data write. By doing this, we can guarantee that the store, because we did the address computation early, we can know that that subsequent load is not going to alias, or we know that R4 is not going to be equal to R2. And we can go execute the load before the store in this case by splitting the store into two different parts, the actual store portion and the address computation. And we still need to, unfortunately, check every single load against all previous uncommitted stores, and we need some structure to go do that. So that's sort of a kind of a problem. That's a bummer. And we're not able to execute any load if we don't know the store address of any of the stores before us, because we're just not going to know whether we can go execute that or not. OK, well, could we do one better? Let's start speculating. Because let's guess that these are not equal. Let's execute the load before the store. And then we hold off committing the loads and store instructions, and we do that in order. And if something bad happens, so if the registers do equal each other, we have to replay all of these instructions. And what's annoying is we also have to kill all of the subsequent instructions. So anything that was after that load and store, which could have picked up a value from the load in the store, or, well, rather from the load, any dependent instructions of the load, we're going to have to go kill all that. And depending on how precise we want to be, we can either try to kill just everything after it, or we can try to kill just selectively the things which are dependent on it. It's really hard to track. And we have a pretty high penalty here for inaccurate address speculation. So if we go and we just execute these two instructions, we put them into the pipe, and they were dependent on each other, we have to roll back a lot of state. So one sort of heuristic on this was done in the Alpha 21264, is called memory dependence prediction. So what you do is you're still going to guess that the loads in the stores do not alias. But then later, if you find that the two registers do equal each other, you're going to squash all the instructions. But then you're going to do something special to that load. You're basically going to say, that's a wait for the store. You sort of put a barrier in so that you're not going to get like multiple rollbacks over and over again. So it's kind of a conservative way that when you see that you're rolling back a lot, there's a lot of thrown away work that you're doing there. So instead, you can just say, well, this load, I think, is dependent on that store. You could potentially even remember that across instruction sequences. So if it's always the case, let's say this load is dependent on the store, you could potentially keep it into your instruction cache or something like that. And then, when you go to execute that same load at a different time, it's going to wait for all the stores to complete, and it's going to barrier. This is kind of a prediction. It's just a heuristic. But it's one way you could potentially not cause that load to always replay. And if you have sort of multiple dependent loads, or excuse me, loads dependent on one store, you could potentially cause those loads not to have to replay multiple times. But the big advantage here is when you go to re-execute that load sometime in the future, you're not going to flush the entire pipe. So this is kind of like a branch prediction, if you will. It's like this branch, I've trained the predictor to say that load usually is dependent on a previous store. So just wait for all the other stores to clear out of the pipe. So it's a cute little trick. OK, so we're almost out of time. OK, so speculative loads and stores. We're going to introduce a store buffer to hold the speculative state. So let's take a look very briefly here. I'll flash up what a store buffer looks like. And then we'll think about it for a second here. So here you have your cache, your L1 data cache, we'll say. We're going to send all the addresses that go to the L1 cache also to this other structure here, which is the speculative store buffer. Inside the speculative store buffer, there's going to be bits basically saying whether it's valid or not. And the load is going to check against here. And let's say the data hasn't actually gone into the cache. It can go pick up the new value here. And the S bit is basically just going to tell us whether it's in flight or not. So it's possible that we allocate into here, but the store isn't at the end of the pipe yet, or we're still calculating the data. So we need to know that we're going to get a hit if we get a load out of order, and we need to go check for that. And that's really why we have 2 bits here. And then sometime in the future, we have to eventually move the data into the data cache, because this structure will get full. If we sort of fire enough stores against it, it's going to get full. So it's probably a good idea to go move that data into the data cache at some point. We can do that at our convenience, though. And if the store aborts, this is important here. So if the store, let's say, was speculative itself, and it's on the wrong side of a branch or something like that, we just remove it from this table. One interesting thing here is if the data is in both this buffer and in the cache, which one takes precedence? So the store buffer has the new values. So we have to look there. And then finally, it's possible to get multiple stores in here which have the same tag, the same address. Because let's say you're storing to the same address over and over again. And when you go to read, you need to go read the youngest value out of there, because that's the most up-to-date one. So the lookup through here is a little complicated. You actually need to do it in program order. OK, so we'll stop here for today. So we're going to be continuing today talking about VLIW, or very long instruction word processors. This is an alternative way to exploit parallelism in a processor, but instead of doing scheduling dynamically, as we've been talking about in out-of-order processors and superscalars, we're going to look at ways to do it statically in the compiler, and then architectures which can exploit that. But let's now start talking about very long instruction word processors. So we've been talking about the superscalar processors. These superscalar processors have a fair amount of complexity in them, especially out-of-order processors. But where does this complexity come from? And can we remove all that complexity? So that's what we're going to be talking about today. So here I draw a picture where I have the issue width of a superscalar processor, and we represent that as W. And then we have the lifetime of an instruction. So that sort of gives you a matrix of things in flight in the processor. Now, these may be sitting in your instruction queue. We're not going to count if they actually, let's say, get all the way to the reorder buffer, because by the time they get all the way to the reorder buffer, they probably, depending on how you build your processor, you probably don't need to continually check those against the other instructions that are coming. You've already broadcast that back to either your reservation station or your instruction queue to issue further instructions. But if you think about the complexity here of what you're really doing when you try to go issue an instruction, you're trying to take these in-flight instructions, and you have to look up basically against them, or in your instruction window, all of the instructions when they complete against basically all of the other instructions, all the registers. Now, we built some structures that make this so you don't have to do a complete all-to-all check. So example structures that we create to help out with this, first of all, the scoreboard. Instead of keeping track of where everything is, sort of our original design where we had portions of, or which register destinations sort of flowing down the pipe, and then we did an all-to-all compare. Instead, we just keep track of the location and latency of the most recent write to a register. And it turns something from a all-to-all compare into an index lookup based on the register. So that's a little bit nicer. But if you think about what's happening in the issue queue, we're still doing as an instruction retires, it's going to basically broadcast the registers that get completed against the instruction queue and try to wake up instructions and see which ones are ready to go. And that roughly, as I said, scales like this, because you're going to be returning multiple instructions per cycle. And let's say you have a bunch of stuff in the instruction queue. You're going to have to check against all of those. And this can get painful. Let's take a look at first sort of the complexity of this for in-order machine. So in-order machine is not so bad. L is kind of the pipeline length. You have your width, but you just basically have to have a scoreboard to figure this out. And as we said, that's an index-based structure. Now, when you start to go out of order, you start to have this sort of complexity of all of the results that come back have to be broadcast against either, if you have a distributed instruction queue, all the reservation stations, or if you have a single instruction queue, you have to check against all of the possible instructions to go issue. And what's interesting is one of the big challenges of building these structures is not actually quite what you'd think. There's an interesting challenge that you have too many things that could wake up in one cycle. So let's say you have a single instruction, or let's say all of the instructions in your instruction queue are waiting on register 5 to become valid. All of a sudden, instruction, some add, let's say, writes register 5 and it enters the reorder buffer, so it gets the end of the pipe. Well, now all of a sudden you have to wake up all these instructions and choose some instructions that are the width of your machine that can go issue. Also, you still need to make sure that you can satisfy all of the different requirements in the machine of functional unit mixes. So if you have, let's say two adds, 2 multiplies, and 1 load and store, you can't just go pick randomly from there. You need to pick exactly that mix. So this becomes a big mess of combinational logic. And this is why front ends of processors can actually, and out-of-order processors can start to get longer and longer. You get more and more stages in there to do this. And as we talked about last time, in like the Pentium 4, there's actually multiple stages out in front there to be able to do this. And unfortunately, you even have to pipeline that, which makes this even more challenging. So roughly, if you look at sort of the out-of-order control logic here, it's sort of growing somewhere between the width squared to the width cubed. And this is not very good. Sometimes there are a couple circuit level tricks that can help you. So if you go look at people who actually do full custom logic for designs of processors, they'll make something that they call pickers. And what a picker is it's actually instead of using straight combinational logic to go compute what instructions ready to go execute, you'll instead have a much more analog circuit in there, where you'll basically have some custom analog circuit there, which is almost like a CAM, or a content addressable memory. But it's not quite a CAM. It's more of a circuit which will choose what instruction is ready to go, and it is typically you want to have some heuristic that is the oldest instruction. This is to prevent deadlock, so you don't really want to issue arbitrary instructions. You want to issue the oldest instruction because you want to make forward progress in the machine. So what I'm trying to get at here is this is a lot of hardware complexity. It's growing as the width of the machine. And some things actually make this even worse. So here, I have a little note here that as you increase the width of your machine, let's say you had a 3-wide machine and all of a sudden you want to go to, let's say, a 4 or 5-wide machine. Typically, you need also a larger instruction queue or instruction window to look across in order to find enough parallelism to keep the machine busy. So as you go wider, you also typically have to make the machine sort of deeper, or at least make your instruction queue deeper, to find enough parallelism to feed your functional units. That's not good. So this causes these sort of blow-up factors here. And you can build these things, but they're hard. So are there alternatives? Yes. But before we move on to those alternatives, let's look at the sort of complexity of this in a real processor. So here we have a die photo, or die micrograph, of the MIPS R10000 processor. This was used in workstations by SGI for many years. It's a real out-of-order superscalar. And one of the interesting things is if you go look at how much area is dedicated just to control logic, it's pretty substantial. So in this processor here, here's our actual data path. It's relatively modest. Cache, instruction cache, data cache, those are pretty big structures. You can see those. We have some other, let's say the data tags, instruction tags, the TLB, those are biggish sort of things. And then all this stuff here is quite large. Let's look at what's inside of here. We have sort of next instruction sorts of things. We have the free list for the, we had talked about this, right? We talked about the free list for the which register is free, if you will, to reuse in your out-of-order processor. We have a big thing that just does register renamer. We have different queues here. So this is a distributed instruction queue or a distributed reservation station processor. So there's one for just address calculation instructions, integer instructions, and floating point instructions. But what's interesting to see here is the percentage of this die that's actually doing compute. Let's say this integer data path, the floating point data path, the floating point multiplier, is sort of pales in comparison to all the overhead. So this is just sort of to get this idea across. Another problem with out-of-order superscalars or superscalars in general is thinking about how do we express parallelism. And I alluded to this in a previous lecture, but it's worth repeating. So let's take a look at what happens for code, sequential codes on a out-of-order superscalar. We start off here with some piece of C code. We put it into our fancy superscalar compiler. That generates some sort of data flow graph and probably also control flow graph inside the compiler. So it's sort of instructions. There's dependencies between the different instructions. And the compiler right now is trying to find independent operations because it's going to try to come up with a schedule. Unfortunately, you have to come up with a sequential schedule because the instruction sets on sequential processors require you to come up with some order, even though it's very possible that there is no one perfect order. It's also possible that you're sort of over-constraining the problem here. Why are we coming up with some ordering when we don't need to? But in our sequential ISA, we have to come up with that. We write it out to disk somehow, or save a file with this code, and then we have to go and actually try to execute it. And what's funny, I just get a chuckle out of this, is the compiler knew what the dependencies were. And then we have our superscalar processor here, which goes and takes apart the sequential code and tries to reorder the instructions and tries to find parallelism in the instruction sequence. But the compiler knew that. But we had like a breakdown here in the middle that we just were not able to express that between the compiler and the processor. Compiler knew about the parallelism. Compiler knew about all the ordering and the requirements. It had to come up with some sequential code sequence, provides it to the processor. The processor takes that sequential code sequence back apart, does out-of-order scheduling like we did on the exam, on the midterm. And it's going to, we build a bunch of hardware here, which has high complexity, as we were talking about in the combinational logic, checking the dependencies. And then it comes up with some schedule. This is done via our reservation stations or our instruction queues, and something's going to fire, and it's going to come up with some schedule, and it's going to execute those instructions by preserving read after write dependencies. And hopefully, if our superscalar processor is fancy, we have some register renamer. We can break some of the other dependencies also, the write after write and the write after read dependencies, and come up with some schedule that's high performance. Now, there's no guarantee that this schedule is what the compiler would have done if it was smarter, or if it could somehow express parallelism across this interface. But it does something. And what's funny about this is there's a whole lot of power that's being wasted. It's a whole lot of effort that's being wasted in the processor. There's a lot of effort of the designers of the processor that are effectively designing all of these circuits to take apart the sequential code sequence and do something useful with it. So it's a lot of work being done there. Is there a better way? So this is where some people got the idea that maybe there is a better way. And I wanted to point out that this is only the tip of the iceberg of what we'll call better ways of having better instruction sequences or better encoding standards between compilers and the hardware. This is actually an open sort of research topic now. Very long instruction word processors, or VLIW for short, is one take on it. There's been a fair amount of work done after this, which we're not going to be talking about in this class, sort of in the last 5 to 10 years, that has looked at this in a little bit more detail, especially given sort of multi-cores and can you schedule across multiple cores. Or there was a project out of the University of Texas in Austin, which tried to schedule across something that sort of looked like cores, but wasn't quite cores. That was sort of, we'll call a super VLIW, but had some dynamic aspects and some static aspects. But for right now, let's talk about very long instruction word processors. Okay, where does the name come from? Let's start there. Well, these things were actually originally called long instruction word processors. The name kind of fell out of favor. At one point, people made a differentiation between long instruction word processors and very long instruction word processors. And it was kind of on how many instructions were packed together. The differentiation is largely sort of fallen out of favor now, and people mostly call all of these things VLIWs, or very long instruction words, because it's hard to say what is long, what is very. It's kind of just an extra term. It's kind of like people talking about large scale integration versus very large scale integration versus ultra large scale integration, or people just sort of keep tacking on extra letters in the front. But let's talk about VLIW instruction sequences and what does one of these things look like? Well, a VLIW instruction will actually have multiple operations within one bundle. So typically, this is either called a bundle or an instruction, with multiple operations inside of it. So in this example here, we have 6 operations that can be executed in this one instruction or in this one bundle. And typically, there is sort of fixed format. So let's say we have, you can execute 2 integer operations, 2 memory operations, and 2 floating point operations per cycle, and that's what you're allowed to encode. So instead of having on the disk a sequential sequence of instructions, now we still have a sequential sequence of instructions or a sequential sequence of bundles, but each one of those instructions, each one of those bundles will actually encode multiple independent operations. So let's look at sort of an example code sequence of this. So for instance, you could have something that looks like this. Let's say so what's interesting about this is we can see that there's actually 2 operations in this first instruction, in this first bundle. The second one only has 1 operation. And this multiply and this add will actually execute, semantically at least, they can execute in parallel. Now, what's interesting is if you look at this, I purposely wrote this to show what looks to be a read after write or write after read or some sort of dependence between these two registers and these two instructions here, this mul and this add. But that's not what's actually going on here. In a very long instruction word processor, within one instruction, within one bundle, these sorts of dependencies are ignored. So just because this reads R3 and this writes R3, they're not dependent on each other. The subsequent instruction is dependent on R3. Let's say if this was R3, then that would probably read the result there. But within one bundle, it doesn't actually matter. So the semantics of the instruction set are everything within one instruction or everything within one bundle are parallel with each other. And there's not dependency checking. What's nice about this is we just took all that piece of hardware that we built. We took all that instruction checking, all the dependency checking, all the scoreboarding, and we just threw it out the window. We don't need that hardware anymore in this instruction set or in this architecture. So that's pretty cool. So we actually took out a bunch of hardware that we didn't need, and we basically let the compiler do that checking for us. Now there's a question of this mul. If this multiply takes multiple cycles, whether this instruction here picks up the result of R3. Sorry, should be drawn the other way. Or let's say if the add had longer latency, if it doesn't pick that up. And we'll talk about that in a minute. There's sort of two different choices there in VLIW designs. Well, let's look at our slide here. Typically, in sort of traditional VLIWs, each operation has a certain amount of latency. So, and it's guaranteed. Unfortunately, because of this, the architecture of the machine is very tied to the compiler. The compiler needs to know how long each operation takes. So that's sort of a downside. And in a typical VLIW, there's no data interlocks. So we don't even have a scoreboard. Now, there are some architectures which do enforce interlocking that are VLIWs. But in sort of the traditional, most basic VLIW, you don't have a scoreboard. You have no interlocking. So if you were to have, let's say, this subtract operation were to read register 1, which the mul wrote. And the mul, let's say it's a floating point mul. It took four cycles. In the most basic operation, this mul here would actually get the old value of R1. So it would not get this value. Instead, it would get the original value of R1. But we'll talk about that in more detail in a second. There's a sort of a choice there in VLIW designs. But yes, so we reduced our hardware. We don't have a register renamer. We don't have an issue window. We don't have a reorder buffer. We don't have a scoreboard. And we let the compiler do a lot of the work. Downsides to this. We're not able to react to dynamicism very well, or dynamic problems. So cache misses, branch mispredicts, things like that. Because we're not going out of order, because we don't have all that extra hardware in there, we can't go schedule around those problems. So that's a downside to these architectures. Now, people have thought really hard about how to make VLIWs have some of the benefits of superscalars and out-of-orderness and out-of-order superscalars. So at the end of lecture today, and probably in the next lecture, we'll talk about some of the techniques that people have added back into VLIWs that bring us somewhere in between an out-of-order processor and a VLIW processor and get some of the benefits of both. OK, so two models. This goes back to when you have an instruction which writes to a register, and the latency of that instruction is coded to be longer than 1, which value do you pick up? Do you pick up the old value, or do you pick up the new value if you have an instruction which is effectively in the shadow of the other instruction? So the first VLIW model, and this is a sort of classical naming scheme. I did not come up with this. It's called the equals scheduling model. So the equals scheduling model, you have a instruction, and the latency of the instruction is specified. The compiler knows it. And if you have an instruction which tries to read a value that gets written to before the first instruction actually does the write, it'll get the old value. So let's go through an example over here. So we're going to have our multiply again. OK, so here we have a mul and an add, which are bundled together. So they're going to execute concurrently. We have an and instruction, or and operation in the second instruction, in the second bundle here. I should say that I'm using brackets and semicolons to delineate sub-operations. Or the brackets delineate an entire instruction or entire bundle. The semicolon is just there to delineate between two operations within one instruction. And here we have an and. We have what looks to be a read after write dependence here. Something like that. And let's say our pipeline looks like this. We have x0, which does ALU ops. We have y0, y1, y2, y3. And then we have, let's say, a two-stage memory pipeline. And somewhere over here, we have sort of write back. So this looks similar to sort of pipes we've looked at before. But now comes the question, let's say multiplies go down this four-stage pipe, very similar to things we've looked at before. Loads and stores go into the memory pipe, and ALU operations go into the X pipe. Should this AND get the result in the multiply if it's scheduled one cycle after it, or should it get the old value of R1, the previous value of R1? So we're going to define in the equals scheduling model that the multiply value for R1 is not ready until the end of Y3. So in the equals model, this AND, the compiler is not trying to express a read after write dependence. This does not actually exist. It gets the old value of R1. And the compiler knew about this, and everyone's OK with this. Now, if this AND was, let's say, 3 more cycles later, it would actually get that value, and there would be a read after write dependence. So in the equals model, we're just saying that the operation takes effect exactly at the specified latency and never earlier. Some positives to this is you get some pretty cool register usage. So if you think about it here, register 1 was live after this multiply. So effectively, this gives us a little bit less register pressure. We can have a little bit more registers in flight without having more physical registers or having more architectural registers at all. We can basically just have more registers because it doesn't go dead when we overwrite it. It goes dead when this multiply takes effect. So as I said, we don't need any register renaming. But the compiler really depends on not having the registers visible early. Unfortunately, this causes some problems, these sorts of architectures. This is actually the sort of first formulation of very long instruction word processors looked like this. There's these equals architectures. The major problem with these actually comes around if you have things that are unpredictable mixed in with this very predictable code sequence. So let's say you take an interrupt. Let's say we just put some unimportant instruction here, some subtract operation. The subtract takes an interrupt. Now, semantically, this multiplication and this add complete because the interrupt doesn't happen until the instruction after it. It doesn't happen until this subtract operation. OK. Now you fall into the interrupt handler for the subtract. What happens when the AND goes to execute? Does it actually pick up the correct value of R1 here? No. It picks up the new value of R1, and it was supposed to pick up the old value of R1. So that's traditionally a problem with EQ or equals scheduling model architectures. People have solved some of these problems. Or sometimes when people build these processors, they don't have interrupts. So some of these VLIW equals processors were not able to handle interrupts at all. So that's something to think about. That's sort of the first case. Now let's look at a little bit more forgiving case. We'll call it the less than or equals model, or LEQ scheduling model. So here, in this model, a value is allowed to become value, a register value becomes valid with the new register value anytime between when it issues and the scheduling latency. So what this means is the compiler still can't schedule an instruction early. So it can't go and try to read the value early, but you're guaranteed not to have a problem when there's an interrupt if, let's say, you come back and you filled in the right value. So the compiler sort of schedules around this and knows not to schedule something too early. So you still don't have to implement interlocks. You still don't need a scoreboard. But you can now have precise interrupts. Some other positive things pop out of this. You end up with binary compatibility preserved when the latencies are reduced. So let's say you make a faster processor where your multiply, instead of taking 4 cycles, only takes 3. That's a positive here. You may not get more performance from it, but at least you won't get incorrect execution. So that's a sort of a positive outcome here. OK, so a little bit of history. Usually I try to not harp on history too much in this course, even though I really enjoy it. But the VLIW processors is, I wanted to make one point that a lot of this research is relatively recent. So if we go look at sort of the dates on this, these first processors and the first real VLIW processors was done in like the late 80s. So this is not going back to the 60s. This is like a portion of computer architecture work which is actually very, very recent. The first long instruction word processor was actually a floating point systems, FPS, that's what it stands for, processor. And this was actually a coprocessor to VAX machines. So it's something that could speed up your floating point on a VAX machine. This was very much the most basic VLIW processor. There was no interlocking, didn't take interrupts. It was really sort of for hand-coded vector arithmetic and floating point math. Probably when people talk about VLIW, the thing that pops into to their head first is actually the multi-flow trace processor, which was made by a small startup company called Multiflow. This was an outgrowth, actually, of a bunch of research that was done at Yale by Josh Fisher and a bunch of his students. And I won't go into too much detail here, but one of the interesting things is they really, really did have a long, very long instruction word here. 1,024 bits long instructions. So this is like a beefy instruction. This is, and you can have anywhere from 7, 14, or 28 operations per instruction. And this was not dynamic. What this actually was is this is how they made different configurations of their machine. So they actually had wider machines that were more expensive and narrower machines that were cheaper. So it's sort of a family of processors, and they customized the compiler to this. Josh Fisher actually is much more of a compiler guy probably than an architect by training, and you can sort of see that in his group's work and the PhDs that have come out of it. He now works for HP Labs, and is sort of semi-retired. At the same time, actually, there was also another company that was commercializing a very, very similar idea. This was the Sidra 5. This was Bob Rao, who's another very famous computer architect. He was a professor at the University of Illinois, and he developed a lot of these things, then sort of left and started Sidrome. And some of the interesting things in that processor is they had this cool thing. Instead of having a register renamer, they had a register file that the naming of the registers sort of changed as you did sort of function calls. We'll talk more about that later today, or maybe tomorrow, or maybe next lecture. But more of what we really want to get out here is this is very recent. OK, so very long instruction words processors still want to have high performance. And we took all this hardware that was in a out-of-order superscalar, and we sort of threw it out. Well, something's got to make up for it. And what makes up for it is a very, very, very smart compiler. So we put a lot of emphasis on the compiler in these sorts of architectures. And the compiler really has to do the scheduling. It has to do all of the dependency checking. It probably has to avoid all the different data hazards. And this is just sort of just getting started. We're going to talk mostly next lecture about all of the different optimizations that a compiler can do to try to approximate what a out-of-order superscalar can do, but by doing it statically. So it's a pretty cool trick. If you take all that hardware, you put it in the compiler, you run it once, and then every time you go to execute the code, you don't have to go and recalculate all the dependencies. Sounds good. OK, so let's see how we execute some code here, and what is the sort of performance aspects to executing loop code on a very long instruction word processor. So here we have a very basic array increment. We're going to take every element of this array. We're going to increment it by the value c. We run it through our compiler, and here's a sequential code sequence. This has not been scheduled yet for VLIWs, or for our VLIW architecture over here. So we load we load the value. We increment our counters. We actually do the floating point add. We store the value back. We increment the array index, and then we loop. Seems simple enough. Let's see how this gets scheduled here. Well, because the architecture and because the compiler knows about the latencies here, let's say this load here has a few cycles of latency. So it's going to actually schedule this add later. And the add, it's a floating point add. This has a couple of cycles of latency also. So it schedules the consumer of that result here, this F2, later. And yeah, I don't know, it can sprinkle in the array additions and the counter additions kind of somewhere free. It has lots of open slots, but let's say it schedules it at the same time as the load in the store. So this is pretty cool. We are actually executing 2-wide parallelism here, and we didn't need all the extra overhead of in-order superscalar. Oh, and we can even schedule the branch somewhere. OK, so first question here, how many floating point operations are we doing per cycle? Are we doing very well here? This looks pretty poor. We have one floating point operation here, just this add. And we have 1, 2, 3, 4, 5, 6, 7, 8 cycles. Yeah. So we're having 0.18 or 0.125 floating point operations per cycle. It's not that great. We do have some parallelism. You know, we're executing 3 instructions here. It's better than nothing, but we're not really using the machine very well. Our out-of-order superscalar would probably try to take instructions that are below here, maybe intermix them, try to reorder a bunch of things, and try to run faster. So what's a technique to go faster? Well, one of the big as I said, we have a lot of emphasis on compilers in this unit. One of the things the compiler can do is it can actually unroll the loop. So here we have our loop. We unroll it 4 times. And now we're going to sort of take the loop overhead, and we're going to factor it out such that it only happens once every 4 times. Ooh, that sounds good. We're probably going to do some more work here per each iteration in the loop. But things get a little more complicated. What happens here if n, big uppercase N here, our terminating value, is not a multiple of 4? Well, we need to do something about that. We probably need to check sort of before we go to execute here whether we're doing OK or whether we actually are a multiple of 4. Conveniently, if n is big enough, we probably can run as a multiple of 4 for a long period of time, and it's only the last iteration that we have to clean up. But we need to generate some cleanup code, and the compiler is responsible to do this. So these compiler optimizations do take some effort. OK, so let's look at the scheduling now of our loop unrolled code. We can do a bunch of loads up front here. So we've intermingled these loops. And what's kind of cool is we can actually pull out the loads and sort of throw them to the top, and the stores and push them to the bottom, and then put all the adds sort of in the middle, and maybe sprinkle the array updates somewhere else. And when we go to actually schedule that, we're going to do something similar. We're going to have the loads executing first, execute the floating point adds, have the floating point stores, and have the result. But what you can notice here is we're actually starting to get some overlap. Because we've unrolled, we can overlap this load and the first floating point addition, because we've effectively covered the latency of our functional units by putting other loop iterations during that time. So if you look at this schedule versus the schedule back here, we've just sort of taken these dead cycles and we've put the other loop iterations in those dead cycles. In this loop unrolled case, we're incrementing these counters and the indexes not by 4 anymore. We're incrementing by however many times we've loop unrolled times the offset. So we're incrementing it by 16 now. Does that make sense? Because in this code here, we were incrementing R2 by 4, because that's the size of a single value is 4 bytes. So we have to sort of move our array index over by 4. But now, because we're batching up all this work together, we actually have to move the index by a bigger value. So we're moving it by 4, because we've unrolled 4 times the size of the data value, which was 4. So we're moving it by 16. And one of the nice things here, if you look, is in both the loads and the stores, we're using our register indirect addressing mode here to add in some offset. So we're actually offsetting, let's say, 12 plus this base register of R1 to figure out where we're actually doing the load from. But it's just sort of a convenient way that we don't have to compute a bunch of addresses. OK, so going back here, we can see we're starting to overlap actual operations with other loop iterations. Well, that's really cool. So we're starting to get some performance here. So let's look at the performance. So we'll ask the same question here. How many floating point operations per cycle? Well, hopefully it's higher. 1, 2, 3, 4. Divided by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 cycles. OK, so that's 0.36 is a lot better than 0.125. So this is good. Loop unrolling is helping us. But is this everything, or can we do more in our compiler? So the smart compiler people came up with even a fancier idea, which is called software pipelining. So it uses a term we've seen before, pipelining, but does it in software. So the idea here is that instead of just having one loop, unrolling the loop, and then overlapping the iterations, we're actually going to take multiple of these schedules and interleave them. And try to fill some of these empty slots. So let's look at this. We're going to have the code unrolled 4 times. This is the same piece of code we had on the previous slide. And we're going to draw our schedule that we had before. So here's the schedule we had before in purple. OK, that doesn't look so bad. But now we're going to schedule it with another iteration of the exact same 4-time unrolled loop, shown here in green. So we've just overlapped this with this other iteration of the loop. Well, are we done here? Well, not quite. We still have some open slots here. So let's try to overlap even another iteration, as shown here in red. Now, the fix-up code that you need to have to do this correctly gets more complex. Because all of a sudden now you're basically overlapping multiple iterations. But as long as you don't modify some value, as long as you don't do a store speculatively or a store, you're probably OK. Because otherwise you're just doing loads. You're doing extra loads, doing extra work. You're doing extra work, and you're filling slots thinking that you're not going to have anything go wrong, or thinking that the index variable n, if you will, is multiple of 4 and large, and you're not at the end. So let's put some names to these things. So we call the beginning here the run-up, the prologue. Here we actually have our sort of actual iteration. And you can see that the, sorry, this is in green. That doesn't show up very well. There are instructions here. There's adds. It's pretty full. We're actually doing a lot of work on our VLIW machine here. And then the epilogue here is when we're done. This is when we're falling out. We're sort of at the last loop iteration of the outer loop, if you will. So let's do some math and look at the performance of this. OK, so that's the same question here. How many floating point operations per cycle? Well, we go look over here. We have 1, 2, 3, 4. And we have 4 cycles in our tight loop case. That looks pretty good. That's cool. We just got a bunch of performance. But we had to do a lot of compiler optimization to make this work. But we were able to use the parallelism in the machine, and we were able to overlap 3 different iterations of this loop that we also did a software transform to unroll it 4 times. So this is called software pipelining. And I have a nice picture here to sort of show what's going on visually. So we're going to have time on the horizontal axis, and we'll have sort of activity of how many instructions are executing or something like that on the vertical axis, or shown here as performance. When you run multiple loop unrolled iterations, you have sort of some startup, you have the actual, you're running the loop, and then you come down from that. And that's better than having a lot of startup and sort of come down with a very small loop iteration portion here in the middle. But when we go to look at software pipelined, we can overlap basically one iteration of loops execution with, or one loop's startup or with the loop iteration of another loop. And we can actually execute sort of our prologue, execute multiple iterations very tight, and then have our epilogue here. Yeah, so our software pipelining, we're only paying the startup and wind down costs once for the execution of a loop and not every iteration of the loop. So that's fun. That's cool. We're getting performance. If only the world was dense loops, life would be easy. Alas, the world is not all loops. If we just had a processor which just did dense array calculations, and all of our problems in the world were just dense array computations, life would be really easy. But they're not. A lot of times code has lots of branches, it has if-then-else clauses, and here we sort of graphically show something like a if-then-else. So we have some piece of code, it makes a decision. It either executes the code on the left or executes the code on the right, based on an if statement. So this is the if true statement, and this is the else clause. And data-dependent branches are a problem typically for very long instruction word processors. Now, why is that? Well, in an out-of-order processor, you can try to execute code sort of around the branches and move instructions above the branch and below the branch. But if you're doing static scheduling, when you hit this branch, and let's say it's a hard to predict branch, you can't really do anything because you've packed a bunch of instructions next to each other and they need to execute atomically. So it's not like you can sort of move code up and down across that branch. The Superscalar can do that because it has this instruction window, it has a bunch of techniques, a bunch of hardware to be able to do that. But in our VLIW processor, that's a problem. So I wanted to introduce a compiler, an important compiler nomenclature here, which is important for this class. It's called a basic block. So what is a basic block? A basic block is a piece of code which has single entry and single exit. So this is a basic block. It has one entry and one exit. And why is single entry important? Well, if you can jump into the middle of this piece of code, the compiler cannot necessarily reorder the instructions inside this block. And if you have multiple exits, and say you exit here, the compiler can't push instructions below that exit point. But if you have a basic block, the compiler basically knows that this instruction sequence is going to execute effectively atomic, but not actually atomic. I mean, you can have other things going on inside there, but from a compiler perspective, it can reorder the instructions around in here to get better performance. Okay. So loops are easy. We can software pipeline. We can unroll. Squirrely code, if then else, spaghetti code, a lot harder. So the compiler guys came up with some fancy tricks to make VLIWs work better and to take advantage of some of the code motion that a out-of-order superscalar does, but in the compiler. and not in dynamically in hardware. And one of the more famous ways to do this is something called trace scheduling, which was John Ellis's, who was one of Josh Fisher's students' thesis work. And this was in the Bulldog compiler out at Yale. So what you do is you profile the code. And you come up with the probabilities that these branches go the one way or the other way. So when I say profiling, this is not something that the hardware is doing at runtime. This is something that you do with the program while you're sort of still back in the compiler stage. You take the program, the compiler goes and runs it on some a given input set, and comes up with probabilities of which way things go. And then what you do is you take this profile information, and you come up with some guess at what is the most probable one. And we're going to circle that here and say these darkened edges are the most probable sort of path through this squirrely piece of code, given this is the entry point. Now, this doesn't mean that you can't have branches that sort of branch out of this. But if you do, you need to have some fix-up code. Because what we're about to do is we're going to take this entire sort of big swath of code here. We're going to remove all of the branches. And we're going to schedule for our VLIW processor as one big monolithic piece of chunk of code. And by doing this, we can move instructions, let's say, that are down here, which there's open slots to execute in the early portion of this code sequence. We can move them up. And likewise, we can move things that use the result of long latency instructions up here and push it down across branches. So our out-of-order superscalar does this with branch speculation. But our compiler can do this on our VLIW processor using trace scheduling. But when we do this, we have to be careful, because there's always the possibility that, while unlikely, you can still branch the other way. So typically, the way this is done is you have some form of fix-up code that if you branch away, you have to sort of fix up anything that was after the branch that made a committed change, if you will, to the processor state. You need to sort of roll that back somehow. So we're basically in software doing the rollback case from our out-of-order superscalar. So instead of taking the architectural register file and copying it to the physical register file on branch mispredict, instead our compiler generates a code sequence which does that same operation if you were to branch away here. And we'll roll back only the certain registers that need to be rolled back and only the memory state that needs to be rolled back. So that's pretty cool, is that we can basically take a lot of the functionality that was done in our out-of-order superscalar and put it into software using trace scheduling. This is a rich field in the compiler research world. And there's been a lot of problems with VLIWs, or classical VLIWs. And people have sort of built things that are somewhere between superscalars and classical VLIWs to solve some of these problems. People have come up with fancy compiler optimizations to solve some of these problems. And some of them are sort of still open. First one on our list here, object code compatibility. In a superscalar, because we came up with one serialized instruction sequence, and the architecture came up with all the scheduling, you could change the number of functional units under the hood in your microarchitecture of your processor, and no one was ever the wiser. It would still execute the piece of code. It may not be optimal, but it would still execute. That's not necessarily the case for classical VLIWs. So you have to recompile the code when you change the microarchitecture. So it's a very tight coupling between the architecture and microarchitecture, because our instruction encoding now says there's exactly, let's say, 2 integer, 2 memory operations, and 2 floating point operations, something like that. But all of a sudden, if you build a machine which has a different mix, your schedule is completely wrong, so it's going to have bad performance, and it's just not going to execute because you probably changed the instruction encoding standard when you go and make that different VLIW. Another big problem is code size. As you can imagine, there's a fair number of no operation instructions or no operation operations inside of a VLIW bundle. If you can't fill a slot on a superscalar, you just don't put the instruction. On a VLIW, if you can't fill the slot, you have to put a no-op there, because you got to put something there. So this causes some serious problems. Also, things that hurt this even more is these fancy techniques that we talked about, loop unrolling, software pipelining, that bloats the code size. We're replicating code. We've unrolled the code. We're using more space. This hurts our instruction cache size and instruction cache footprint. We'll talk a little bit more about this in a few slides, but variable latency operations are very hard to deal with. So if you have a load, you don't know whether it's going to take a cache miss or not. So your schedule may be wrong if you guessed wrong. You can do it with some high probability. You can say, oh, I think this load usually takes a cache miss. Or you can say, oh, I think this load usually doesn't take a cache miss. But you can guess wrong. And there's similar sorts of things with this, with sort of branch mispredictions. Scheduling for statically unpredictable branches. This gets very hard. There are some techniques to solve this. There's something called predication, which we'll talk about in a few slides, that helps to solve this. So you can add things back into the architecture, into your VLIW architecture, to deal with sort of short branches that are very hard to predict, or data-dependent branches. And as I said, depending on your design, precise interrupts can be challenging, to say the least. If you're actually using the EQ model, you probably have a hard time figuring out what to do on a single step, or if you actually have a branch sort of in the middle while you have a pending operation going on, sort of undefined, it's icky. It's sort of similar to having like branch delay slots and having a fault in your branch delay slot. What do you really do with that? Also, this is an interesting point here, is that does the fault, if you have a fault on, let's say, one operation in a bundle, does the entire bundle fault or just the operation fault? Or take an interrupt? Typically, the way people implement this is you have the entire bundle or the entire instruction be atomic. So if anything in the bundle takes a fault, you actually don't allow any of the sub-operations to commit. That's kind of the most rational thing to do. People have done things in the middle. I probably don't recommend you building any of those machines. And the VLIWs that I've always built, an entire bundle is atomic. That makes traps a lot easier. But people have not always done that. One of the interesting cases, if you think about this, if you have, let's say, 5 instructions in a bundle, and only one of them faults, maybe you handle that one, but you let the other ones commit, and then when you come back, you have some sort of mask to say which ones you need to re-execute. People have built things like that. They get tricky. OK, so let's talk the rest of today's lecture and next lecture, we're going to talk about techniques to solve a lot of these problems or solve a lot of these challenges. Some of them are compiler, some of them are hardware, and some of them are both. First thing people try to do is they try to come up with compressed instruction encodings or fancier instruction encodings. But when you go to do this, it makes the front end more complicated. So here we have, let's say, some instruction. But inside of the instruction, we can have different groups, which inside of the group executes parallel, but between groups is not parallel. So something like the Itanium processor, which was the IA64 processor from Intel, actually looks something like that. Other things you can do is you can have compressed instruction formats. And then when you go to actually execute it, you uncompress the no-ops into your instruction memory, maybe. That's what multi-flow trace processor did. this marking parallel groups is what I was talking about before. Sidrome had an interesting solution to this. They actually had a single operation VLIW instruction. So to save space, they sort of had their wide instructions. But if you had a case where you were only going to execute one operation in an instruction, there was a special encoding format just for that case. And that saved a lot of encoding space, or a lot of instruction space, if you will. Another example of this actually is a processor I worked on called the Tylera Tile64 processor. We were a 3-wide VLIW. We had an encoding standard, or we have an encoding standard, which allows you to execute either 2 instructions at a time or 3 instructions at a time. And that can, when you're executing 2 instructions at a time, you have a richer palette of instructions you can execute. So it's sort of something in the middle. It gives you some better code density benefits, but not with the sort of complexity of having sort of compressed formats and things like that. OK, so that's one way to deal with the instruction encoding challenges. One thing you can think about, though, is you can just have a bigger iCache, or and a wider bus from your iCache out to your memory system. That does solve a lot of these problems. That costs hardware, but it's sort of a simple, stupid solution to the problem versus a smart solution. These sort of things on this list here are complex, smart solutions. Simple solution, just have a bigger instruction cache. And if you have bigger code sequences, you won't feel the performance hit as much from that. OK, so now we're going to sort of go through different problems with VLIWs and different solutions to those problems. Sort of the top one on this list is a problem of hard to predict branches and how that can limit instruction level parallelism. So you just remove the branch. And we're going to call that predication. So we're actually going to add instructions to the hardware, which we're actually going to add 2 instructions here. So this is limited predication, where we add 2 very simple instructions. And if you look at these instructions, they're very similar to the question mark colon or the select operator in C. So what does that operator do? If we have A equals I don't know, C question mark D colon E, semicolon. What does this do? Well, it loads A. If C is true, it loads A with D. If C is false, it loads A with E. Well, you can think about actually doing this with some sort of if-then-else piece of code, which is pretty common. If A is less than B, so you can sort of put that here. X gets A versus X getting B. That's our select operator. Well, we can add two special instructions here for our limited predication. Move if 0, and move if not 0. Well, what does this do? Well, if this operand is equal to 0, then this RD gets RS, else, and that's all it does. That's all that instruction does. And the flip one here is it checks if it's not equal to 0. Why is this cool? Well, this allows us to transform control flow into a data instruction. So we taken a branch out. So if we look at this piece of code, if we were doing it with branches, set less than, we do a branch. So this computes our condition code flag here. Branch equals, and if it's the one way, it branches here. If not, it jumps over it. So we have a bunch of control flow here. We have 2 control flow operations, the branch and the jump. when we add these instructions, we can basically do that if then else in an instruction. And basically every VLIW processor you're going to look at is going to have predication, or at least limited predication. This is not full predication. This is limited predication. We'll talk about full predication in a second. OK, so let's think about that for a second. We just took control flow. We turned it into something which is never going to take a branch mispredict. That sounds pretty cool, because branch mispredicts, were pretty bad. If we had a branch which was hard to predict, we didn't know with high probability if A was greater than B or not, we can just sort of stick this code sequence in here and just be done with it. And why this is really important for very long instruction-oriented processors is because whenever you take a branch mispredict, you're basically having a bunch of dead instructions, and you can't schedule something in that point. But a out-of-order superscalar can attempt to sort of schedule things in there. We can try to schedule non-dependent operations. But our compiler has to come up with some code sequence and has to make them parallel at compile time. OK, so a few questions here. What happens if the if-then-else has many instructions? This was a very simple case here. We just sort of had one thing inside of each of these if-then-elses. It's not the end of the world. What you can do, and typically what people do with partial predication, which is what this gives us, is they'll actually execute both sides of the if statement, interleave them in your VLIW somehow, and then choose the result at the end with a predication or a move z instruction. Or these are typically called conditional moves. If you go look in something like x86, I think these are actually called cmove. If you go look in MIPS, it's called move z, but people sort of name these things slightly differently. So it's not the end of the world, but when you go to do that, you're actually going to execute extra instructions that you may not have to have executed. And that's a bummer, because you could very easily, if there's a lot of code in here and a lot of code in here, and you're executing both code sequences, you're basically doing twice as much work. And if it grows large, you're doing lots of extra work, and you may not have enough open slots to sort of fulfill that. At that point, you have the choice. You actually put a branch in. If it's unbalanced, also not the end of the world. It's probably actually a little bit easier. You're probably not going to execute twice as much code. At some point, though, you may want to actually, if it's super unbalanced, like 1,000 instructions on the one side of the branch and like 2 instructions on the other side of the branch, you may just want to put a branch, an actual branch there, and not try to predicate it. Because if you took the side which only has 2 instruction, or the 2 instruction case, well, all of a sudden you've bloated that by an extra 1,000 instructions kind of in the common case, and that's not very good. So that's partial predication. Let's talk about full predication, which is kind of the extension of that. Instead of just adding a simple instruction which moves data values dependent on another value, it being 0 or not, let's say every single instruction in our instruction sequence, except for maybe, let's say, branches or something like that, can be nullified based on a register. What does this look like? Well, here we have some little bit more complicated piece of code. We have 4 basic blocks. It's roughly an if, then, no, see, if, else, then, and then sort of some code at the end. And let's see how this works with predication. Well, what you can do is, first of all, you have to somehow set the predicate registers. So typically, these architectures have extra registers, which we call predicate registers. The predicate registers get loaded with some values sort of early. And then, let's say this instruction and this instruction execute in parallel. Different notation here. Let's say there's just a semicolon here, and there's sort of brackets around that. And this, in front of the instruction here, in parentheses, we have a predicate register, which says whether this instruction was supposed to execute or not supposed to execute. Now you can do even more complex things than our partial predication. Instead, now you can basically execute everything and not have to do any moves at the end. You don't have to do any bookkeeping, and you can only execute just the sort of side of the branch that you need to execute. Scott Melke in ISCA 95 showed that if you do this and you sort of have a fancy enough compiler, he was working at UIUC on the impact compiler, you can remove, let's say, 50% of your branches. A lot of these branches are sort of short little branches in your programs. And with full predication, you can do some pretty fancy stuff. This showed up in the Plato compiler, which was a HP, or the Plato architecture by HP, and the sort of compiler for that, which was the Wenmei Hu's project at UIUC, the impact compiler. So you can sort of see that you can get a lot of benefit from this. So I'm gonna stop here today, but I just wanted to briefly wrap up and say we started talking about how to deal with dynamic events and how to get a lot of the advantages of speculative execution from out-of-order superscalars, but in a statically scheduled regime. And we're going to talk more about how to do some of this code motion, how to move instructions across branches, how to move memory operations across other memory operations. And then we're going to talk about how to deal with some dynamic events, which are hard to deal with in a statically scheduled environment in the next lecture. OK, well, let's stop here for today. So today we're going to continue our discussion of very long instruction word processors. And we're going to start talking about how to change a classical VLIW processor into a processor which can actually get a lot of the parallelism and instruction level parallelism you can get inside of out-of-order superscalars. And to do this, we're going to have to add a lot of extra features to a traditional or a classical VLIW. And we're going to slowly work through that. And we're going to basically list out or enumerate all of the possible different types of instruction level parallelism and where that comes from in something like an out-of-order superscalar. And we're going to systematically add features into a very long instruction word processor or VLIW processor to get us to that point. But I'll give you a hint that not all the things that out-of-order superscalars can get are easy to get in VLIW processors or even possible in the realm of things that people have built up to this point. So before we do that, I wanted to take a step back and review something from last class and also review something from, I wanted to clarify something that I had said about how the EQ model and the LEQ model, or the equals model or the LEQ model, work from a scheduling perspective. So let's back up to slides way back at the beginning. And more of what I wanted to say was just a comment that the equals model of VLIW scheduling and the less than or equals scheduling model are just scheduling models. That's all they are. They're not actually something that's in the hardware. They may influence what the hardware has to do or what the hardware has to provide. So for instance, if you have an equals model and you have an instruction followed by another instruction in your very long instruction word processor, and let's say the instruction reads the value of some register in sort of the shadow of while that value is being computed, you're going to get the old value in an EQ model. So as a quick code example here, we can take a look at a bundle of instructions here. Let's say you have something like a multiply, R1, R3, R4, and in the same bundle or in the same VLIW instruction, we have some other random thing here. We're going to use the curly braces here to denote that it's one instruction or one bundle. And then this multiply, we'll say, has a latency of 4 cycles. So you can't actually go read the result. And if you look at something like an EQ model, we're going to end up with, let's say we just have some other instructions in here. But this one here is important. We have an add. Which reads R1. Note this multiply writes R1. But as we said, the multiply has a latency of 4 cycles. So this, in the EQ model, is going to get the value before the multiply. So it's not going to pick up this result. And then, let's say we just have some other random stuff. I don't know, maybe some non-dependent adds and subtracts. And I'm not going to write the registers here because they don't read anything or write anything which is read or written in these two bundles. Maybe you have a no-op. And then finally, down here, we have something which does a load of R1 and gets the result of this multiply. So all I'm trying to get across here is this is a scheduling model of what the compiler needs to do and where it needs to place code that we're talking about in these scheduler models. It's not a hardware problem. If we were to try and take the same piece of code and run it in an LEQ model, the main difference is this add here, which reads R1, would not be allowed in the shadow here. So what would the shadow of this multiply, or the delay of the multiply? Because if you were to, for instance, take an interrupt or something like that, and this add were to get moved later than this load, or move more than 4 cycles later, or 3 cycles later, you would actually pick up the new value, and you'd basically change the semantics of your program. So if you were to do this in something like a LEQ model, this add would have to be above the multiply, and you'd have to replace this with a no-op. But more of what I'm trying to get across here is that these are just scheduling models and not actually scheduling models that the compiler wants to use and not models, or not hardware models. The hardware has to implement something which makes sense for the scheduler model. But when we talk about these different concepts, they really are just a software scheduler model. OK, so now we're going to go back forward here and move on to new content today. OK, so we left off talking a little bit about how to encode instructions in a VLIW, or how VLIWs encode instructions. And as you may recall, in a VLIW instruction encoding, you have a very long instruction word. So it could be, I don't know, many, many bytes. So if you go look at something like the multi-flow processors, the multi-flow trace processors, they had very long instruction words. They could, I think, execute something like, in their largest machine configuration, 20-some instructions. And they had to encode this. But one of the challenges was that you didn't necessarily want to have all of that encoding space used all the time. So if you are executing a simple instruction or something which doesn't actually need all the encoding space, you end up with a whole lot of no-ops. Or if you have a very long dependency string in your execution trace, if you will, so you have an instruction which is dependent on the next instruction, which is dependent on the next instruction, which is dependent on the next instruction, and you cannot fill any of the extra slots, you're going to end up having a lot of no-ops in your program. So how do we go about solving this? Couple different solutions here. Sidra 5 went off and added a particular instruction, which is a single operation instruction, and used a much smaller amount of memory. So this would effectively reduce your instruction cache pressure. There was compressed formats in memory, so you can hold your instruction sequences in memory, and then when you go and pull it into your instruction cache, it would expand to the fully expanded version. And this is kind of like a compression algorithm. You're basically compressing your VLIW instruction sequences, because otherwise these things are very, very large and have lots and lots of zeros or no-ops in them, because the probability you're going to fill sort of 20 instructions per cycle is low, but you want that capability there in case you actually do want to execute 20 instructions per cycle. Another solution here is what's actually used in the Intel Itanium or IA64 processor line, and also the TI DSPs, the C6000 series. They have the ability to effectively mark where a bundle starts and stops. So it's something sort of between a variable length instruction and a fixed format VLIW instruction. So we'll talk more later in today's class about how IA64 or Intel's Itanium handles this. But roughly what happens is they have a fixed instruction format, and you can fit sort of 3 instructions per bundle, or what they call a bundle. And then if you want to go over that, you can keep going over that. And they have special bits in their instruction which says, oh, well, this is going to express some more parallelism later. So you need to look at the next bundle and try to fetch that bundle, and that's all can be executed parallel. So it's still a parallel execution semantics, but the formats are not necessarily fixed. And this is sort of outside the bound of classical VLIW. Now it's going into a little bit more modified VLIWs or more contemporary VLIWs. So today we're going to, as I said, talk about how to go about getting all the performance that out-of-order superscalars can get, but in the context of a VLIW. So we're going to slowly build up all the different techniques that out-of-order superscalars have and all the ways that they can get instruction-level parallelism, and then apply that inside of VLIW, or how we make small changes to classical VLIWs to get a lot of the performance back. OK, so let's talk about the first trick here. One of the questions that comes up, or the problems that comes up here, is if you have branches and they mispredict, this can limit your instruction-level parallelism in a VLIW. OK, so why is this worse than in a out-of-order superscalar? Well, an out-of-order superscalar can dynamically schedule around branch mispredicts. So if you branch mispredict, you can basically schedule other code or speculatively schedule code depending on your prediction. But on something like a VLIW processor, that's a lot harder to do because you don't have a dynamic scheduling engine behind there. The compiler had to go do all that scheduling statically at compile time. So how do we go about fixing this? Well, one solution is just to eliminate all the hard to predict branches. So you take out the branches that might be hard to predict. So your branch predictor is trying really hard. You could still have a branch predictor in your VLIW processor, but some of these things you don't know. It's like a data-dependent branch. How do you know which way it's going to go? And this is a problem even for superscalars, but at least in a superscalar, you can try to sort of backfill instructions or try to do something or move around, if you will, loads or long latency instructions around branches. So in the out-of-order superscalar, you can potentially move a load beyond a branch. But in a VLIW processor, that's not easy to do because the compiler has to make that decision whether that branch is going to predict taken or not taken. And that may change over the lifetime of the program. And it may also change as the depending on the sort of input sets to the program. So it may not be something that's compiler time even knowable. OK, so our first technique here that we're going to use is called predication. So let's define what predication is. Well, first of all, predication is a technique that allows you to basically change the result of a register based on some other register. And it's going to let us transform hard to predict branches into data flow or data dependencies. So we're going to add something to our instruction set, and it's going to take what looks like a small branch or a short distance branch, and we're going to basically execute both sides of those branches, or the taken and the non-taken code path, and then at the end, decide which one was the right one with something like a select operator from C. So this is like the question mark colon operator, which no one ever uses in C. This is sort of the equivalent of that, but we're going to do it in one instruction, or maybe 2 instructions. So let's take a look at how this helps with small branch regions or branches which are hard to predict. So we're going to introduce two instructions. And I also want to point out that predication sometimes shows up in superscalars, processors, or sequential instruction sets also. So a good example of this is two instructions very similar to this are actually in x86. They're called cmove, or conditional move. And we're going to introduce conditional move as the most basic form of predication. So let's look at the semantics of these two instructions we add for conditional move. First instruction here, move 0. So what does move 0 do? Well, move 0 tests whether one of these input operands here, RT, is equal to 0. And if it's equal to 0, it's going to move RS into the result register, or the destination register here. So it's going to move RS into RT, or RS into RD if RT is equal to 0. And if RT is not equal to 0, it's just going to leave RD alone. OK, well, on first appearances, that seems like a very simple instruction. It's basically just doing a copy operation. It's a gated copy. It looks a lot simpler than something like add or subtract. We don't have to do any math, at least. There's no compare. I mean, the compare is easy. It's just the equals. It's not a less than equals. So it's a pretty simple instruction. And we're also going to introduce move not 0. So it's kind of the complementary one of this. And we're going to want this because when we go to execute code, we're going to want to, let's say, have an if then else, and we're going to want to execute the then and the else at the same time, or roughly at the same time, or indiscriminately, not dependent on the branch. And at the end, we're going to decide which one was the correct one. And we need sort of two instructions here to choose, well, was the positive one the right one, or the one where the conditional value is true or false the right one, or the one where it was true, or vice versa. So move not 0. Move not 0 is going to do the same thing here. It's going to see, except the sense of the condition code is going to be different. It's going to sense if RT is not equal to 0. And if RT is not equal to 0, then RS is going to go into RD. Else, we're just going to leave RD alone with the original value of RD. OK, so let's walk through a quick code example here and see how this helps. So here we have a code example. We have some C code. We have non-predicated MIPS-like assembly code. And then we have a MIPS-like assembly code here with these fancy two predication instructions. And all three of these are doing the same thing. So let's look at this piece of code here in the C code. It's probably the easiest to understand. It's going to start off, and it's going to say if A is less than B, so as a condition, and then there's a then and an else. So what does this actually implement? Well, this is a minimization function, or a min function. X gets the minimum of A or B. If A is less than B, it gets A. If A is greater than B, it gets B. So it's going to assign to X the smallest value of A and B. And these sort of if-then-elses, you can see here it's pretty short. We don't have a whole lot of code in either the then case or the else case. And that's going to be important in a second. You'll see why. Mainly it revolves around if you have lots and lots of code, or one of the sides of the branches is long, it may not make sense to actually predicate this, because there's some cost to predication. OK, so here's some assembly code, does a similar sort of thing. Set less than, this is a comparison operation in MIPS. So we're going to do set less than, and these are going to be R2 and R3 are going to have our two A and B values here. If it's less than, we're going to put it into R1. If not, this gets set to 1 or 0. And then we have a branch 0 here, effectively. What is this? This is a branch. OK, so branch equal with 0. It's a little odd. We probably should have just put branch 0 there instead. but it's going to check to see whether this value is 0 or 1. And if it's the one direction, it's going to jump to L1. If it's the other direction, it's going to fall through and then jump over this move. And these two moves here are the two assignment operators, the x equaling A or x equaling B. OK, that's not so bad. Let's analyze how long this takes, how many cycles this will take to execute on a sequential machine. OK, it does this set less than. It's 1. It does this branch. So that's 2. Let's say the branch is not taken or falls through. 3, 4, and then the jump over. So it's going to be 1, 2, 3 instructions in the one. Is that right? 1, 2, 3, 4 instructions in the one case. And the other case, it's going to take the branch and jump to here. So it's going to be 1, 2, jump over all this stuff, 3 instructions. OK, that's not so bad. So the one case is 4 and the other case is 3. They're different. Now, something else that makes this interesting is, let's say this branch is mispredicted. It's a data-dependent branch, A and B. So what's a good thing to predict here? Can our branch predictor do a good job on this? I don't know. Depends on what you know about A and B. If the compiler knows nothing, or the hardware knows nothing, you're not going to be able to do a particularly great job. So let's say it's a data-dependent branch, and it's 50% the one direction and 50% the other direction. Is this going to slow down our execution? Well, sure. It's going to slow down our execution because all of a sudden, when we take a branch, one of the directions, whichever way we predict, the mispredict path is going to add some mispredict penalty. So instead of the one path being 3 and the other path being 4, let's say the branch is predicted, I don't know. Let's say the branch is predicted not taken. So it predicts the fall through case. So all of a sudden, the fall through case is going to be 1, 2, 3, 4 instructions. And let's say we have a 2-cycle branch mispredict penalty. So let's look at the other case. So the other case is going to be 1, 2, and then 2 cycles of mispredict. So that gets us up to 4. We're to branch over 5. So it's going to be 5 cycles. So all of a sudden, we have our branch mispredict penalty coming into the equation here. And 2-cycle branch mispredict is relatively benign. If that starts to go longer, then you really start to have problems with this. OK, so let's take this code sequence and look about how to predicate it. So if we're going to go predicate this, we're actually going to execute both sides regardless of the value of the if clause or the conditional clause here. So if we look what we do, we actually have restructured the code here a little bit. And this is our compare. This is our if still up here. We have a set less than. And then we say if R1 is 0, move R2 to R4. Else, just leave it alone. And then here, if R1 is not 0, move R3 to R4. And what's important to note here is this non-destructive operation, especially here in this last instruction, is really important. Because if the move 0 was executed and that copied a new value into R4, and then this move not 0 were to somehow change R4, you lose that result from this previous one. So this really depends on these operations being non-destructive if their condition is not true. OK, so let's analyze this from a number of instructions perspective. First question is, does this matter what happens to the branch or what happens to the condition? Is it going to have different numbers of instructions or different numbers of cycles dependent on the direction of the condition? Well, no, there's no branch. Nothing's going to change. So in all cases, this is just going to take 3 cycles. So all of a sudden, we've transformed something which can take, as I said, if let's say you have a branch mispredict penalty, 4 cycles or 5 cycles. So on average, let's say the branch is taking 50% of the time either direction. We'll split the difference there, and we'll call it 4.5 cycles on average. And we've turned it into something which takes 3. Well, that's a great win. So where else is this useful? Does you always need to have if, then, else clauses to make this work out? So no. This also works good for small code hammocks. So I say a small code hammock is just a if which jumps around a small piece of code. And if you can't predict that if very well, then it makes sense just to go execute effectively what's inside that code hammock, or that small piece of code, always. If, for instance, you have 2 instructions inside of a code hammock, and your mispredict penalty is like 10 cycles, and you don't know whether the branch is being taken 50% of the time either way, all of a sudden, your average mispredict penalty is going to be something like 5 cycles. You could have just executed the code in the middle, and it would have been faster. You could have executed the 2 instructions and then just done a conditional move at the end, and that would have been basically always better. OK, so we bring up some questions here. What if the if, then, else has lots of instructions? So let's say we have an if, then, else here, but there's 1,000 instructions here and 1,000 instructions there. Should we predicate this? Let's say the branch mispredict penalty, as I said, it's 10 cycles, and it's 50% either way. But there's 1,000 instructions in the if, the then clause and the else clause. Well, no, that would never make sense to do, because you're basically doubling your code, and if there's a lot of code there, you'd be better served by just doing the branch, because you'd be taking something that was could be 1,000 instructions and turning it into always 2,000 instructions, or doubling the number of instructions executing, versus just adding, let's say, 10 cycles of branch mispredict penalty, or an average 5 cycles of branch mispredict penalty to your 1,000 that you have to execute. So all of a sudden, you're adding a little overhead. So where this predication really helps is for small pieces of code where you don't necessarily know the branch outcome, or can't predict the branch outcome very well. OK, what if the code is unbalanced? So you have an if, then, and an else. But the then clause and the else clause are very different in size. So one is 3 instructions, and the other is 1,000 instructions. Does this make sense? Well, it goes back to the same argument we had before with the very large if, then, else clauses. If the code is really unbalanced, you have a lot in the then clause and a little bit in the else clause or something like that, and let's say the branch is taking 50% of the time, it might make sense just to use an actual branch there and deal with the mispredict penalty costs versus trying to somehow predicate it. Because in effect, what's going to happen is, let's say you have 3 instructions and 1,000 instructions on the 2 different sides. You're going to be executing, if you predicate, 1,003 instructions every single execution time, plus maybe some sort of conditional moves at the end, some overhead involved. Versus if you have 50-50, and you have to add a little bit of a branch overhead penalty, your 50-50 chance is going to say, well, I'm taking 1,000 plus 3, and I'm going to add those 2 things together and take the average of them, basically. So it's going to be, what's the average of that? It's going to be like 501 or something like that, or 502 cycles. And that's going to be better than always executing 1,000 cycles. Let's see, anything else we wanted to say here? Yeah, one last thing I wanted to say here before we move off this slide. Move 0 and move not 0, or sometimes called C-move, conditional move instructions, are what are called partial predication. And we're now going to move on to full predication, where we can actually put conditions on every single instruction in our register, every single instruction in our ISA. But this is a little bit easier to do than full predication. This is sort of the first step that people typically implement, and it's called partial predication. And just to hammer this home one more time, predication is really turning what was control flow into a data flow operation or a data operation. OK, so let's take a look at full predication. Full predication, we're actually going to change the instruction set such that all of the instructions can be, or almost all the instructions are executed conditionally based on some predicate. If the predicate is false, the instruction is not going to do anything. It's just not going to have any side effect. So let's look at a code sequence here. So in this code sequence, we have an if, then, and an else, and then some code after we're done. So here we have if. A little bit different. This is not actually in MIPS code. This is something just sort of pseudocode here. But it's going to say, this is our if here. If A is equal to B, then branch to B2, else fall through. Here we're going to execute our else clause. And when we're done, we're going to branch over the then clause. So not anything interesting here. 4 basic blocks. I don't know if we've introduced this term yet in this class, but I wanted to introduce the term basic block. Basic block is a piece of code which has strictly one exit point and one entry point. So you could enter it from other places. You can jump to it from other pieces of code. But once you enter the piece of code, you're going to execute the code all the way to the end, and then there's one place you can leave. So you can either jump to someplace else or branch, and you can fall out to 2 different places. But the exit point is only one place. So what we're going to make the differentiation here is the piece of code can have, for instance, 2 branches. That's not called a basic block. That's called a bigger type of block. But this is a compiler term. And it's just good to know. OK, so let's apply full predication here. So these are relatively short code hammocks. 2 instructions here, 2 instructions there, and 2 instructions in the else, 2 instructions in the then clause. This looks like a really great place to think about predicating. OK, so let's take a look at the predication here. And I want, before we do that, I wanted to just say that one of the big reasons that we're trying to predicate on a VLIW in particular is in a VLIW, we have lots of extra, or we could potentially have extra parallel execution slots. So in our instruction sequence or instruction encoding, we have extra places to put code. So it may not actually hurt us to predicate. Because a lot of times when we go to predicate, we're basically going to execute both sides of the if, then, and else. And it's bad if we have to execute both sides of the if, then, and else, and they're big sequentially. But if you try to sort of slide them up next to each other, if you have extra no-op slots or extra slots in your VLIW, you can actually decrease the critical path through your program. So let's look at this, and we're actually going to do this in this example. So in this example here, we took this piece of code and added full predication. So when we say full predication, we added some extra things to these instructions. They look a little strange at first. So here we have instruction 3, instruction 4, instruction 5, instruction 6. And these are the same ones that were back over here. But instead, we added some extra words in front of them here, or these parentheses with P's in front of it. What that is these are predicate registers. So we're going to add a second register file into our processor where we can store effectively 1-bit values, sort of true or false values, that are going to determine whether this instruction executes or doesn't execute. Excuse me. So what this means is if P1 is 1, execute this. If P1 is 0, nullify this instruction 3 here. And we have a double pipe here. What am I trying to show with this? Well, I'm trying to show that this is parallel. This and this are executing at the same time, because we have a very long instruction word processor. We can execute multiple things at the same time. And what we've done here is we actually slid this up next to the then up next to the else. And we're going to execute them at the same time, dependent on these predicates. So this is the else block, and this is the then block. We're going to execute concurrently. OK. Sort of stuff before the if, stuff after the if then else is all done. That's sort of from that 4 basic block example. What's this instruction? This instruction has very interesting semantics. And this is something that you probably have to add if you're going to try to have full predication. OK, so it's a compare. So this is our comparison. If A is equal to B, and then it writes into 2 outputs. Ooh, that looks broken. That looks wrong somehow. How can we have one instruction write to 2 things? And what is the semantics of it? What does it write to here and here? Well, what this is actually doing is this is writing the positive outcome of this compare to the one, and the inverse or the negation of that to the other. And this is useful because then we can go use these predicates down here. We can use the positive one and let's say the negative one, and that can drive whether we execute the sort of else clause or the then clause. So lots of instruction sets that have full predication have either something like this. This is one option. You can actually have sort of 2 outputs, and you load 2 predicate registers. The other option is when you go to actually encode the instructions, you have sort of a not bit. So it denotes the predicate register. But when we denote the predicate register, we also denote whether we take the predicate register being true or the predicate register being false as what drives whether the instruction executes in our full predication scheme. So in effect, this is computing P and P bar at the same time and running them 2 different registers. And then we can use those separately down here. And interesting result here in ISCA 95, Scott Melke showed that you can, on average, let's say, remove 50% of your branches by using full predication. Now, full predication is not easy to build. Very few instruction sets have actually had full predication. Itanium was probably the closest to a real processor that was built that has almost full predication. It doesn't have quite full predication. The HP Plato instruction set, I think, actually had full predication. I think this is what Scott Melke was working with, or a derivative of that. So you can actually have instruction sets that people have thought about that have had full predication, but not all things are easy. So first thing, you need to add an extra register file for the predicates. You need to bypass those predicates. You need to compute them. There's some overheads involved, and we're going to talk a little bit more about that. OK, so let's take a look at our data path here and see where predicates fit into the data path. And we're going to focus actually just on the conditional move predicate or predication instruction here. We're not going to look at full predication just yet on the data path, but it follows a similar idea. OK, so what do we need to do? What do we need to add to our sort of boring MIPS-style 5-stage pipeline to add this instruction? OK, instruction comes in, moves down the pipe. Oh, this is interesting. I know, this is a really cool trick. Let's just, if this condition is not true, let's just kill the write back to the register file. It's brilliant. We just suppress the write back. We don't have to actually change our data path at all. We just put an AND gate in here. And this AND gate depends on this condition. Simple. It's easy. Maybe this is what we should do. Looks simple. We just add an AND gate where the big X is, and life is done. OK, well, that looks good. Can we bypass this value? So can we have an instruction that directly follows this move 0, or this conditional move 0, and reads RD? Well, where are we changing RD, or not changing RD? Where are we making that decision? Well, in this pipeline, because we did it in the write-back stage, it doesn't happen until down here. Down here in our write-back stage, or this wire, that's the write-back wire, runs all the way back into the write enable on a register file. OK, well, that doesn't really help us a whole lot, especially if we're trying to bypass, and we're trying to bypass out of here, our ALU, back around. Because at this point, we haven't figured out any way to suppress this. So we don't actually, we're not able to actually suppress that. So what do we think about this? So how do we go about doing this? So let's think about how to actually bypass out for this conditional move instruction. Because conditional move, it's just a simple comparison with 0. We should be able to do that in one cycle. We don't really have to wait to the end of the pipe to do that. And we want to be able to bypass it into a back-to-back instruction. OK, so how do we do that? Well, our bypassing doesn't work. What if we somehow pipe forward the original value and the new value? OK, so what do I mean by this? So this instruction is very interesting. It is much more interesting than your standard like add instruction. So why is it interesting? Well, let's look at the semantics very closely here. Move 0 is going to write RS to RD, or it's going to write RD to RD. Now you say, why do I need to write RD to RD? Well, in the bypass path, when we provide this value around, back to our bypass registers or our forwarding logic here, or bypass muxes or our forwarding logic, we need the old value of RD. So the traditional some sort of RISC pipeline here, we're only going to fetch our two sources, and we only write one location. So we're going to fetch RS or RT, and then we're going to write to RD. Now, all of a sudden, in this instruction, we need to read RS. OK, we need to read that because we need to overwrite RD with RS if the condition is true. And we need to read the condition RT. But aha, we may also need to read RD here. And this is because when we get to this stage here, and we want to use this bypass path to forward the value of what RD is going to be in the future, we need the original RD. So sort of to draw this a little bit more succinctly, because this is pretty important, we have if the register value of RT equals 0, we have R of RD gets RS. Okay, that's the easy one. We can count the registers here. One source, two sources, one destination. They're like simple. And what everyone always forgets is there's an else case here. And what does this else case say? Well, the else case is going to say register RD gets register RD. And you might say, well, RD already had RD. That's true, but our bypassing or our forwarding logic didn't have that. So we need to actually read this RD. So that means we need to read 1, 2, 3, and we need to write one location. OK, so that's going to cause us some problems over here. Because all of a sudden, we had our register file, which had 2 read ports. And we need to now have 3 read ports. So we need to add an extra read port on our register file. And this could be expensive. So if we actually want to build predication, it's going to have some cost. We might, if we want to build predication and actually bypass something like a predicated conditional move, we're going to have to add another read port to our register file. And that actually has some costs. And this is especially costly if you look at something like a VLIW. So let's take, for example, a 3-way VLIW, something like the Tylera processor. So it's a 3-wide VLIW. Each of those ways, or each of those pipelines is going to read 2, if you don't have conditional move, we'll say. And it's going to write 1 value. So it's going to have 6 read ports and 3 write ports. So it's a 10-port register file. No, excuse me, it's a 9-port register file to begin with. And if all of a sudden we add something like conditional move here, and we need to add these extra read ports, we're going to go from a 9-port register file to a 12-port register file, where you have, let's think about this. You're going to have 3 write ports and 9 read ports. That's hard to do. It's hard to build these really heavily ported register files. OK, so to sum up here, our problems with full predication is that you need to add another port to the register file. You need to bypass the predicates. So what I mean by that is you're computing predicates, and you want to use it in the next instruction. So if we go back to this instruction sequence here, we compute these predicates, and we want to use it very carefully, or very, very quickly after it. We don't have to wait to the end of the pipeline for those predicates to be computed. So that effectively is going to make it so that we're going to have a predicate register file sitting somewhere here, and we're going to have bypassing around the predicate register file, or forwarding of the predicates to get the predicates there faster, or get the predicates to be used in the next instruction. And you're going to have to add extra pipeline registers to pipe forward the old value, because you might need to keep the old value in the bypass. And in fact, actually, a lot of times when people do these things, they actually always write the register file and just pipe forward both, and at the end make the decision, or along the way they make the decision to go into the bypass or not. But then sort of when the instruction finishes, that's when they make the decision. So we're going to actually have to add more pipeline registers to pipe forward the old value that was in this case, RD. OK, so now let's start talking about how to leverage different more techniques to get a lot of the performance that we received in an out-of-order superscalar, but in a VLIW processor setting. And we're going to break this sort of into two different things. Dynamic events, so things that happen in the processor that you can't necessarily or you can't really do anything about statically. It's really hard to do anything statically about it. You just don't know what's going to happen. Something like a interrupt or an exception happening. How can a compiler know where the exceptions are going to happen? It's just not really possible. And then we'll talk about speculation, which an out-of-order superscalar does. And a lot of the things that fall into this case, actually we can add things to classical VLIWs to get us closer to getting those performance improvements, or the instruction level parallelism improvements that you can get from speculation. And we're going to talk about sort of two different types of speculation today. We're going to talk about how to move or speculatively move instructions over branches. So in particular, this actually gets really interesting with loads moving across branches, because you have a load and you want to move the load as early as possible. You want to pull the load up early into your program so that if it misses in the cache or it has to go out to main memory, you can hide the latency while you're doing other things. We're also going to talk about speculation of speculating that two memory addresses, one of a load, let's say one of a store, or you could also think about this as loads with loads and stores with stores, but we want to reorder those. Similarly, because we want to get sort of loads started early and stores started as late as possible, so we have enough time to do the computation we have when we do the scheduling. And remember, in VLIWs, we're doing all this scheduling statically in the compiler. And as you may recall, from an out-of-order superscalar perspective, when you try to do load-store speculation and try to reorder loads and stores dynamically in an out-of-order superscalar or some sort of superscalar processor, you need an extra structure to figure out when you made a mistake, when you reordered something that was not a valid reordering. And we're going to have to add that same structure into our VLIW processor, or a very similar structure. So let's start off by talking about what the compiler has to do, or how the compiler even starts to think about this speculation. So I wanted to introduce a topic here from compilers. And this is sort of an introduction to how we schedule for VLIW, the nitty-gritty of what the instruction scheduler or the back end of the compiler is going to be doing. So here we have two pieces of code. We have before code motion and after code motion. So what is code motion? Well, code motion is reordering of instructions in order to tolerate the latencies of the instructions, or to do something good. So it might not just be tolerating latencies of instructions. It might also be reordering for alignment issues sometimes. Sometimes branches can only happen on certain alignments, or the performance is better. So, but roughly, we're trying to reorder the code or do valid reorderings of the code. We can't just move a read after write dependence and move it someplace else. We can't say, instruction A reads the result of instruction B. We can't move A before B because it just wouldn't make any sense. But a lot of times, the compiler has some flexibility in what it can move around. OK, so let's look at this example case here. We have a gobbledygook of code. And what we're going to try to do here, well, two things to note. One, this branch at the end is dependent on register 16. Register 16, where does it get computed? Does it actually get computed anywhere in here? No. We're also saving away register 16. OK, so does register 16 get computed? Maybe not, but we probably want to give it as much time to be computed as possible. Some other things going on here. We have a load. OK, well, the load, what if the load cache misses? Well, this next instruction here is directly dependent on that load. So we probably want to give it as much time as possible to execute. So traditionally in code motion, you want to sort of push the loads up and push the stores down. Well, we're going to do this, if we were to push the loads as high up as possible and the stores down as possible, we're going to move a load and a store past each other. And the question comes up, what if this value and this value, these two addresses, are the same? Well, so let's assume that they're not, and let's assume the compiler can somehow prove they're not. So you should be able to do code motion here where we're going to rejumble all the instructions, and we're going to push the load up and push the store down, leave the branch at the end. So we've done some code motion. The next thing we're going to want to do is we're going to want to bundle or schedule the instructions. So when I say bundle, we're going to take several operations and pack them together into one VLIW instruction or one VLIW bundle. And we denote that here with these braces to say these execute parallel or at the same time. So first, you're going to sort of want to do scheduling. Then you're going to want to somehow bundle non-dependent instructions together. There's been a couple algorithms that have tried to do sort of scheduling, code motion scheduling and everything, and bundling together. Those don't always work out as well. So most of the VLIW compilers now will actually do the code motion and the scheduling first, and then they'll do the bundling at the end. OK, so let's look at our first technique here to get at instruction level parallelism, and our first type of speculation in a VLIW processors. So what's our challenge here? What's our problem? Well, our problem is the branches, or the presence of a branch, rather, is going to restrict the forms of code motion the compiler can do. So we have a branch. We have some code after the branch. If you have, let's say, an add instruction, that's pretty easy to move it before the branch. OK. How about an instruction which can take a fault or take an interrupt? Loads are a good example of one of those sorts of instructions. How is that possible? Well, a load can take a page miss or a page fault. It can try to access some value which is not mapped in by the operating system. So let's say we take this load and we move it above the branch. OK, that's not too bad. Now what happens if that load takes a trap or takes an interrupt that was never supposed to happen? In correct program sequence order, the branch was going to branch around the load. So the load was never going to execute. But all of a sudden, the load got moved up, and the load executes. And it takes an interrupt. Well, your program crashes. It takes either a segenv or a bus error if you're on like something like a Spark system, or you're basically taking a segmentation fault. Even though nothing went wrong, this branch was supposed to protect this load from never executing. So R1 here, let's say, just gets loaded with some bogus value if the branch is taken. And the compiler knew that, and the programmer knew that. But all of a sudden, the compiler decides to reorder things and has moved the load up now that, because it wanted to try to get more performance. This is something that you can do in your out-of-order superscalars also. The out-of-order superscalars are going to pull non-dependent loads up in the program and try to move them across branches. But in out-of-order superscalar, if you pull a load up and it does something wrong, it was speculative state. You just don't care about it. So we need some way to have loads that don't hurt the system. So it's a similar sort of idea, but we can't move this load above the branch because it might cause some sort of exception. So our solution to this is we're going to add special instructions, special versions of the instructions which don't take faults. So if the fault were to happen, it sort of remembers that the fault happened, but it doesn't actually interrupt the process. And this allows us to pull some of these instructions before branches, or reorder, perform code motion statically at compile time. OK, so let's take a look at this example here. How would we go about doing this? OK, so we're going to move the load up. So let's say we move the load as high as possible. We move it above these two instructions, instruction 1, instruction 2 here. And what do we need to do? Well, if you note, we don't have the word load here anymore. We have load.s. So this is a speculative load, which has different semantics. This load.s never causes an exception, even if it has like a page fault or a null pointer exception or unaligned memory reference or anything like that. It's not going to actually take that fault. Instead, it's just going to sort of remember that. And this is typically done if you look at something like Itanium, which is this is a sort of code sequence out of Itanium processors. in Itanium, what they're going to do is they're going to, the destination of the load, in this case R1, is going to be set with a poison bit. Itanium, this is actually called not a number. And what that means is the destination register of the load is marked as not there, or that it's not a thing or not a number. And what's important about this is when you go to use that value, that's when you take the exception. So let's take a look at an example of this. What we do is down here, where the load originally was, we put in a check speculative instruction. And it uses R1 here. So what this is going to do is it's going to check the value of R1. And if R1 took a trap or exception, and there was some problem with it, we can jump to fix-up code. So there'll be some other piece of code somewhere else we can branch to, and that fix-up code is going to re-execute the load and make sure everything is OK, and then jump back to the use. So it's speculation. We try to prove and we try to make sure that the common case, when we pull this load up, nothing bad is going to happen. But we put a check in just to make sure that this is the case. One other thing I wanted to point out here is these poison bits, or these not a numbers, they propagate. So why is this important? Well, what that means is, actually, I want to correct something you said a little bit here. If you try to use R1 somewhere else before you do a check, the not a number propagates. It doesn't take a trap. It only takes a trap, or only jumps to fix-up code when you go to actually do the use, or when you have a special check instruction, or there's another load you can put there that'll re-execute the load if the original load didn't work, a non-speculative load to the same value. OK, so why is this propagation of not a numbers important? Well, this allows you to pull code down here up and above this branch also. So we can pull the load up, we can pull dependent instructions up, and then just as long as we do the check at some point, and check to make sure that the load didn't take an exception or not a problem, we can basically speculate that the load is fine. We can speculate that the instructions dependent on the load are going to be fine. But if any of the dependent instructions on the load are not fine, that we've also speculated, when we go to, at some point in our code, we need to introduce this check instruction here, which sees if this value is not a number. So if it propagates all the way through your code, you have a load, a add, a sub, which all reads and writes, let's say, register, or somehow reads from register 1, and there's sort of a dependency tree from register 1 through that code sequence. At some point, you want to check after the branch has actually happened whether everything's OK. And because it all propagates, you can basically do work early and then check later. And when you do the check later, you can say, oh, I get it, everything's OK, and it has a value in it. If it has not a number in it, or it has this poison bit set, and it's propagated all the way through, at that point, and you can jump to fix-up code, which you can re-execute the load and all of the code you've pulled up, all that speculative code. And that's why you need fix-up code and not just re-execution of the load. Because the fix-up code might have to re-execute more than just the load. It might have to execute the load and all the code, the other code you pulled up in front of the branch. OK, so let's move on to another type of speculation. And this is data speculation. So in data speculation, our problem here is we have memory hazards that are going to limit our scheduling, especially if we have to do all the scheduling statically. So if you're conservative in your compiler and you can't prove anything about the different addresses, all of a sudden what you have is every single load is dependent on every single other load, and every single store is dependent on every single other store. Now I might say, why are loads dependent on other loads? Well, though loads and loads you might be able to reorder pretty easily, you have to worry a little bit about if one takes a trap before the other. I guess we could have already talked about how to solve that problem. But once you reorder a load in a store, then you start to have problems. Or reorder a store in a store, or anything with a store, then you start to have problems because all of a sudden you have some state that changed in your memory system that you have to make sure that in original program order, the later instructions actually pick up the result of that. So later loads or stores somehow honor the results of that. So it's really sort of focused on moving loads and past stores. So what's our solution? Well, our solution is to add some hardware check to guarantee that the pointers or the two memory addresses, when you do the reordering of a load in a store or a store in a store, that these addresses are not the same. And this is actually the same thing that we did in our load store queue or our load store memory disambiguation that we talked about in out-of-order processors. So it's the same sort of thing going on here. But we need to actually change the instruction set to handle this in a VLIW setting versus in the Superscalar, where it was all microarchitectural issues, sort of below the instruction set that no one ever had to look at. OK, so let's look at how to do this. We have a code sequence here, some instructions, a store, and then a load. Compiler can't prove anything about these stores and this load. But in an out-of-order Superscalar, it could guess or speculate that the load and the store don't share the same address. And if they did, it can basically roll back the code and re-execute the load. And we want to emulate something like this, but doing it all statically with the compiler. OK, so how do we do this? Well, this is something else that Itanium added and was also talked about in previous research VLIW processors or explicitly parallel instruction set processors. What you're going to do here is you're going to move the load up above the store. And this is basically speculating that the load and the stores don't hit the same address. And much the same way that when we reordered loads above stores in an out-of-order Superscalar, added the load address to a load store queue and a memory disambiguation queue, we're going to do the same sort of thing here. That when we move this load up, we're going to have a different instruction here of load and add. So what this is going to do is it's going to do the load and add the address to a special table, which we're going to call the address, what does ALAT stand for? Advanced Load Address Table. The ALAT is what Itanium calls this. So it's a structure that's a associative structure where you can put addresses in it and then check other addresses from other instructions against it. And if you get a hit or something like that, you know that something bad happened. And you can re-execute. So we're going to see here that we're going to have a load, which is going to get the load out in the memory system. We can overlap the time in the memory system with executing other instructions. We have a store here. Now, the store is going to take the address of itself. And we've changed the instruction set here because we added these two new instructions here and changed the semantics of a store. And it's going to check in the ALAT, or the Advanced Load Address Table, to see if the address the store is happening to is already there. And if it is, it's going to change the table somehow. And we'll talk about that in a second of what exactly happens. But roughly, it's going to take this address out of the table. And then when this load check happens here, this checks to see if the address is still in this table. And if it's been bumped out of the table, it jumps to fix up code, which is basically going to re-execute the load, or re-execute the load and all the dependent instructions on the load. So we can effectively do data speculation, but all in software. But this is going to require us to have an associative hardware block or some sort of content addressable memory, a CAM, that we need to add that all load addresses and all store addresses are passed across. And this is similar to how we had our memory disambiguation queue in our out-of-order Superscalar. OK, so let's look at the ALAT, the Advanced Load Address Table. OK, so what do we have in here? Well, three things. We store the address. We store the size. This is important so we know Is it word, double word, half word, byte sort of thing when we go to do matching. And when a load.a happens, it adds one into this table. And we denote the register number that is the target of this also. It's kind of useful to know when we go to do the check. This is to match up to make sure that the same load is the same load from before, and we can effectively remove the address from the table when we do the check. OK, so we added an address. OK, we're running along. And no, we execute stores, but the stores don't hit on that address. So when a store executes, what is it going to do? Well, it looks in this table and cams or does a comparison against all of the addresses with size matching and everything against this table. And if it's in the table, it removes it from the table. So by the time that the check or the load check happens, that address is not in the table then. So when the load check happens, it's going to look in here, this table again, and say, oh, I'm not in the table anymore. This address is not in the table anymore. So at that point, you can know, let's go re-execute that load. But if it's still in the table, that means no stores bumped it out of the table. So no stores in the interleaving time bumped it out. So the speculative load was fine. So we've effectively done what out-of-order superscalars can do. We can move now loads above stores. And through a change to our instruction set architecture, by adding these special check and load check and check instructions, and by changing the semantics of load and adding a load add or load a instruction here, we can change. We can have data speculation into our program. OK. A couple other things that are fun to add to classical VLIWs to improve performance. I just kind of want to breeze through these next two ones a little bit faster here. First one, multi-way branches. So problem, you have a VLIW architecture or very long instruction word architecture. And if you have, let's say, 10 things in one instruction or 10 operations in one instruction or 10 operations in one bundle, but you have sort of short branches, or maybe you have multiple branch decisions happening. You want to have sort of a branch every 3 instructions. Well, you have lots of wasted slots. If you can't somehow have one instruction branch multiple directions, now you might say, branching multiple directions, that's a really weird idea. How do you have an instruction go multiple ways? I thought branches could go 1 of 2 places. They could either fall through or go someplace else. Well, we can actually change the instruction set to have a branch that can go multiple directions. So let's look at this with a full predication example here. So we have 2 bundles of code here. This first one here is 3 instructions in it. These are all executing in parallel. And what this is going to do is it's going to do 3 different comparers. So this is similar to this is our full predication example here. It's going to write to these predicate registers with the logical positive and logical negative sort of versions of the predicate comparison. OK, so that sort of stages us to do 3 different branch comparisons. And then down here, we have 3 branches that all branch based on this predicate, or these different predicates that we already staged or set up here. And they can branch to 3 different places, label 1, label 2, and label 3. And this also could be fall-through code if none of the branches are taken. And one little wriggle here that you have to sort of figure out the semantics. And I should say Itanium actually supports this. So you can buy real chips with this in it. If you have 3 branches together, you need to somehow order these branches. Because let's say they all say taken. Well, or they all resolve to actually being taken. Well, which one do you take? Because you could branch to all 3 different places. And we want deterministic execution. So typically, when you have an instruction set like this of multi-way branching, you define some order. Maybe the first one has priority over the second one, which has priority over the third one, et cetera. OK, so let's talk about some of the other things that were on our list of limiters to instruction level parallelism, and ask ourselves, are these things which we can solve very easily? Well, things start to get harder pretty fast here. Like I said, dynamic events, they're basically things the compiler has no way of reacting to. Now, the instruction set might be able to react to it. You can add things into the instruction set. You can maybe take a branch dependent on a dynamic event. But let's look at some dynamic events. First dynamic event here, cache miss. Well, it's really hard for a compiler, just all things being equal, knowing whether a load is going to take a cache miss or not. It might have some guesses, and that could influence the code. But actually doing something about it. If you think about what an out-of-order superscalar does, if you take a cache miss, it'll reschedule the code around the cache miss. It'll take the non-dependent instructions, the instructions that are not dependent on the load, and pull those up and try to execute those. But if the load hits in the cache, you want a totally different schedule. You want to actually try to start executing the instructions that are dependent on that load as soon as possible. So an out-of-order superscalar has dynamic means to be able to do this. It has dynamic instruction execution. But our VLIW processor, which is statically scheduled, can't really do this. So what's some techniques to go about after this? One thing is something called informing loads. As far as I know, this actually has not been built in any hardware, but it's been proposed, at least in the computer architecture academic circles or in the computer architecture literature. And informing loads was actually come up, the original paper about this is by one of our faculty members, or one of our faculty members here at Princeton, Margaret Marinozzi wrote she's one of the authors of this paper. But the basic idea is that if you have a load that misses in the cache, you can not execute subsequent instructions. Else, you can or there's actually no else there. If the load misses in the cache, you just don't execute some subsequent instructions. You can basically nullify those instructions. And this allows you to change the code sequence dependent on whether the load hits in the cache or whether it misses in the cache. And this was done with Todd Mowry, Margaret Marinozzi, Professor Margaret Marinozzi, and Professor Todd Mowry, I think both when they were graduate students. And Mark Horowitz from Stanford was on this paper. I think a couple, I'm trying to remember who was the last author, the professor on this work. Another option is something that the Elbrus processor people did. So you've probably never heard of this processor. It was something that was built in the, well, I actually don't know if it was ever finished. I think they had a prototype of it. Sort of in the Soviet Russia day, right when the Soviet Union was kind of breaking down. This was the design house in Soviet Russia, which made all of these sort of military processors. They later went off, and that same design team was going to go build some commercial processors after the fall of the Soviet Union. So they went and they went to go build this processor, and it's a VLIW processor. It's some very long instruction word processor, and they had an instruction in there which tried to solve this dynamic event problem around cache misses. So what it said is, if an instruction misses in the cache, go execute a different piece of code with a different schedule than if the instruction, if a load hit in the cache. So you could effectively have two different code sequences. The compiler could actually generate two different code sequences, and you can get back a lot of the performance and get back to almost exactly what an out-of-order superscalar could do. Now, this processor never really made it commercially, and later the company went under and was bought. I actually don't know if the assets were bought by Intel, but at least all the people who worked at this company now work at Intel effectively. So they still live in Russia. So just a funny story there that, yeah, it didn't work out from a commercial perspective, but they had some cool ideas in there that you could actually try to schedule around branch mispredict, or schedule around cache misses. OK, so some other things. Branch mispredicts. Well, we already talked about one technique here, when you talk about you can add predication. But that doesn't help if you have big pieces of code, big code sequences, and big code hammocks. You can't necessarily predicate your entire program. So what do you do instead? Well, one solution that people have come up with for this, and this is a hard one to deal with here, is you can add branch delay slots. So you have a VLIW processor, let's say it's 3 wide, and you add branch delay slots in your instruction set, and then you use predication in the branch delay slots. And what this allows you to do is it effectively lets you mask some of the branch mispredict penalty and change the code schedule a little bit dependent on the prediction. Or change it actually completely based on what the branch is. And the way this works is in the delay slots, you use the same predicate that the branch is branching on. So the branch is branching on, let's say, if A equals B. Well, you use that same thing in the predication, and effectively you can reschedule the code differently depending on whether the branch is taken or not taken. And because you're putting it in the delay slot, you can sort of get around some of the problems here of whether it's taking the one direction or taking the other direction, no matter which way the mispredict happens, or whether the branches can be predicted correctly or not. And what we're doing is basically putting code in the delay slots that will always execute, but it can be predicated, and you can effectively pull code up from the 2 destinations of the 2 branches. So it's sort of a way to get around branch mispredict penalties here. This is actually done in a research processor that was built at MIT. And I think this is probably also done in some of the other HP processors. But the MIT processor, at least, was called the M machine out of Bill Daly's group. He's now at Stanford, but I think the M machine was sort of built right when he was moving from MIT to Stanford. But they had, I think, 3 delay slots, and they were 3 wide, and they could predicate the instructions in the delay slots. So last thing is exceptions. So you take an exception, and you want to schedule different code, and these are like impossible to predict. The compiler has no way to try to predict this. But this is hard on a superscalar also. When you have a traditional superscalar and an exception happens, they usually end up flushing the pipe anyway. So, and it doesn't happen that often. It probably doesn't hurt your performance that much. So no one's going to lose too much sleep over this one. So I briefly wanted to say something about how to build really wide VLIWs. As we start to go to wider and wider VLIWs, lots of instructions execute at the same time, you have to start thinking about what does the register file in the bypass network look like. So in this drawing here, we actually have a figure of the C64000 series processors. So these are TI DSPs. This is sort of the flagship DSP processors. And this is a sort of block level diagram of what they have. And what they actually have is they've divided the machine into local register files when they bypass inside of what's called a cluster. So it's a clustered VLIW. It's similar to how we have clustered superscalars, which also divide the register file. But this is an architectural, a big A architectural or ISA level architecture splitting or dividing going on here. So in something like the C64000, they actually have 4 instructions per cluster, so they're executing 8 instructions at the same time. And you can bypass values between these 4 ALUs within them, or you can bypass within these. But if you want to sort of take a value from here and move it to there, you have a very low bandwidth sort of bypass path here, and it takes an instruction. You effectively have to have a move instruction to move between the 2 different clusters. So there's a lower bandwidth between the clusters and a higher latency between the clusters, but inside of a cluster it's very fast. And what's important to know here is these are not 2 processors. These are all executing 1 instruction at the same time. So it's an 8 wide instruction executing on these 8 different ALUs. And this is used in the TI high-end DSPs. Also, it's used in HP's and ST Micro's LX processor. This is probably a processor you never heard about, but this was actually what Josh Fisher went on to go do at HP Labs after multiflow. So this is after sort of a lot of the original VLIW work. Same person. Went and built this LX processor, and this is sort of a joint collaboration between ST Micro and HP, and this shows up in printers today. So it's not something you're going to really have. The LX processor is probably something you're not going to have in your desktop machine. OK, so I wanted to just briefly give a case study here of one of the more interesting modern-day VLIW architectures, or probably the most famous and possibly also the most infamous VLIW processor out there. This is the Intel Itanium, also known as the Intel IA64, or what's known as an EPIC processor, explicitly parallel instruction computing architecture. And a lot of this work actually was done in collaboration between Intel and HP. HP uses these a lot in their big servers. They're sort of big mainframe, well, not quite mainframes, but big, heavy, big iron computers. And Intel was trying to use this to effectively kill all of the other workstation vendors. And this was going to be their 64-bit solution to computing. So it's a modern, non-classical VLIW. And this was going to be Intel's chosen ISA. They were going to deprecate x86 and choose IA64 as the 64-bit ISA. And as we now know, going a few years forward after the creation of all this stuff, that didn't really happen. Intel went and did this. It built a bunch of processors with this instruction set. You can still buy processors with this instruction set, but it never got as good of acceptance as the competitor. The competitor is what at the time was called AMD 64, which is a 64-bit extension to what people already had. And that's what people ended up wanting. It's just a 64-bit extension to what we already had versus something totally different. OK, so a couple features here. It's an object code compatible VLIW. So it's not quite a VLIW in a classical sense. It's object code compatible, which means different generations, different microarchitectures of this VLIW can have the same instruction code and the same binaries, and you don't have to recompile. And how they did this is effectively, as I alluded to before, they had the ability to have parallelism straddle across instruction bundles. And they had this notion of groups, which we'll talk about in a second. So first few implementations of this, Merced was the first Intel Itanium implementation. It's kind of like the 8086 for x86. But Merced, as lots of things, you'll realize if you look at Intel code words and Intel code names, named after a river. Intel likes to name their things after either rivers or places. I think this has something to do with you can't trademark a place name, so they just sort of get around that and make sure they don't have any trademark issues by choosing place names for all their code names. One of the big problems here, it was supposed to ship in 1997. First customer shipment, not until 2001. It's a 4-year miss. And Superscalar is another thing that sort of had caught up on it at that time. And it was supposed to be faster and better than everything else. And the first one was not very good. It had low clock rates and was not as high performance as it was supposed to be. And sort of the x86 side of Intel's business line actually had almost the same performance as the first Itanium, and then very quickly surpassed the first Itanium. So their high-end processor wasn't actually very high-end. Couple other things here. So McKinley was the second implementation, shipped pretty quickly after that. This was much better implementation, but it's still hard to do. But we're still building these things. So in 2011 at ISSCC, Intel introduced the Polson processor. Big machine here. 8 cores and 32 nanometer, lots and lots of RAM. We'll look at that. Yeah, so 32 megabytes of shared L3 cache, big processor. 544 square millimeters in 32 nanometer. So at the time this came out, this was the biggest processor ever built. Most number of transistors, so over 3 billion transistors. Or at least the biggest commercial thing. Intel might have had a research prototype, I think, that might have had more transistors than this. I think their multi-core processor, or their, what do they call it, the SCC, their single chip cloud computer might have had more, but I don't actually know the transistor count. But from a commercial processor perspective, huge chip. But they're selling it into extremely expensive sort of sockets. They're selling this chip for a premium. It's going into big mainframes. That was not where this was originally destined for. It was destined for both big mainframes and workstations. But now this is sort of the, in 2012, standing here now, this is not used in lots of other places except for sort of bigger hardware mainframe sort of things. So a few interesting things here is the cores are multi-threaded, and you can execute 6 instructions, or you can fetch 6 instructions per cycle, and you can execute up to 12 instructions per cycle per core. And then there's 8 cores. So this is a beast of a machine. Very high performance computer. OK, so let's dive into some of the details here of Itanium. Itanium has a 128-bit instruction bundle. And inside of there, you can fit the 3 operations. And then there's some what are called template bits, which sort of says what is in the instruction bundle. So it's not actually a fixed format bundle. These instruction boundaries can move around a little bit. And they did that so you can sort of mix in something like a immediate instruction with an instruction which doesn't have immediate, and get more space in the bundle for the immediate bits. So you can have, or branch offset or something like that. These template bits also describe how a particular bundle relates to other bundles around it. So sometimes these are called begin and end bits or start and stop bits. So it says the number of instructions which can execute explicitly in parallel. And the machine doesn't necessarily have to execute these in parallel. So for instance, if you say 20 instructions can execute, or 20 operations can execute in parallel, but your machine's only 2 wide, or they build a 2 wide implementation of Itanium or IA64, you just are going to execute 2 wide for 10 cycles or something like that. But what's really cool here is the compiler is able, just like all the other VLIWs, to express the parallelism to the machine explicitly. Some interesting things about the registers. Because this is a VLIW processor, and because you're going to have to do code scheduling like what we saw in last class, and that increases the general purpose register pressure. You don't have a register renamer. So you can't go and use different names for things, and the hardware is not going to rename things for you. So instead, the compiler and the software is going to have to do the renaming. So they had 128 general purpose registers and another 128 floating point registers. And they also had these predicate registers. So they're not quite full predication, but they're pretty close to full predication. So you can have bits that say whether later instructions are going to execute or not, and you have to compute that into a little register file. So they had a predicate register file that you have to bypass. So that's sort of interesting to see. And then they had a really interesting feature here, which is called rotating register file. And let's talk about what a rotating register file is. So the problem this is trying to solve is in a code sequence as we saw in last lecture. If you have a very long instruction word scheduled piece of code, and you want to get good performance, you're going to have to unroll the loop, and then you have to software pipeline the loop. But when you do this, this is going to increase your register pressure or increase your register names, how many register names you need to use. And as we saw, you're going to have to add extra special code in the prologue and the epilogue, which are different than the main loop body. So how do you solve this in one fell swoop? Well, you add a subset of your register space, which will sort of statically rename itself every loop iteration. So it'll slightly change the loop iteration or change the naming of the registers. And what this looks like is if you go to access, let's say, register R1, there's a register, sort of a architectural enabled register called the rotating register base, or RRB here, which has a value that gets added to this, and it's modulo arithmetic, so it rolls around at the end. And that points to different locations in the physical register file. Oh, this is pretty cool. So what we're going to do is every single time we come to a new loop iteration, we are going to change the RRB, and it's going to point to a different set of registers. And we can actually effectively software pipeline just by using this one feature. So here we have the same code sequence we had from last lecture. So it was the previous code example. And if we recall, when we unrolled all of this, what we ended up with was a load, an add, a store. We'll talk about this in a second. This was kind of the key thing we were trying to execute. And if we have to unroll this, we basically had to unroll the code and then look at the dependencies. So let's look at the dependencies here. Well, dependencies that we're going to have is this load writes F1, or the floating point register F1 here. And we know that this is actually going to want to get read. Let's say the latency on this is 1, 2, 3 cycles, and it doesn't get read till here. Likewise, this add here computes P10, and the add, let's say, is a floating point add. It has some long latency. And down here is when it's ready into the store. So on something like a Itanium with a rotating register file, we don't actually generate all this code. Instead, we generate one instruction, this, which is going to take care of our epilogue, our prologue, our epilogue, and the main loop. And what we're going to do is we encode the distance in register numbers between these two values here. So what this means is if this writes F1 and 1, 2, 3 loop iterations in the future want to read that value, we encode that here with a register number that is that number off. And then likewise here, so this would be F1 to F4 because it's off by 3. And here, this writes F5. And we know this wants to be read 1, 2, 3, 4 later. So we encode it with a register number that's 4 into the future. And now we're going to talk about this instruction here. So what this is going to do is it's going to change the rotating register base number, or the RRB, and it's going to bump it by 1. So we can basically just keep branching to itself here. And each time we do it, all the registers are going to change names. So by the time this is ready, or by the time the load is ready here, these other values will have sort of caught up with it, where the physical register that they're actually going to look at will now point to the correct location. So we can effectively encode into one instruction here all of this, including the prologue and the epilogue, using this rotating register file. OK, so last slide of today. Why do I think Itanium, I think we can pretty confidently say, failed? I actually don't think it was a lot of the ideas. I think a lot of it had to do with the implementation. So first off, if you tie the hands of the microarchitect, they're going to scream. So IA64 added a lot of architectural, big A architecture, or ISA level features in order to get a lot of the speculative parallelism. And a lot of that stuff was implemented and talked about, but never actually built in real processor. So people didn't go through the effort until basically the first Itanium to try to implement some of these things. And they didn't all mix well together. And they added a lot of state and they added a lot of complexity to the processor. So we have ALAT, full predication or almost full predication, rotating register files, to name a few. This really complex bundling sequence that's probably one of the hardest to decode instruction sets in the world. Very, very challenging. And this was a big challenge. And it tied the hands of the microarchitect. And the microarchitect couldn't make decisions. So a good example of this, and a funny story here is that after the DEC Alpha employees, Digital Equipment Corporation employees, left DEC and were sort of assumed into a part of Intel, that same team that used to build out-of-order alpha processors went on to go build sort of the next generation of an Itanium processor. And what they said is they went in to go look at the Itanium processor, and they're like, wow, this is really complicated. It took them much more complicated than alpha. And then they said, oh, well, we could probably do better if we just built an out-of-order superscalar, took apart all of the instructions, took apart all the dependencies, poured that data into what was effectively an alpha out-of-order superscalar core, and then execute it. And what was funny is if you go look at this is like all the people, you can sit there and just bang your head because you did all of this work and added all of this architectural state to allow the compiler to do all this work. And then they just wanted to undo it all. I mean, they would do this because they wanted performance, but then they wanted to undo all of the sort of state and all of this hard work the compiler did and just redo it all dynamically because they thought they could get better performance. They probably could have. It probably was a good idea, but what's kind of funny there is you built an instruction set that had one microarchitecture in mind, basically an in-order architecture, and then all of a sudden people are thinking about building out-of-order variants of it. And it sort of throws everything you had before away, or all these notions sort of went away. So it's just a funny story there that people tried to build out-of-order versions. They ultimately did not end up doing that. That same team decided it was basically too hard, mostly due to predicate registers and sort of how to bypass predicate registers of out-of-order things. And I think they ultimately ended up not doing that, or they definitely ended up not doing that. And that's what's sort of known now as the Wachusett or excuse me, nothing Wachusett. It's known as the Tukwila processor from Intel. Other couple of problems here. First implementation at a very low clock rate, so your first one out the gate just was not very good. This sort of hurt. And it's hard to build these things. They're wide. The speed demons versus the sort of brainiacs. This is this question of do you want to go wide or do you want to go long and narrow? Long and narrow was doing OK at the time. Big code size bloat. Fundamentally did not solve all of the dynamic scheduling problems that out-of-order superscalar could get at. So for instance, branching or changing your instruction schedule based on whether a load hit or miss in the cache, they couldn't do. Big compiler complexity, you needed profiling and not everyone wanted to profile. There was also just not that much in static instruction level parallelism in all programs, so the compiler couldn't necessarily find all the parallelism or it wasn't there statically. And if you're going for a compiler-only approach, you need to be able to do that. And then this is what really killed it here is the people did go build these more complex out-of-order superscalars. So at the time, there was this big discussion, can we build more complex out-of-order superscalars? And people said, no, those are too hard. They're too hard to build. They cost too much. We don't know how to solve all these problems. So instead, we'll try to build something simpler and push a lot of the complexity into the compiler. Well, there was money behind this question. So people went and did build these complex out-of-order superscalars. And that's what we're basically still using today in our sort of desktop processors. We have out-of-order superscalars today. And then finally, the last big one here, AMD 64 happened. What is AMD 64? Well, it's a 64-bit extension to x86. AMD originally did this. Intel, after sort of dragging their feet for a couple years on this, finally decided, oh, we're gonna use that because people wanted this. People wanted code compatibility with the ability to do 64-bit sort of wider, both arithmetic operations and wider addressing, so more amounts of memory. And 64 bits is a lot of memory. So AMD originally came up with this. This is now known as, I believe, EMT64 or Intel 64. not to be confused with IA64. That's what Intel calls now the 64-bit extension to x86. And now Intel's building those processors too. So everyone has sort of jumped on that. And Intel's kind of de-emphasized Itanium now in the Itanium instruction set. And instead, we're basically sticking with IA64 in this instruction, or IA32, the 32-bit x86 with extensions to 64-bit. And that's taken over the workstation market. And what's kind of funny here is this processor was really designed to kill or unify all of the workstation vendors together under one processor that was going to beat them all. And it did its goal to some extent. Because this processor was coming around, either companies went out of business or they jumped on the IA64 bandwagon and decided they were going to take that on. But what replaced all of the different little variants of processors that were in workstations. So Spark, PA Riskin for HP, SGI's sort of MIPS processors. I already say Spark. Yeah, all these sort of other different things, and Power by IBM. Power's still around, but a lot of the other ones sort of died through attrition or moved on to were supposed to move on to IA64, but IA64 did not end up winning this. Instead, we replaced it with 64-bit x86 processors. So it sort of did its job. It killed the workstation processors, but replaced it with not itself. It ended up replacing it with something else. Anyway, we're gonna stop here for today, and we'll talk more next lecture. Why is branch prediction important? So let's talk a little bit about motivation. Then we're going to move on and start talking about branch prediction and the two things we need to predict when we're predicting branches. And the top thing that jumps to mind is the branch taken or not, the outcome of the branch. But that's only half of the story. And today we're also going to talk about figuring out where you actually go when you take a branch. And when I say branch, we're going to loosely put all forms of control flow into this. So it's not just a branch, it's a branch, a jump. You might even think about trying to put something like a interrupt, because that changes your control flow of your program, but most people try not to predict their interrupts. It's hypothetically possible. But let's start off by talking about why branch prediction and what is the big motivation for branch prediction. So as I said, longer pipelines and more complex pipelines require us to have relatively good accuracy trying to figure out when we take a branch or when we don't take a branch. So here we have our in order fetch, out of order issue, out of order execute, in order commit pipeline. And a couple things you should note here is, we added this extra stage out here. We added this issue stage. But we also added this issue queue or instruction buffer here, or issue window, depending on what book you read, in the front here. Well, instructions pile up into this. And if you don't actually figure out if the branch is taken or not, let's say until somewhere here in the execute stage, then you're going to have more basically instructions you need to kill when you take a branch mispredict. So when you start to go to these out-of-order processors, when you sort of have this seemingly short pipeline, seemingly easy pipeline, more instructions can get sort of queued up into some of these structures, especially if you have a queue. So this effectively lengthens the front of your pipeline and makes it such that if you mispredict or you fetch the wrong instructions relatively often, you're just going to be out in the weeds. You're going to be killing lots of instructions and having done a lot of extra work that you didn't really want to do. So also, if you wait all the way to the end of the pipe in sort of these out-of-order processors to resolve your branch, that's also going to make life even worse here, because that makes your mispredict penalty even longer. Most people don't actually do that. I mean, you might say, oh, I don't want to actually kill instructions until I know the branch commits. And that was sort of our simplistic example we had when we were talking about these out-of-order processors, is we waited all the way to the end of the pipe and then sort of cleaned out things. You can wait for it to go to the end of the pipe to actually fully clean out things, but you're going to want to redirect the front of the pipe or redirect the fetch or the PC in the front of the pipe as quickly as possible. because you just don't want to be fetching off into the weeds, because then you're just wasting cycles. Here we have, going back to our super pipelining lecture that we had before, and we look at for some real processors, the Pentium 3 and the Pentium 4, what their branch mispredict penalty is. And in this Pentium 4 here, you have 20 odd cycles here of branch mispredict penalty. That can be pretty painful if you take branch mispredicts quite often, because you're going to be taking branches, and the branch penalty is going to be quite high if you don't have the correct subsequent instructions after you. Now, we talked about some techniques. You can just stall and wait, so you don't actually predict the branch. But then, if you have to wait for every branch to get to, let's say, the 20th stage of the pipe before you go and fetch the subsequent instruction, that's pretty painful. So we had talked about speculating the next PC, or the PC plus 4, we'll say in a MIPS-style architecture, or an architecture where each instruction is 32 bits long. But that doesn't really help you when you're trying to predict, or when it doesn't really help you if you have high probability you think the branch is going to be taken, or you think the control flow is going to be taken. So you need to start thinking about how to actually deal with that in a pipeline. And up to this point, we've only talked about speculating the fall-through case. We talked briefly about speculating the non-fall-through case, but we didn't say how you could possibly do that. And today we're going to talk about what the hardware is to do that. Also making life worse is if you start to go wide, this hurts also. So if we start to go wide here, let's say we have a dual issue processor, but if you go wide here, when you go to kill instructions, you're killing twice as many instructions in flight in the pipe if you take a branch the wrong direction or mispredict a branch. So showing that from our pipeline diagram perspective here, this is just recapping. We had seen this in a previous lecture. But here we have a fetch for this branch. And we're fetching 2 instructions per cycle here. So even for a relatively short pipeline, you end up with 1, 2, 3, 4, 5, 6, 7 dead instructions on a mispredict. So what this really comes down to here is you have the pipeline width, or approximately how much stuff you end up getting killed is the pipeline width multiplied by the branch penalty. So it's width times length before you can resolve the branch. And if you can shorten the time it takes you to resolve the branch, that's good. Or if you can make the processor narrower, that may be good. It's good from fewer instructions being killed, but we like to execute multiple instructions at a time because that improves our performance. So this is really the motivation for thinking about trying to put something useful in this time here, and also trying to reduce the probability that we start fetching incorrect instructions at all. So this brings us to some techniques. So we're going to start off by talking about prediction and how we can use branch prediction to determine 2 things, the outcome and the target address. So branch prediction. Everyone always thinks that it means this first thing. That's not what it means. It encompasses both things. You have to predict the outcome. So that's whether the branch is taken or not taken. And you also want to predict the target address. Now, if you think about that, the first one sounds relatively trivial. I could just sort of pull numbers out, or I could pull something out of a hat. Take it, not taken, just sort of choose randomly. It's going to do OK, probably. I could probably try to correlate it somehow, use some heuristics. The second part here, I have to get the number exact. So if I choose at random for my branch prediction outcome, I'm going to get a 50% right. Or if I just always choose, I don't know, we'll say we would just always choose not taken or something like that, we're probably going to do pretty good. But getting the actual destination correct, you have to be exact. You have to choose a number out of, let's say if you have a 32-bit instruction pointer, you have to choose some random number out of 2 to the 32 locations and get it right all the time with high accuracy. So we'll spend some time about this, talking about this and some strategies to getting the prediction target and predicting our branch target and our jump target correct. But you have to think about both of them, is all I really wanted to get across here. OK, so this is something is a little bit more review from something we had talked about in lecture, I think, 2. We talked a little bit about figuring out where we can resolve a branch. So here's a little bit longer pipe. 1, 2, 3, 4, 5, 6 stages. It's not quite our 5-stage pipe. I put a issue stage in here. And let's look to see where everything gets known. So we know that our target address for branches, jumps, and jump and link will likely be known here. But that's not really helpful unless we know which way the branch is, or rather, unless we know which way the branch is going or the branch outcome. Because even if we know, at least for jumps and jump and links, we know the outcome. It's taken. But for conditional branches, we may not know that until somewhere over here. So we can't necessarily use that information until later in the pipe for branches to do something useful in the naive approach. In the execute stage, we know the branch outcome. We talked about a trick in MIPS, at least, where we can try to pull that forward a stage into our decode stage by having some sort of special comparator on the output of a register file, comparing it with 0. But that doesn't work for all branch types. So if you have something like a branch equals, where you're actually trying to compare 2 real registers, you have to wait for the full bypass. Doing a 32-bit compare is sort of the equivalent of doing a full 32-bit subtract. You're not really going to know that until the end of the execute stage. That trick doesn't really hold water. It holds water for comparing with 0. You might even be able to do it if you have lots of extra time in your decode stage. But let's assume that you don't. Also, target addresses for jump registers and jump and link register. Jump registers, jump and link register, you need to read the actual address that you're going to out of a register somewhere. So this, you can't even have a chance of trying to predict it out here or the destination. It's pretty hard because, I don't know, it's somewhere in the bypass. You just compute some value, then you jump through it. So we don't, at least out in here, by the time we're done here, we have one of 2 addresses. We have both of the addresses that the branch could potentially go to. It could go to either the fall-through address or the branch target. And we know that sort of at the end of the decode stage. For jump and link registers and jump registers, we don't even have that information. It's not encoded in the instruction anywhere. It's encoded in a register. So we need to go fetch something from the register. It might have to go through the bypass network. So we're going to have to wait. So let's look at some techniques to deal with outcome prediction for branches. And we're going to look at this mostly, first of all, in the static domain. So things that are not trying to watch the dynamic instruction sequence, but instead can basically statically analyze the instruction sequence and with some high probability, we'll say, try to predict the location. The first technique is actually not a prediction at all. The first technique, we had talked about this a few lectures ago, or we talked about this in lecture 2, adding delay slots. So instead of, I don't know, having that time just be dead cycles when we're trying to resolve the branch, let's say we put if we don't resolve the branch till here, we have, let's say, 1 delay slot, 2 delay slots, 3 delay slots. and we have 3 instructions, we'll say. Or maybe you can redirect at this point out of X, and you have 2 branch delay slots, depending on how you sort of wire that in, if you can make the cycle time. Let's say you have 2 branch delay slots. What ends up happening is you have instruction BEQZ here. Let's say that is at address 100. And then you have 2 instructions which execute no matter whether the branch is taken or not taken that follow it. So these instructions are in the delay slots of the branch. And you could have architectures which have things like load delay slots and other things like that. But for right now, we'll talk about branches. And we can force these instructions always to execute. Unfortunately, if you go look at the sort of percentages of probability you can actually fill these delay slots, it's pretty low. It's always not easy to find work to shove down here, because you're basically taking work that was above the branch and in the compiler reordering the code to put the instructions that were before the branch after the branch. OK, well, this is good. I mean, if you could actually make this work out, this is great. One of the problems with this, though, is the probability of filling 1 branch delay slot, let's say, is 70%. And the probability of filling 2 branch delay slots is even lower than that. It's maybe 50-ish to 40-ish%. As we said before, if you have a monkey pulling out of a hat, or just some random process pulling out of a hat, you're going to do 50%. Correct. So, and as we'll see today, if you use some more fancy branch prediction or the outcome prediction techniques, you can get the prediction accuracy of a branch all the way up into the sort of 95, 96, 97% probability, and all the way, and people have built, if you go look at your sort of out-of-order Superscalar, it's on your desktop, your Core i7 these days from Intel, that's probably somewhere in the neighborhood of 98 to 99% correct. So being able to fill these delay slots with some probability, which is less than 98%, is not a good trade-off. You would have better been served possibly by allowing some fancier prediction mechanism trying to fill it, if you care about performance. Now, if you care about complexity or reducing complexity in area, a static prediction might be a good way to go. So let's look at some basic rules of thumb here about static prediction. So the overall probability the branch is taken, let's say, out of something like spec_int is 60 to 70%. But it's not equally distributed. Backwards branches have a much higher probability of being taken than forward branches. OK, so we got a question coming up here. Why is this? Yes, so loops with high probability, or by definition, to be a loop, you're going to have to jump backwards. If you jump forwards, it's pretty hard to loop. So if you jump backwards, it's a loop. And in fact, people like to execute loops and stay in loops for a while, because that's where a lot of work is done. So if you're sitting in a loop and you're just spinning in this is increasing the probability that the backwards branch is taken, and that has a high probability. So that's this half. Forward branches, 50%. Can we, what's going on there? Forward branch, 50% going forward. These are usually some form of data-dependent branches, like an if-then-else clause. So that's why the probability of this is much, much lower. You sit in loops for long periods of time. Forward branches typically sort of are if-then-elses, and there's you're checking some data value, and then you're either executing or not. Now this gets a little trickier with some more advanced compiler techniques. Because sometimes with advanced compiler techniques, you will actually effectively convert a loop with an if-then-else into it, or a condition check at the end, into a unconditional backwards branch, and then a little sort of branch that goes around the piece of code which checks the loop sentinel, or checks whether the loop is completing or not. But even that's actually not a horrible thing, because at least that backwards branch will always be predicted taken 100% because it gets turned into a jump. So that's not bad for performance. It's just might change these percentages a little bit. But things do like to sit in loops, is what you should take away from this slide. OK, so let's think about a technique to try to take advantage of this. So one technique that you can take advantage of this with is actually to add extra bits to your instruction set and allow the compiler to hint to the architecture whether the branch is taken or not taken. Now, this is still a hint. If it gets it wrong, we still want the correct execution. So if it takes a branch, we still want to go correct. We still want to execute the right piece of code, but the performance might just be worse. So let's take a look at two branches here. We have branch.t and branch.nt. Branch.t is a branch which is taken or predicted taken, and branch.nt is a branch that's predicted not taken. So what do I want to say about this? Well, architectures do have this. I was going to say the Itanium architecture actually has static branch prediction completely. Some things have sort of intermediary things with this. For instance, the Motorola 68K kind of has something like this, but not. You can't do it with all branches. So this does exist in real architectures. And one of the things is that this can actually be very accurate, especially if you profile your code. So if you run the code once and you allow the compiler to see which way the branch was taken, it can do quite good. And some of the insight here is there's a lot of branches in a program which are there just to check error cases. And the probability that they actually are taken or not taken one way or the other is one that can basically almost be statically determined at compile time. And definitely if you have feedback information of execution of the program once, that's a very good indicator. So for instance, if you had a loop, the compiler would denote that the backwards branch is taken. So it would put a br.t. And if it's, let's say, some piece of code which just jumps over an error case and checks an error condition, and 99% of the time that it never falls into that, it would predict that taken, because it would just jump over that little piece of code. So you can actually have very high prediction accuracy. Now we're not up into the 99% here yet, or something like that. This isn't great. We're still doing static things here, and at this point it might actually make sense still to have a delay slot, because we're still not over our 70th percent. We're sort of a close trade-off here. You have to get the static prediction correct, and your delay slot might actually still be a better approach at this, depending on sort of how this accuracy compares up to how many times you can fill the delay slot. But let's take a look at what happens in the pipeline here. So here we have a branch taken, and it's predicted taken to this target. We still end up with a dead cycle here because we do not know where that target is until we've effectively decoded the instruction. So that in this sort of intermediate time here, we just have to fetch, let's say, the fall-through case or something like that. But because we predicted it taken, we could do better here. We don't have to have two delay slots or two dead cycles. We can fill it. We can actually get the correct next instruction in here for the target. This branch not taken, let's say we speculatively execute the fall through, we don't actually have any penalty for a correctly predicted branch here. So if we predict this branch not taken, that's the fall through case. We can just fetch PC plus 4, PC plus 8, and just keep executing, and we have no penalty there. OK, so if we get the hint wrong, what are we going to do? Well, we've effectively taken a mispredict penalty here. And if you look at the branch taken case and you take a mispredict penalty, what's going to happen here is you're actually going to end up having two dead cycles because we don't actually determine whether we took the mispredict or not until this execute stage. And that's the soonest we can go redirect the front of the pipe. Now, if you look at this and squint really hard, you can see that we actually fetched op A twice here. This was the fall through instruction. It is hypothetically possible that you might be able to not hold off killing this instruction, if you will, and in this case, sort of have the pipe do something special and actually end up getting the instruction after op A or op B here, if you will. But that's pretty hard to do. So for the base case, we'll just say that you end up with an extra cycle of mispredict penalty when you mispredict. Yeah, so just to reiterate that, what I was trying to say here is that with a branch taken, we fetch the subsequent instruction, the fall through case. We fetch the target of the branch. We try to kill this, but lo and behold, we actually end up fetching the exact same instruction again. So you could, if you really wanted to, try to optimize around that and not fetch this twice, but then you're kind of having things out of order in the pipe here, because you'd have this instruction's dead, and you have to figure out how to kill sort of sub-portions of your pipe or things out of order in your pipe, and that gets pretty hard to do. But this does really quite well if we do static software-based branch prediction. OK, so let's look at hardware branch prediction. Now, when we say hardware branch prediction, that does not necessarily mean dynamic hardware branch prediction. This could just mean that you have the hardware doing the prediction without any hints from the software. And we have a couple different cases we can try to implement, heuristics, if you will, in hardware. The first one here, always predict not taken. This is what we've done so far in all of our pipelines that we've designed. We predict fall through effectively, and we just fetch PC plus 4. We didn't put a name on it, but this is actually what we were doing. We were doing speculative execution with a static hardware branch prediction of PC plus 4. It's pretty simple to implement. It's what you guys have done in your labs so far. You know the fall through early. Accuracy is not very good. You get all your loops wrong. All your backward branches of your loops just are always predicted wrong. OK, let's do the inverse here. Predict taken. Let's have that be our static strategy in hardware. Well, kind of hard to do here because we don't really know the target of this branch in decode. So it's like going back to here. If we predict everything taken, what do we fetch in this cycle? Well, I don't know. It's a big question mark there. It doesn't do super well on if-then-else's, because a lot of times those are sort of forward branches over things, or some depends on how you structure it. Some architectures which have things like these static prediction techniques will actually restructure their code such that the compiler will figure out the probability of a branch being taken or not taken, and then work the code around it to make it work out. That's actually pretty common. The Motorola 68K had something similar to that, and the compilers there actually try to work around it. So, well, this is definitely a bummer here. Maybe we can fix that. Like we said, this is the second part of today's lecture, is trying to fix this problem. OK, how about we use a heuristic that all backwards branches are taken, and the forward branches are not taken. OK, so this does a lot better. This is our heuristic of what we were saying before, that loops and things like that will get caught up in this. So a forward branch is not part of a loop. We'll predict that not taken. We'll predict the fall through. Backwards branch will predict taken. This does pretty good. It's better accuracy. It's still nowhere near the sort of 80% accuracy that we had if the compiler could get involved, because that's effectively the compiler case that we were talking about before could actually implement this entire algorithm in software, or something much more sophisticated, and that's usually what ends up happening. OK, so that was one way to figure out the outcome. Let's look at a little bit more dynamic way. OK, so we can try to build pieces of hardware which determine the outcome of a branch dynamically. And this is by adding extra little pieces of hardware somewhere in the front of the pipe. So somewhere in our PC+4 calculation, there's going to be this multiplexer here in the PC+4 calculation. And effectively, we're going to use some piece of hardware to feed into that. And this is our taken and not taken prediction values. And we'll talk about this in a second. But one of the questions here is, what things feed into this PC+4 hardware? Well, one of them is going to be PC+4. One of them should be your branch target. Unfortunately, as we said, we don't know the branch target till here. So we can't have that come around in one cycle. So we need to hold off. That's this target address question. But first thing is, how do we swing this multiplexer here of our next PC? OK, so some solutions to this that are dynamic in hardware that try to increase the prediction accuracy is we can think about having something which exploits the nature of programs. So what we're going to try to exploit, first of all, is temporal correlation of a branch, a branch outcome with previous outcomes of that same branch. So if you're in a loop, and you fall into a loop, and you have a branch that's predicted taken, or let's say you have a branch that is taken, you can use that in the future to predict the outcome of that same branch. So here we're actually going to have a 1-bit predictor, as denoted by this finite state machine. And what's going to happen is, let's say we start in the not taken state. If the outcome of a particular branch is not taken, we just stay here. We continually predict not taken. If we then take a branch, if we then end up taking a branch, we transition over to this other predict taken state, and we sit in there if we're not taken. And if we have alternating branches, taken and not taken, we're basically going to be predicting the wrong one. Or, well, we might have been predicting the wrong one every single time. But we can implement this with 1 bit, 1 extra bit to our control logic. It's not a lot of logic here. It's literally 1 extra bit. And it just says which of these 2 states you're in. Let's take a look at the performance of this. Does this help? So let's say we have a loop here that iterates 4 times. So we're going to graph the iteration number. And then we're going to show the prediction that's coming out of the predictor, this 1-bit predictor. And then we're going to look at what actually happened. And we're going to see if we predicted right or wrong. OK, so in the first iteration, let's say we train up the predictor. It says not taken. It starts off as not taken. That's the start state. We're going to predict not taken. It was actually taken because we're going to loop 4 times in this loop. So we mispredicted. That wasn't great. But then it transitions from the not taken or predict not taken state to the predict taken state. So the next few times we iterate the loop, we're going to get it right. Now this is a relatively short loop. We only run it 4 times. But if you have a loop that executes 100 times, this might actually do OK. OK, but then we look at the end here. And well, the fall through case at the end of the loop, we're going to predict taken, but we actually fall through. This is the last little bit of our loop. That's not great. So here, if you look at prediction accuracy, this is 50%. This was not very good. Let's try to execute the loop again. And I just kind of wanted to show here, the reason that I show a second execution of the exact same loop is to show why the start prediction was not taken. The second time we come back to the same loop, we left this predictor trained up to be not taken. So now when we go to execute again, we come in not taken, and we mispredict the first time, correctly predict the second time, correctly predict the third time, and mispredict the fall through case. So that's why you need to sort of execute this loop twice here to see what the common case is with sort of the loop back to back. Otherwise, if we were to change the start state, you might end up thinking that this predictor does better than it actually does. So that's not a whole lot of magic there. It's simple. It does OK. Can we do better? Well, we're nowhere near 99%. So the answer is going to be yes. OK, so what happens if we start to have more bits to do prediction? So here, instead of having one extra flip-flop added to our computer architecture or our processor pipeline, we add 2 bits to our processor architecture. We add a 2-bit saturating predictor. So what do I mean by saturating? Well, what this means is we start off, let's say, in the strong not taken state. And then if you have a predict taken, it moves here. If you have another predict taken, it moves here. If you have another predict taken, it moves here. So we slowly can we have a range here, if you will, of taken. So we have weak taken, strong taken, weakly not taken, strong not taken. And we can sort of move across the spectrum as we reinforce the taken or not takenness of a branch. So still not quite rocket science. There is some subtleties here. Effectively, we're introducing hysteresis into the prediction that we're trying to do here, or our prediction algorithm. And that can help. So let's see how that helps. So let's execute the same loop here. Another time here, let's start off with strong not taken. Strong not taken predicts not taken. And the first time we execute this loop, well, it was actually taken, because loops like to be taken. Well, that's a mispredict. But we transition from strong not taken over here into the weak not taken state. So something actually happens. That mispredict was not in vain. The second iteration happens, and we still are predicting not taken, because we're in this weak not taken state. And we did take it, so we mispredict again. But now we actually transition to the weak taken state. This time, things get a little bit better here. We're actually going to have a prediction of taken. The actual thing is taken. We predicted it correctly. And then finally, 4 here, prediction of taken. It was actually not taken. Sorry, this is actually a mispredict here. This is incorrect. So if you go, this should be yes. But you can see that this is actually doing worse, or appears to be doing worse than our 1-bit predictor. Well, does life get better? Well, we trained this up a little bit at this point. So let's take a look at now. Let's execute the loop another time, given that we started off in this strong taken state. So now we're going to execute again, and we see that we actually predict taken, taken, taken. It actually was taken, taken, taken. And we just mispredicted the last one. And what's nice about this is now when we go to execute it again, we're going to start off, because we mispredicted the end state here, we're actually going to start off in the weak taken state. Sorry, so this probably should be weak taken. Is that what you were going to say? Yeah. So this is another bug in the slide here. I'll fix this in what I upload. This should actually say weak taken, because that's where we left off at the end of this one here. But the prediction accuracy is the same. We're still going to predict taken. So you can see that this does not get tricked, if you will. It does not get untrained by this one not taken case here at the end. But what's nice about this is you can train up, basically, and the hysteresis will not get fooled by one branch at the end of a loop sort of falling through. And that's positive. You can even think about this as actually being helpful, that the fall-through case might even signal you to do something. People could actually have you could even use that to sort of trigger something in your finite state machine. If you see lots and lots of takens, then one not taken on the exact same branch, that might mean something to you. And people in fact, have done things like that. So you start to get, even with 2 bits, you can think about having different state machines for the same thing. So here we have something which jumps directly to strong from weak. So instead here, when we had strong, weak not taken, and we have a taken here, we actually jump to strong. So we train effectively very fast. So still hysteresis, but sort of faster acting hysteresis. So this looks pretty similar to what you had before, but now this weak not taken state will jump straight to strong taken if you have one mispredict or something like that. But this is only one example. If you go look in actually the Shen Lepaste book, in the chapter that talks about this, they give like 3 other examples that look similar to this and are different heuristics to sort of try to get different chances or different behaviors that are common with programs. But none of these are going to be super, super great because they're only 2 bits. Is you actually start to think about having a table of these predictors. So you have local predictions. So it's not predicted globally, but instead we're predicting based on each different branch. And how we do this is we take bits out of the program counter and we index that into this big table. And then we can store, let's say, 2 bits in this table, and then we can train each of these things separately. Now, we're not going to want to have an entry in this table equivalent to the number of branches in the program, because it would be huge. But you want to somehow have some number of bits, k bits in fact, maybe just take the low or the medium order bits of the program counter and we use that as an index, similar to how we use indexes into caches. You could also think about having multi-way associative versions of these. So instead of having, this is a direct mapped version, but you can have a multi-way associative version of this. And if you look at, let's say, something which is a 4 kilo entry version of this, that's pretty big, actually. But a 4 kilo entry branch history table with 2 bits per entry, now we're starting to get somewhere. We can get sort of 80 to 90% prediction accuracy. So that's starting to get us there. But we had to build, I don't know, 8 kilobits worth of storage. And we had to somehow pipe it into our next PC logic, which is kind of a sensitive path on our processor. But this can be helpful in performance. So let's actually, before I move off this, I want to make one point. There are other ways to organize this table. So what we're really doing here is we're indexing into a table, and we're, let's say, running through some sort of finite state machine decoder here, which tells us taken or not taken, and then we're individually updating sub-entries of this table for a particular branch. You could think about having other things to index into this table. So either more complex hash functions, or maybe some other history information, or maybe previous states, or just some other bits up here. So this is just a base case. We're going to show some more complicated examples for spatial correlating predictors. But a lot of the ideas that we're going to talk about in spatial correlating predictors, you could apply that to these temporal correlating predictors. But I just wanted to make that point that these things do, what we're going to talk about, we're going to show much more sophisticated versions in our spatial correlation predictors. But you could apply a lot of those ideas back to these temporal ones. OK, so let's look at spatial correlation. We talked about temporal correlation. So in time, one branch and the direction that one branch goes has a high probability that it's going to influence, or it's going to predict, rather, whether that branch in the future is going to be taken or not taken. That's what a temporal prediction is. A spatial prediction, what it's trying to get at, this piece of code here, is that if you have, let's say, one branch do something, the future branch that's, let's say, right below it is going to somehow be correlated. So a good example case, and this is kind of the canonical example here, is if you check this value and it's less than 7, it's also less than 5. And you get code like this relatively often. So these branches are correlated. But they're not the same branch. They are different branches. This branch and this branch. So we're having some sort of spatial correlation here. And we wanted to try to exploit this somehow. And this was Yale Pat and one of his students came up with this not that long ago, surprisingly, in the 90s. And the idea here is that, I don't know, we're going to have an extra register we'll call a branch history register, which will store whether previous branches that we've executed were taken or not taken, and then use that to index into some tables, or use that somehow to predict what's going on. So this is actually going to be a shift register, where we're going to shift in what the branch did. So it's not based on just the address. OK, so here's our picture of our branch history register. The branch outcome, either whether taken or not taken, goes into here. And every time we take a branch, we're going to shift a new value in and let the old one sort of fall off the end. So what can we do with this? Well, we can use it to index a table. So if we have a pattern history table, what the pattern history table is will be indexed by previous branches. And then based on this pattern, we're going to look in this table, and that'll output either some bits that go into our state machine, or it might just output one bit which says taken or not taken. But in a general sense, it's going to output n bits, maybe 2 bits, which will feed into a state machine which updates itself, like what we had before. What's cool about this is, let's say you have a loop which always has 4 iterations. So we're going to have taken, 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 not taken. Well, what's going to happen is we're going to shift in these 4 taken, 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 not takens into this register. And then let's say we execute the loop. We execute that whole loop multiple times. We can train up this history table here, and it'll detect if we've seen the loop, let's say, have taken, taken, taken. What do we think the next thing is going to be? It's going to be not taken. And this predictor can detect that. And that can do that actually with only one bit here, just a 1-bit state machine. Because if it sees taken, 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 not, or excuse me, if it sees taken, 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 that's going to index into this table, and the output of here is going to be not taken. So it's going to be able to predict sort of short runs, loops which have short runs. And if this, as this gets longer, this branch history register gets longer, you could actually predict loops which have longer runs. So if this is 100 bits long, now you're never going to have 100 bits long because a pattern history table of 2 to the 100 is a very large number. But as this gets longer, let's say it's 10, that's very reasonable. You could predict a loop, let's say that loops 10 times, and it'll get the fall through case correct. It'll get the start case correct. And you will have 100% accuracy in that loop for your branch prediction. Wow, that's pretty cool. So this is where we're starting to actually get some traction here. And this is where branch prediction really started taking off. This is where we started getting sort of above 80%, we start to get to higher numbers. If we want to go even if we want to even have better prediction, we can start to think about having a branch history register which indexes into multiple tables and then chooses based on some bits in the program counter between these different pattern history tables. Now, why do we want to do this? Well, we want to know, based on our PC here, which one to choose. So this is trying to sort of get the mixing here of temporal and spatial correlation here. Because if a certain branch gets executed, you want to use that prediction for that particular branch. And here, you use some hash of some bits in the program counter. We'll choose between some number of these history tables. So this is mixing our spatial correlation with our temporal correlation together here. And this is called two-level branch prediction, because we have multiple levels here. We have the history register indexing in here and the program counter. And this can do quite well. And if we want to have a sort of generalized two-level branch predictor, and you want to make this even go better or even go faster, you can start to add multiple branch history registers and have them be per branch effectively. Now, you're never going to have it per branch. You're going to have it be somehow aliased into here. So you have multiple shift registers, and only when that branch is indexed is when you actually shift that shift register. So for relatively small numbers of m coming into this index into this branch history register table and k indexing between different pattern history tables, you actually can get very high accuracy. You can get like sort of 97% accuracy. Now we're still not 99. Now you might say, why do I care? 97 sounds pretty darn good. Not good enough, unfortunately. You actually need to go higher if you have a 22-stage pipe and you actually want to have decent performance, because 22-cycle mispredict or 20-cycle mispredict is really quite bad. Is pretty damaging when you go sort of work through the iron law math. So before I go on, this is kind of one of the more complex slides that we're going to see today. Does anyone have any questions about this, of what's happening in the mechanics? So let's talk about training this. So as you're executing, you're going to be shifting, when a branch occurs, you're going to be shifting the old outcome into this register, one of these registers here, based on the PC of that branch. And then you're also transitioning, based on the outcome, the prediction, or the state machine, which is embodied in the prediction. So this is actually a pretty complex machine here. And you don't probably want to be updating that, we'll say, right in the fetch stage or right in the decode stage. So typically how this works is you go to do this update later down the pipe, sort of at the end of the pipe somewhere. You go and you actually feed back the true outcome of all the branches, and that feeds back into the branch history register and the pattern history tables. And the downside to this is, by waiting to the end of the pipe, is, well, first we'll go for the upsides. The upside is you know that the branch was actually executed. You know the actual outcome. You know that it wasn't squashed by something else. If you were an out-of-order pipeline, you know it was actually committed, because you don't really want to train your predictor on bogus data. So you don't want to like sort of train your data on incorrectly predicted branches themselves. So if you, let's say, have a mispredicted branch, and in the shadow of the mispredicted branch, you have something else, and that would to go and try to corrupt your prediction state. That's not good. So usually you sort of wait to the end of the pipe. The downside of waiting to the end of the pipe is there's more feedback, and it takes longer to train up. It doesn't necessarily take longer time, but if you have a branch followed by a branch that wants to use that prediction, you can't actually use that, let's say, until it gets to the end of the pipe. So you're going to be using sort of old, stale data for a little bit of time, or as long as your pipe length is. Not the ends of the world, but something to be aware of. OK, so now we're going to start talking about getting into our higher 90s, well, higher than 97%. We're going to talk about sort of getting into our 99% accurate branch predictors. And this brings us to tournament predictors. It's a great name. Came up first in the alpha 21.264. And what they did is they actually had predictors to predict which predictor to use. So one of the interesting things, going back to this too low a branch predictor, is sometimes you want per branch information or per branch history, and sometimes you want global branch history. The per branch history, you're only basically training this up based on that previous branch. But in this example here, you're training it upon other branches. So sort of going back here, this is a different branch than that branch. So you might actually want global history. But there are times, for instance, in a loop, you actually want local history. So tournament predictors, actually, they end up with things where you're using a predictor, we'll call it a choice predictor, that predicts which predictor to use. I show two examples here, one which is choosing from a global predictor and a local predictor. That's kind of the canonical usage of this. Actually, in 21.264, they had something more complicated. I think they had, I think anecdotally I heard they have about 10 predictors in there, and they're trying to choose between 10 different predictors. And they train the choice predictor based on which predictor was correct. So you can use, basically, because you run loops and you run code a lot, you can train up the choice predictor to choose between other predictors based on the accuracy of the other predictors. So for a particular branch, one of the predictors is always wrong. The choice predictor can say, just don't use that one. Just exit out. So this does quite a bit well here. And you're starting to get into the 90, I don't actually know the full numbers here, but it's probably 98 to 99% accuracy for large individual predictors hooked up to this. The book Shenlapasti that you have talks about sort of some other things you might want to try to stick into here. But for right now, we'll leave it at this, that we have sort of global predictors, local predictors, things that use a branch history register for both of these, and then something which predicts between the two. But I'll just restate it one more time. You train up your predictor to determine which one to use, and it has lots of training data. But this is all heuristics. If you go look in the book, actually, there's they even joke, it's actually not a joke, it's something someone actually has proposed. They call it the perceptron predictor, and they basically have like a neural net hooked into the prediction strategy. So these things can get pretty sophisticated. I don't know if anyone has actually ever built the perceptron predictor for real, but at least has been proposed. OK, so that gets us out of the outcome part of today's lecture. Let's start talking about how to figure out where we're going. So this brings us back to this picture. And I took some stuff off this picture now. But now what we need to do is we need to know the targets, the relative targets. And as I said, we don't know the target for a branch, a jump, and a jump and link until we actually do PCE plus the offset calculation, sort of somewhere in the decode stage, until we at least get the instruction. For jump registers and jump and link registers, we don't know that until later. But this is baking out. This is not looking at the outcome. This is just looking at when do we know the value. But this is important because even though we have the prediction of where whether it's taken or not taken, and we can do that, let's say, with 99% accuracy, this is the harder one. We're trying to pick from 2 to the 32 possible numbers. Can we actually do a good job here? So something not on the slides, but something I wanted to talk about very briefly here is we can use a static algorithm similar to what we had seen with the other predictors to do this calculation through the compiler, if you will. So there's been a few architectures. One example actually is the Hitachi or now Renesas SH5 architecture, which is sort of a media processor, we'll say. And they actually have an instruction which loads the target of a future branch. So they decouple the branch into 2 instructions, the actual branch and a prepare to branch, which they have to execute earlier in their instruction sequence and says, I'm planning to do a branch, and it's to address something. It's actually called prepare target is the name of this instruction, or PTA, on their architecture. And because of this, they don't have this problem. All they need to do is actually do the branch. So they know the target of a branch in the fetch stage. They can actually just go, because they have this instruction which says, load up this special register with my target of the branch, and then we'll decouple the actual taking of the branch sometime in the future. So this is an interesting idea. I'm pretty sure there was actually one of the CDC machines, the controlled data court machines, did this a long time ago also, but I couldn't find the reference in time for today's lecture. But I know the Hitachi SH5 definitely has this instruction. So all I'm trying to get at here is that there are static software ways to go about doing this. In addition, now let's talk about some dynamic ways. OK, so the most common way to go do this is to implement something called a branch target buffer. And the branch target buffer you actually do in parallel with both the branch prediction outcome, or the branch outcome prediction, and the PC plus 4. So you put into it the current PC, and it's going to tell you somehow 1 out of 2 to the 32 possible targets. How does it do this? Well, what it does is it actually just keeps a table of where that branch has gone in the past. So the first time it executes, it just gets it wrong. But then the second time it executes, but given that first time it executes, it's actually going to load a table with a predicted target. So we're going to load the predicted target based on where this branch went in the past. We're going to index into this table based on our current program counter. And then we're going to check to see that we actually match. So we're going to take the whole PC. We're going to do a tag check, very similar to our cache. This is effectively a cache. And if we hit in this small cache here of targets, we have the new program counter if we predicted taken. If we predicted not taken, we just want to use PC plus 4. So in effect here, we can actually predict the target of the branch based on where this branch has gone in the past. Well, that made this a lot easier. I thought this was going to be really hard. Well, it's actually not that bad. One thing I should say is the size of this table kind of matters. If you alias too many places into here, you may end up just pulling out wrong data, or you might having a miss quite often. So you want to size this table appropriately. But you don't want to make it too big because you're carrying the entire program counter in here. And that can get big. So the data in here is quite large. So one way to solve this actually is typically people try to make these things set associative. So you'll actually have multiple PCs and predicted targets, because that actually has a little bit better performance if you can check multiple in parallel versus making it larger. I mean, you can just make it larger, but typically having a little bit of associativity helps with this. But you're really executing this in parallel with the PC+4 logic. One thing that also makes this a little bit better here is the branch target buffer does not hold every instruction. If it's not a branch or a jump, don't put it in this table. So you really only put in instructions that are branches into this table, which helps save a lot of space. OK, so we have a question here. How do we achieve this effect without decoding the instruction? So we have a branch target buffer. We don't want to decode the instruction. Can we just look in the branch target buffer? Is this good enough? Is all the information we need in that table? Because we're executing it in parallel with the PC+4. We haven't fetched the current instruction. Is that good enough? Or are we missing something? Yeah, this is kind of what I was trying to get at, is that because we check the program counter here and do a full bit width match, this is good enough. We don't actually need to look at anything else. One thing this comment was here to make a point about something called a line predictor. Sometimes you want to get rid of this valid bit and this PC from before, and then you just have coming out of here, instead of predicting the program counter, you don't really need to know the program counter. You just need to know where to go get it from your cache, sort of which entry in the cache to go fetch. And this is called line predictor. So a full branch target buffer will give you an actual PC. At some point, you actually do need to know the PC, but you can wait to actually know the PC until later down the pipe. Well, all we really need to know is which line in the cache we want to go fetch the next cycle. And we can do that actually by just sort of removing this check and just ad hoc, just having it fetch whatever it gets pointed to from here, which might be wrong, but we have to check that. So anyway, this is a trick question. We can achieve this with a full BTB, a full branch target buffer. If we don't have this check, it turns into something called line predictor. So we're predicting which line in the instruction memory or which line in the instruction cache to go fetch from. Oops. OK, so this brings us to jump register. So jump register. This one gets harder to train. We can try to train it the same way. We can try to use the BTB. So let's look at these different cases. So what is a jump register used for? It's used for switch statements. It's used for C++ virtual function pointers or dynamic function calls. So if you're doing a jump through a function pointer. And it's used for returns from subroutines. So how well does a BTB work in these different cases? So for switch statements, if you use the same switch statement and the same case gets lit up, this works pretty well. It's kind of like training any other predictor. If the probability that you're actually choosing something out of a switch statement is data dependent or highly data dependent, you're probably not going to predict it very well. And you're not going to do there's probably no great solution to this. There's some people who do sort of data prediction and try to look at the register values to try to do this a little bit better, but it gets very hard. Dynamic function calls. Well, this works very well. So if you ever ran a C++ function, in C++, they have function pointers all over the place. And this is to implement polymorphism. And this is how, when you, in C++, you sort of do a method access on some sort of function, you're actually indexing through a jump table inside the data structure. And it just so happens that this is basically always correct, unless you actually reassign that object to something else or if that object actually changes to a different type. So an example of that is that you have class animals, and you have dogs and cats, which subclass from animals. And you have a pointer to an animal, and you have a cat and a dog. And let's say you assign a cat to this function, or excuse me, this object pointer, which is an animal, and you call some method on it, like run. Well, that's going to train up very well, but all of a sudden, if you change that cat to a dog, the virtual function pointer, because what you actually execute on a cat, when you run the function run on a cat versus running the function run on a dog, they do different things. Cats like to sleep a lot, and dogs like to run around a lot and bark. So the code in the middle of the run function of the cat and the dog are different. So we no longer jump to the same location. So our BTB will be wrong, but it'll train up pretty fast because you're probably not changing the object pointer very often. So that's decent. Okay, so subroutine return calls. Jump registers are used there a lot. So you call into a function, you do it with a jump and link. To come back out, you come out with a jump register. Well, BTBs are okay if the place that you are returning, or excuse me, the place that you call from, you're calling from that location a lot. But if you're calling a function from different locations quite often, effectively what's going to happen here is one function is going to be called from lots of different locations, and you're not going to be able to predict the return location very accurately. So if one leaf function gets called from lots of different locations, that's not particularly very good for a BTB. One interesting thing about this subroutine return case is that the jump register at the end of a leaf function, the program counter for that jump register is not correlated to the function which called into it. So effectively, when you go to index the BTB, you're using the address of the jump register, and it might point to some other function that had called it in the past. And that may have no correlation to something that calls it in the future. And that's why this is really hard to do. So can we do better for jump registers? Yes. So there's an idea of a subroutine return call stack, or a subroutine return stack. And the idea here is you have a small predictor, specifically just for jump register subroutine returns. And what you do is you track function calls, and you push the return address onto a stack. And then when you do a return, you use that prediction. So let's say we have these three functions here. We have function A, which calls function B which calls function C calls function D, as denoted here. We have some stack that we're going to push entries onto when we do jump and links. So we know that there's something to load this predictor with. So when the function call gets executed or the jump and link gets executed, we're going to push the address of what is after, effectively, the function call site. So I'll denote it here by the address of FB. So that's for when FA calls into FB. In reality, it's probably like the instruction right after that is where we're going to return to. Likewise, when FB then calls FC, we're going to push the return location after FC. And when FC calls FD, we're going to push that. And these come off in the inverse order because it's a stack. So when we try to pull off this, we're actually going to pop return addresses boop, 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 like that. So we're going to pop off the FD, FC, and FB, or the address after FD, FC, and FB, and we're actually going to predict the return for this function, or the leaf function, correctly every single time. Where it gets a little hard is if we have our call depth be deeper, or recursion depth, if you will, be deeper than how many entries we have in a return stack predictor, then we're going to start predicting wrong. But otherwise, we can do pretty well with this. In fact, some architectures make this a little bit easier on the hardware, and they'll actually have a special instruction for the jump and link, or the call instruction. So for instance, in x86, they have the call instruction, and that tells the code, basically, or tells the hardware to load this predictor. Because otherwise, a jump and link, there's too many other uses for a jump and link. It's not always a function call. It's almost always a function call, but it's not always a function call. But for a call instruction on x86, that's basically always a call. So you know to load this. And then on x86, there's a return instruction, which is always a return from a function. That's the semantics of it are tied very well. OK, so there's actually one other topic I wanted to talk about today that's not in the notes. This correlates to line prediction. We talked about line prediction. The one other thing I wanted to talk about is way prediction. We haven't talked about this yet, but if you have a, let's say, two-way instruction cache, we talked about where to go look, of which line to go look at in the instruction cache. But one of the things that's just as hard is if you have two-way instruction cache and you're trying to fetch the next instruction, which way do you go and shove into the decode stage of your pipe? Way 0 or way 1? It's tough. You don't know. So this is one of the reasons a lot of times people will build direct map instruction caches, because it's very hard to know which way is the correct way. But our predictors, just like our branch predictors, helps with this. We can build a way predictor. So we can have the same prediction architecture we've talked about today in today's lecture, dynamic, multi-level predictors, sometimes even baked into the branch predictor. And then that can be used to predict whether we choose from, let's say, way 0 or way 1, or if we have a four-way set associative cache, way 0, 1, 2, or 3. Anyway, that's what I wanted to talk about today, and let's wrap up here for today. OK, welcome to today's ELE 475. Whoops. So today we are going to be moving to a little bit different topic. We're going back to one of the topics we talked about at the beginning of class in lecture 3. We're going to be talking about caches. And we're actually spending 2 lectures on caches because they're really important to performance. In the, we'll say, 90s, 80s, and 90s, a lot of computer architecture papers and a lot of effort were spent trying to use more and more transistors, which Moore's law was giving the computer architect, and applying them to build either bigger caches, fancier caches, more set associative caches, harder, we'll say, ways to think about caches, all for higher performance. And we'll be continuing to videotape today's lectures and put them online for everybody. And so let's start off and look at what we're doing today. So we're going to start off with a little bit of review from lecture 3. We're going to talk about the 3 C's of caches. So capacity, conflict, and compulsory misses. We'll be talking about the basic cache optimizations we had talked about in lecture 3, which are mostly kind of make your cache bigger, make your cache more highly associative, somehow to reduce these 3 C's. And then we're going to start talking about much more advanced cache organizations and optimizations we can make. So let's briefly talk about it. It's sort of a hodgepodge. And this is kind of just the nature of the beast. There's lots of little things that sort of add up to make either the cache more effective or integrate the cache into your pipeline more efficient. And this is only the beginning. We will have about 5 or 6 more topics next time. Let's start off by looking at what we're going to be talking about today. So we're going to look at how to pipeline a cache right. So one of the things we haven't really thought about when we were working on our labs is we do a write to the cache, and it just sort of magically gets stored there. But if you actually are trying to build a real cache, you have to look at the tag data, and then you have to write the data. Because you don't want to be writing something into the cache if it's, let's say, a different piece of data is in that same location. So you need to check the tag first. And we'll talk about some ways to optimize that. We'll talk about a write buffer. A write buffer is an extra data structure we can put after our first level of cache, which can hold victims. So a victim is a line or a cache block that is being evicted from the cache. And if you are going to, let's say, replace something in the cache, you need some place to put the old data, or the data that was, let's say, dirty in the cache from before. And the slow way to do this, or things we've sort of looked at up to this point, is you take that line and you wait for it to go get written into either memory or the next level of cache. But if you want to go faster, you can think about trying to store it some way, place in some side structure, and we'll say write to the next level cache or write to the main memory in the background. We'll talk about multi-level caches. So multi-level caches, meaning you have a level 1, a level 2, a level 3, maybe a level 4 cache, then main memory, and why this can improve performance. We'll talk about victim caches. Victim caches is this idea that can basically increase the associativity of a cache by putting a low associative cache, or maybe a direct mapped cache, next to a cache with very high associativity. So maybe like a fully associative cache, and then you use them together to basically implement a pseudo higher associativity cache. We're going to talk today about prefetching, both hardware and software. So prefetching is the act of either a piece of hardware or software trying to get data that you need early into your cache. We'll talk about how to increase the bandwidth to your cache. So up to this point, we've looked at doing 1 memory operation per cycle. Well, we built machines that can execute 2 operations per cycle. And on your exam, you had a machine which could execute 3 operations per cycle. Wouldn't it be great to be able to do 3 memory operations per cycle versus just 3 ALU operations? So how do we go about doing that? Well, we can put multiple ports on this structure, but that's not particularly great for performance from a clock perspective, because it makes the structure very large. So you can start to think about banking, which we'll talk about today, as a mechanism to increase the bandwidth. And then we're going to talk about a bunch of different compiler optimizations or software optimizations that the compiler can do to restructure code to have better cache performance. So this is just what we're talking about today. Next lecture, we're going to continue on this. And the main topic of next lecture, as far as the advanced cache optimizations are concerned, is we're going to be talking about how to build caches which can deal with out-of-order memory, or can deal with the ability to have loads and stores which hit in the cache, or loads and stores which miss in the cache, and then you can continue on past that point. So in our sequential machine up to this point, even in our out-of-order machines we were talking about, when you took a cache miss, you basically had to stop the machine, because you had to wait for the data to come back, because you didn't know if the next instruction was going to need that data, or maybe the next load would need that data, or something like that. So if you want to try to go out of order, you can start thinking about that, and that's what the bulk of next lecture will be about, is how do you go out of order in your memory system, or what this is largely sometimes called is a non-blocking cache. And I should point out that a non-blocking cache is actually not just for out-of-order processors. This is sometimes good for in-order processors. So if you have an in-order processor, the instruction sequence is going in order, but you don't want to, let's say, wait when you take a cache miss, you could actually have the memory system be out of order with the pipeline be in order. And that's actually a pretty common thing for people to do. OK, so here let's go look at our review. We have processor. And in our basic machine, we go out to main memory when we want to get data. Main memory is big. It holds everything. But it can be slow. So we put a cache in front of that, which keeps a subset of all the data in the main memory. And it has a faster time. And it can take something, for instance, like this example here, where you go access memory, and you have to wait for the memory to come back. And it can shrink this time. Now, if we look at the sort of average memory access, it's your hit time plus your miss time times your, your miss rate times your miss penalty. This is just review. OK, so going back to the 3 Cs, here we have a 4-block cache. So it's a 2-way set associative cache. And let's look at what are the major types of misses you can have, or the only types of misses you can have. You can have a compulsory miss. So this just means that's the first time any portion of your program has gone to go access the data. There's no real way around this. Maybe you can prefetch, but you're not really going to magically be able to get the data in there early unless you have some sort of aggressive prefetching mechanism. Capacity. So in this cache here, we have 4 blocks. If you're looping over, let's say, 5 cache blocks worth of data, you're basically not going to ever be able to fit all the data in this cache. Or a more common case is, let's say you have a cache that's an 8 kilobyte cache, that's your L1 cache, and you're trying to add 2 arrays where each array is 16 kilobytes. Well, that needs 32 kilobytes of data, and maybe even another 8 kilobytes of data if you're not doing it in place for the result matrix. And it's just not going to fit in your cache, so you have capacity problems. And things are just basically going to get continually kicked out of your cache. Conflict means that you don't actually have, you have enough space in your cache, but too many different loads or stores you're trying to access alias to the same location in your cache. So let's say you're trying to loop over 3 different cache blocks, or trying to access 3 different cache blocks, which all alias to one set in the cache. And effectively, you can only fit 2 things, and you're trying to fit 3 things in 2 spots. And this is kind of the pigeonhole principle here. Comes up and says, no, you just can't fit 3 things in 2 boxes. So we get conflicts. OK, so still review here. Let's take a look at one way to reduce our hit time. Hit time is just the fast case. That's actually you find the data in your cache. This is the good case. But for hit time, one way to make it lower, this is actually in nanoseconds, is just to have a smaller cache or a simpler cache. So small, simple caches are, in this drawing here, we have time on the vertical axis. On the x-axis, we have different cache sizes. And the 16 kilobyte cache is faster than, let's say, the 256 kilobyte cache. So if you make a smaller cache, you can go faster. And we had seen an example of this actually in the Pentium 4 when we were talking about super pipelining. In the Pentium 4, they had a very small cache. And the real reason they did that is because they had such a high clock frequency that they couldn't put anything bigger and still fit it in one clock cycle. In a perfect world, if your clock cycle was slower, you could try to fit some bigger cache in there. So you can try to reduce the miss rate. There's a couple different techniques on how to reduce the miss rate, and this is there's the advanced techniques, which we'll be talking about later. But one of the basic ones is to change the block size. As you make the block size larger, you're going to be pulling in more data. So you'll get spatial locality, and hopefully you'll be pulling in data that you actually need. So the positives of this is you're really going to have less tag overhead if you have a larger block size or cache line size. Because for the same amount of data, let's say you had a 64-byte line versus a 128-byte line, you're going to have half as much tag sort of cost or area dedicated to the tags. And usually as you go to larger block sizes, this is good for the farther out layers of your cache because you can basically burst more data in. So if you look at something like a DDR2 memory or DDR3 memory, so this is the traditional DRAM technologies that we're using today, they want to actually, their block size, their line size is very, very long, sort of thousands of bits. And if you have a longer block size, you can use all those bits and pull them all into your cache in one big chunk, and you can use wider buses. Downside, you can waste bandwidth. If you have a very large block and you don't actually use all the data in the block, let's say you use 1 byte out of your 256 byte cache, you're just pulling in all this data and you're wasting a lot of off-chip bandwidth for no real good reason. And if you have fewer blocks, you're going to have less locations to put data for the fixed size cache. So you might actually increase your conflict rate. So this chart here, what we're trying to show, this is from your book. We're plotting the block size versus the miss rate. And you want the lowest miss rate possible. So if we start here with a 16-byte block or 16-byte cache size, or cache line, as you increase it, the miss rate actually goes down. But at some point, you end up wasting a lot of bandwidth because you don't have enough, the program will say does not have enough spatial locality. So you actually just end up pulling in more data than you need. You also could potentially have more conflicts. So it starts to go up. So there's sort of a minimum here. Traditionally, people have thought about this as actually increasing block size usually increases your performance for most applications. But that's up to a limit. And the reason why people traditionally thought this is cache sizes used to be sort of smaller. Or excuse me, cache block sizes or line sizes used to be smaller, and they sort of started getting bigger. And then people really weren't looking way out here. But now that we look at way out here, it does get worse for some applications as you get farther out. OK, so another way, just the basic ways we can reduce miss rate is we just have a bigger cache. This one's great. Bigger cache, lower miss rate. You got to pay area for this. And potentially, it takes longer to access this larger cache, as we had seen in the first graph that we showed today. I'm not going to really talk about this, but empirical rule of thumb, if cache size is doubled, your miss rate usually goes down by the square root of 2. It's just empirical, people have found, but good rule of thumb to know. Same graph, tells a different story. If you go to a higher associativity, your miss rate goes down. So if we have a direct mapped cache, and we go to a two-way set associative cache, the miss rate goes down. And the traditional sort of rule of thumb about this is if you have a direct mapped cache of size n, it has roughly the same miss rate as a two-way set associative cache that is half the size. And you might say, wow, that's pretty amazing. So can I just continually apply that over and over again? It doesn't quite work. It also gets very hard to actually build very highly associative caches because your tag check becomes pretty hard because you have to check against all different places in the cache it could be in parallel. And that becomes hard. Now we begin the meat of today's lecture. And we're going to talk about all these different advanced cache optimizations, starting with pipelining the cache. OK, so here is our sketch of what happens in a cache. In a cache, we have a tag, and we have the data blocks here. And we want to go do write into the cache. So forget about the read for a second. But instead, let's focus on the write. So in the write, you're going to do a tag check. So you're going to index into here with the index into your tag array. It's going to spit out the tag. You want to check the valid bit also. and you're going to do a comparison here. If it matches, that means that the data is already in the cache, and you're doing a write. So you can just write the data into the cache. So that sounds good. Some challenges here is it really is sequential. You need to absolutely do this first before you do the write. Because if you have a different address stored in this location here, and you just blindly do the write, you're going to overwrite the wrong data. And then you're just going to be very unhappy because you overwrote some data which wasn't apportioned to this, this particular write, or was at the wrong address. So that's definitely a bummer. So do we think we would want to try to do this in one cycle? Anyone want to wager a guess here? Do people build machines where they do this in one cycle? Well, sure. Original machines did do this in one cycle. It's possible to build. You have a nice combinational path that sort of comes through out of the index, through here, through all this logic, and then through the write enable into here. It's buildable. Not great for your clock performance. So the first optimization, so how do we reduce the hit time for a write? And there's a couple different strategies to this. So we can think of this as trying to do this over two different cycles. The first cycle checks the tag, we'll say, and the second cycle does something to the data. That's kind of our problem statement. What are our solutions? One solution is kind of innovative, is you can build a multi-ported cache, or a cache which can simultaneously do a read and a write to the same address. And you do that. So you have a cache, you're doing a write. You blindly do the write, not checking the tag. But at the same time, you read the old data that was there, and you save it off. And if you took a tag miss for the write, you go back and actually fix it up by filling that back in. That is an option. People have built such things. So you just restore the old value on a tag miss. Works perfectly fine. You need a side buffer. This kind of looks like a victim cache, which we'll talk about later in today's lecture. But you can do a write and a read at the same time. And it's kind of like you're putting the new data in speculatively, pulling out the old data, the victim. And if the write hits in the tag check, then you just let it go and everything's great. If not, you have to basically pull that back out and undo it. It's doable. Not a lot of people do this, but people have built machines like that. Another solution is trying to build a fully associative cache. Now, what do I mean by a fully associative cache? Well, I mean a cache which has lines such that you can store to any location in the cache. And in those structures, typically the tag check and the access are kind of done in parallel. So because you don't know where to find the data, there's no index operation. The index operation is the tag check or the CAM operation or the content addressable memory operation. You're basically doing it in parallel. So, or you're basically doing the tag check to do the read anyway. And it doesn't really hurt you to sort of do the tag check first and then do the write. So it just doesn't really hurt you. It's not necessarily a great design if you have a very large cache. But for a small cache, you can definitely have a content addressable memory for the tags, and then just have it so you can write anywhere if you have a fully associative cache. That is one way to solve this write problem. And then we're going to look at But this is what we're going to focus on in today's lecture, is pipelining the write. So to pipeline the write, instead of actually doing the write in the cycle, in the M stage of your pipeline, we're going to do the tag check in the M stage, and then hold the store data for some time in the future. Now you're going to say, did we actually do the store then? Well, yes, we're going to call that committed state. So this is what we're going to focus on today, is how to do a pipelined memory access to reduce our write hit time. So here we have our 5-stage pipeline. And what we're going to do is when we get to the M stage for a write, we're going to check the tag, and we're not going to fire up the data array at all. Now you might say, where do you put the data? Well, we put a nice little buffer here, which is a basically to-be-stored buffer. It stores the data that's going to be stored in the future, or a delayed cache write buffer is what we'll call this. So in parallel, you check the tag, and you store the data here. And then, sometime in the future, you want to move this into the cache. But you need a convenient time to do that. So one option is you wait for a dead cycle on the cache. OK, that sounds good. How do you know you're going to get a dead cycle? I can't guarantee that. I can write a piece of code which does store after 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 store in a really tight loop. So you'll never have a dead cycle. A cool little trick here is a subsequent store only has to use the tag array. So if you have a store after a store, the first store will check the tag and not use the data. We'll store the data here. And then when the second store comes down the pipe, it'll check the tag, but the data array is open. So you can do the store at that time. So it's a cool little trick there. If you have a store after a store after a store, you can basically decouple the tag from the data for stores and use the port on the cache to do the data array of the cache to do the store later. And we can look at this with a little bit more detailed drawing here. And this is just kind of to reiterate what was going on. You do the store, it checks the tags, and it's going to store the address and the data. And at some point in the future, when there's an idle cycle or another store going on, it'll actually transition this data into the data array. That sounds good. OK, so pop quiz question here. What happens when you do a load and there's data in the delayed write data buffer? You have to bypass it. Yes, you need to go check it. So you need to have something which is going to check, and that's actually drawn here, the delayed write address against a future load. And if you get a hit there, you need to have this data come around and come out. So we basically need to go check this buffer. One thing I did want to point is this is kind of the naive way to do this. More advanced processors will actually typically have a multi-entry version of these delayed write data buffers because caches are sort of usually pipelined inside the cache too. It might take multiple cycles to actually access the data array. So you might not do this till the end of the pipe. So some of the processors that I've worked on, these are sort of on these delayed write buffers are sort of in the order of maybe 2 to 4 entries big. So you can abstract this and make this into a bigger data structure. And when you do loads, you obviously have to do a content addressable match against all of those entries and see if the data is in the delayed write data buffer. OK, so let's go see how well this does. Pipelining our cache. We're going to use this throughout today's lecture. Ways that it makes life better. You can either reduce the miss rate, so do something good for miss rate. You can either do something good for reducing the miss penalty. You can reduce the hit time. And this would be like, for instance, having a smaller cache reduces the hit time. Or you can increase the bandwidth to your cache. But all these things are going to factor into performance. And not all of the techniques, optimizations we're going to talk about today touch all of these. In fact, most of them only touch sort of one at a time or two at a time. OK, so pipeline caches, what do they do for us? Are they going to reduce the miss rate? I see people shaking their heads no. Yeah, we didn't make anything bigger or smaller here. It's probably not going to touch the miss rate. Is it going to affect our miss penalty? So this is when we miss in the cache, how long it takes us to go to, let's say, the main memory or the next level of cache. No, it's not actually going anywhere different. Effectively, this is implementing the exact same thing. Hit time. Does this affect the hit time? Well, it's going to affect the hit time. It's kind of hard to see whether this does it in the positive or negative direction here. If you compare to having the, let's say, tag access and data access all in the same cycle, pipelining is actually going to make the hit time a little bit better because you're doing less in a cycle. So that would have us put a plus here. But if you compare to, let's say, not having a cache or just having a big RAM there, it actually makes the hit time worse because we need to mux in multiple extra stuff here. We need to basically do this extra check. We need to do the associative check against our delayed write buffer data. So that actually hurts us a little bit there. So, OK, that might be a plus or a minus. The bandwidth, though, is actually going to be better through this cache. Because before, we had to just sort of wait for this cache for, let's say, the whole time to go through the tag check and the data check, and the data write. But now we can actually have two stores sort of happening at the same time, or the tag for one store and the data for a different store. So this is really going to make the bandwidth better for this. So that's where we are with pipeline caches. So that's our first optimization technique. There's no questions. We can move on to our second optimization technique. Your book lists 10 optimization techniques. We're only going to cover, I think, 7 of them between today and next lecture, because I think some of them are not actually that important. But we're also going to cover some other ones which I think are important. OK, so next thing we're going to look at, the next optimization we're going to look at is how to deal with how to deal with read misses in the cache that have some data there that needs to get kicked out of the cache. So here we have our CPU, L1 data cache. Our next level of cache here, we'll say a level L2 cache or maybe main memory. There's something in this cache at a particular line, and it's dirty in the cache. So the dirty bit is set. It has state we cannot throw out. We do a read, and it aliases that same location. And we need to evict that line or create a victim. In a naive implementation, we'd actually have to sit there and wait for all that data to go out to main memory while we go get sort of the next, while we go to do the read and get the data and fill it in. Okay, that's not very good. We sort of have to wait for this evicted dirty line. We'll talk about that in a second. So the processor could be stalled waiting on writes. One thing you can do is actually have the read misses go beyond the writes, sort of past the writes and past the writes going out to the unified L2. But one of the problems here is you don't have that many ports onto this unified L2. You really only have one port out here, we'll say. So you could either have the load sort of pass it, but then you have to do this little dance that when the read data comes back or the load data comes back, you need to have a place to put it. So either at that point, you might need to wait for it to go out to main memory or go out to the next level of cache. So you can't really get around this. So you can say, oh, well, I'll try to get my load out early and just sort of worry about it later. Yeah, but that doesn't work if that load hits in your next level of cache. You need to access the next level of cache, and you're waiting for this data to go out because you need some place to put it. So the solution to this is we put a little buffer between our L1 and our L2, or L1 and our main memory, and this will hold writes or victims that go out from the L1 to the L2. And now we have some place to put the data. So if we wanted to do this fast, we'd actually do the load. We'd miss in our L1 cache. We'd send that request out to here. And then instantaneously, we would start evicting the line into this buffer. And the reason we can't evict it here is because the load's actually using that data right now, or it's using the L2 cache, we'll say. But we have some place to put the victim data. And when the load comes back, we can put it into the L1 data array. So this brings up a whole bunch of problems. Biggest one being, at some point, you actually need to transition from the write buffer into the L2 cache. You can do that if you have extra time. So you can just have some circuit here which checks. But then comes the question of if you need to do this a second time, what happens? Your second, let's say, load that has to create a victim, and this buffer's full. What do? Well, you can just stall and wait. That's a pretty good option. So this kind of what you're saying here is the probability that you have two victims generated in a very short period of time is low. And this is actually a scheme that people do use. They don't do anything special, and the first victim that gets generated goes into the write buffer. The second victim gets generated, just stalls the pipe. That's OK. You can have higher performance if you can have the subsequent read basically go beyond the write buffer here and start actually doing something in the memory system. And if you want to do this, you need to, just like what we did in the previous example, you're going to have to check this write buffer to see if the data is there. And that introduces complexity, because now your data can be here, or even farther out. So it's just more places to check. OK, so that's like the first half of write buffers. The second half of a write buffer, why we want to put a write buffer, is if we have a write-through cache. So we've been talking about write-back caches, which introduce victims. But if you recall, a write-through cache, every single store that happens gets stored into the data cache, the low-level L1 data cache, and it also gets written into the next level of cache, we'll say, because it's writing through. So let's say you have a write-through from the L1 to the L2. And one of the challenges with this is you might not have enough bandwidth into the L2 cache to basically take in every single store that occurs. So the solution to this is you actually put a write buffer here, which will sort of buffer up some of this extra store bandwidth. And we'll introduce a notion of a coalescing write buffer. So this is a extra addition to a write buffer here that it'll actually merge multiple stores to the same line. So let's say you have a store to address 5 and a store to address 6 with a write-through cache. You don't want to actually have to write sort of 2 full cache lines out to the L2. Instead, what a lot of people do is they have coalescing write buffers. So there's one write buffer here. It might have multiple entries that holds a whole cache line. And that first store will push the entire cache line out into here. The second store will try to push the whole cache line out, but it'll notice it's for the same address that it already has in it. So it'll actually merge the 2 cache lines into one location. And what this does is it actually decreases the bandwidth that you need at the L2. Because it's very common in codes to write sequential addresses. So it's very common to, let's say, you're adding 2 arrays, the destination array, you'll actually just be writing address after address after address. And you don't want to actually have to go fire up the L2 for every single store that you do in that array operation if you have a write-through cache. So you can put a coalescing write buffer here to save bandwidth into your L2. So this is our sort of second technique, is having this write buffer. OK, so what does the write buffer do? Does it decrease our miss rate? Caches are the same size. Associativity is the same. Probably not going to change our miss rate. Miss penalty. OK, raise your hand here. Who thinks this affects the miss penalty? Some people are raising their hands. I think we should probably all be raising our hands, because that was really what we were trying to do with this whole write buffer, is to reduce the miss penalty. And the reason this reduces the miss penalty is when that read misses in here, it doesn't need to wait for the write to occur of the background data or the victim data. Instead, it can just have that happen in the background. This also doesn't affect our hit time. It may actually help our bandwidth. The reason it doesn't affect our hit time is our L1 cache just will still work the same way it worked before. You still can do loads and stores against that, and if you hit, it's fine. So it only affects miss sorts of things. Bandwidth, like I said, if you have a write-through cache, this might actually effectively give you more bandwidth if you have a coalescing write buffer. So the next memory optimization, or the cache optimization we are going to go look at, is adding multi-level caches. And you probably see this in sort of any modern day processor you have. There's level 1 caches, level 2 caches, maybe level 3 caches, maybe even level 4 caches. And we're going to talk about why this might be a good idea and what the effect of this is on the different parameters we've been looking at throughout this lecture. So what's the basic idea here? Well, the basic idea is you have a CPU, and instead of just having 1 cache, we say, let's add 2 caches. And why do we want to do this? Well, it comes from the insight that it is both difficult to have a very large cache and a very fast cache. So how do you solve this problem? Well, you could think about trying to fill this entire room with RAM. That would be a very large, let's say, cache for something. And if you think about this, they actually do have sort of notional caches like this. If you go look at something like a internet scale data center, there will be basically a room full of mostly just RAM. And they'll use this to cache things like lookups. And there's a sort of, you might see something like memcached, which is something which caches queries to databases, or is a key value store that typically caches queries to databases, which people store in large RAM. the problem with having a very large cache is, by definition, if it's large, and you don't want to violate the laws of physics, to get to the farthest extent of the cache, you might have to go very, very, very far. And if you run a wire very, very, very far, it's by definition going to be slow, because you can't violate the sort of physics law here that you need to travel at maybe the fastest you can travel is maybe at the speed of light. So the farther you go, the distance becomes a factor. So our problem here is that you can't have something that's both large and fast memory. So what can we do? Well, we can actually add multiple levels of cache so that if you have a certain size working set, you can try to store that, let's say, in a small local cache, which is both small and fast. And then you can have different levels of cache here. Say a level 2 cache, which is a little bit large, so has a larger capacity, but is a little bit slower and a little bit farther away from your CPU. And this can mitigate the cost of having to go all the way out to DRAM. OK, so I wanted to introduce some nomenclature here, because this is important that you're going to see sort of over and over again throughout caches. And it's important that we introduce it now when we start talking about multi-level caches, because just because you see, let's say, a low cache miss rate does not mean a cache is performing well, especially when you get into the multi-level cache domain. And why is that? Well, let's say we have this level 2 cache here, and I say it has a very low miss rate. Well, that sounds good, but this level 1 cache is filtering accesses to it. So just because the level 2 cache has a low miss rate doesn't necessarily mean that the level 2 cache is performing well. Or vice versa. Let's say the level 2 has a very high miss rate. You might say, oh, that level 2 cache is doing a really bad job. Well, to some extent, all of the easy misses are being filtered by the level 1 cache. So all of a sudden, the miss rate out of your level 2 cache might look very different. So we need to come up with some way to sort of discuss these different misses with correct nomenclature. So I'm going to introduce three notions here. Something we're going to call local cache miss rate. And this is just going to be the number of misses that you have in a cache versus the number of accesses in a cache. And this is local per cache. So if you were to look at, let's say, a level 2 cache here, and you have a certain amount of accesses coming into level 2 cache, and a certain amount of misses coming out, it's all local to the level 2 cache. So this is going to be the actual miss rate of a particular cache. Now, that's not the same thing as something like a global miss rate. So global cache miss rate here will take the number of misses in the cache relative to the number of CPU memory accesses. And this might be a better metric in a multi-level cache hierarchy, because you might want to say, in our level 2 cache here, what is our miss rate out of the last level cache or out of our L2 cache relative to the number of actual accesses that the CPU is doing? And this will help you encapsulate sort of the level 1 and level 2 together. So that might be a better metric. And you'll see your book sometimes use these two different metrics in different ways. And then finally, something that's useful to think about is the number of misses per instruction. Now, why do we bring this up? That sounds pretty similar here to like a global miss rate or something like that. Well, the difference here is the denominator changes. Instead of having either accesses per cache or CPU memory accesses, instead we have per number of instructions. And why is this useful? Well, if you have misses per instruction, it takes out of the equation how many loads and stores you have as a percentage of instructions in your program. So if you have, let's say, a program which has very few loads and stores, but it has a relatively high miss rate per access, you might say, oh, this is bad for performance, or if you just looked at the cache miss rate, like the local cache miss rate. But in reality, it may not be so bad for performance, because if you never do a load or never do a store in that particular program, maybe it doesn't actually affect your performance very much. So this last metric here, this misses per instruction, encapsulates that. So it encapsulates both the percentage of instructions that are loads and stores mixed together with the number of cache misses in the program here. So it can give us, and this can either be local or global, but usually this is considered to be sort of global-ish. But it could be either, you could also use this metric for a particular cache. So we can say this cache misses once every 1,000 instructions. That would be pretty good. And depending on the number of loads or stores per set of instructions, so let's say you have a load or a store once every, I don't know, 5 instructions. So maybe 20% of, or a little bit less than 20% of the instructions are loads or stores, which might be typical in a typical processor or a typical program for a typical processor. So then you could say, you can make some notion here about how the cache is performing on aggregate. And you'll see actually a lot of the numbers in the Patterson-Hennessy book actually use misses per 1,000 instructions, which could be a more useful metric or is typically a more useful metric. OK, so let's take a look at how adding a level 2 cache influences the design of level 1 cache. And this is pretty common that when you add multiple levels to your cache hierarchy, it actually influences the lower levels of your cache hierarchy. So how does adding a level 2 cache potentially influence the level 1 design? Well, one interesting thing you can do here is just by having a level 2 cache, this might allow you to think about having a smaller level 1 cache. So if you have a relatively close level 2 cache, for the same performance, you could actually have a much smaller level 1 cache and have a level 2 cache take care of these things. And this can actually even help performance maybe more because you can potentially move the level 1 cache closer because it's now smaller, or increase the speed of the level 1 cache. But the miss rate from the level 1 cache is going to go up because you made it smaller. So what about energy? Well, this can actually be a really good energy win. So how does this energy win? Well, you were able to take your level 1 cache and make it smaller because you now have a level 2 cache. So the common case thing is that now you're accessing your level 1 cache, and this level 1 cache is smaller, so you can be accessing it relatively frequently, and each access you do to it is itself going to be less energy. So something to think about here is that our level 2 design is going to influence our lower level designs, and it's not in a vacuum. So it's not like we can just slap on a level 2 cache or a level 3 cache and say the lower levels of the cache hierarchy don't change. Another thing that, another way that the level 2 design or the presence of a level 2 can really influence the level 1 is you might be able to have a much simpler level 1 cache design because you have a level 2 cache. So what does this look like? Well, let's say in your old design, the level 1 cache was a write-back cache. So it stored dirty data, and when a cache conflict occurred, it had to find an eviction and evict something out of the level 1 cache and wait for that eviction to occur, or at least find the bandwidth for that eviction to occur. In something like a level 2 cache that backs a level 1 cache, you can actually move to a write-through design. Now, how is this possible? Like, why would you be able to do a write-through design when you weren't able to do a write-through design before? Well, if you only had one level of cache and you had to do write-through, every write you did would have to have gone out to main memory. And largely, that's not, you don't have enough bandwidth to go do that out to your main memory store or out to your DRAM. So because you now have a level 2 cache, you can use that as a buffer, if you will, to absorb write-through traffic. And that traffic doesn't have to go off chip. So your write-back cache, you can have a write-back L2, which tracks all the dirty data and makes sure that it actually invalidates out to, it has to do evictions on invalidations, for instance, for dirty data. But the level 1 cache can just write through all data. Now, this requires you to have enough bandwidth between your level 1 and your level 2, but that's typically a lot easier to come by because your level 1 cache and your level 2 cache are usually, to some extent, located near each other and both on chip in modern-day processors. Let's see, other reasons that this is good. Well, it really simplifies your level 1 design. If you have a write-through cache in your level 1 design, you don't have to worry about having dirty victim evictions. The control becomes easier. And a lot of times this becomes easier to integrate into your pipeline, which is a good thing. Something we haven't talked about yet, but we'll be talking about at the end of this course, is how something like this multi-level cache can actually simplify your cache coherence issues. So something we haven't talked about yet is how cache coherence deals with, caches can deal with coherence. And by having a smaller L1, which is right through backed by an L2, you can really think about simplifying the cache coherence issues. So what is cache coherence? Well, we've talked about compulsory misses, capacity misses, and conflict misses. But when we get to the end of this class, not this class, but at the end of this course, we'll be talking about cache coherence, which is keeping multiple processors with caches and keeping the caches coherent between those different caches so that the data does not become stale between those different caches. Well, one of the questions that comes up here is, by having write-through and simplifying the L1, does this become easier from that perspective? And it does. Now why is that? Well, something we're going to learn about is these coherence misses. And what coherence misses are going to be is basically a different cache is going to reach across a bus or maybe a network on chip connection and tell a different cache to invalidate something out of its cache. And if you only have one cache per processor, if you only have a level 1 cache, we'll say, or something like just one cache level, when you go to reach across the bus and this cache is tightly integrated into your pipeline, you now have to deal with these sort of external requests coming in to do invalidations or to do something like snoops, which we'll also be talking about in a few classes when we get to the end of this course. But if you have a level 1 backed by level 2, you can have the level 2 service a lot of that complexity. So you can take complexity and push it from the level 2 or the level 1 into the level 2. Now, you're still going to have to figure out how to do invalidations in the level 1. But before, when you actually had to do invalidation, you could potentially have had dirty data, and you would have had to determine a victim and evict that line in the invalidation and actually generate the eviction. But now, because level 1 is, let's say, a simpler write-through level 1, you don't have to generate the eviction. Instead, you just have to invalidate it. It's a lot easier to sort of blast away lines than it is to blast away lines and actually figure out how to take that data and evict it. And this is a lot less disruptive to your main processor pipeline because you don't have to stop to do the eviction and have to block further loads and stores coming from the main processor pipeline. Last, if you have a write-through cache in your level 1, this can really simplify error recovery. And when I say error recovery, I mean from a soft error perspective. So if you have your chip and it gets struck by radiation, and this is actually a relatively common occurrence. You have a chip and you have an alpha particle, something coming out of the sky, some highly energetic piece of radiation hits your chip. Well, that flips a bit. And how do we protect against this? Well, there's a couple different solutions. We can use error correcting codes, or we can use some simpler ideas like parity. And if you have something like a write-through cache, because you never have dirty data in the cache, you can get away with maybe just having parity bits and not full ECC or something like that. And if you were to detect a parity error now in this write-through cache, you just have to basically invalidate the line. You don't have to declare it as being corrupt in memory, because you know that the L2 has an up-to-date copy, which is up-to-date and has the most up-to-date version of it. So the L2 might have more protection on it, but the L1 can basically just invalidate if it gets struck by an alpha particle. So something to think about there, that our level 2, the presence of having a level 2 can really influence our level 1 designs. OK, how else does this occur? How else does a level 1 and level 2 design commingle together? Well, there's a question that comes up of what is the inclusion policy? So now that we have multiple levels of cache, we can actually think about having the lower down level, let's say the level 1, having a certain piece of data, and the level 2 either having that same piece of data or not. And we're going to call caches which have the level, anything which is in a level 1 cache being in a level 2 cache, or anything in a lower level cache being in a higher level cache, we're going to call that an inclusive cache. So the inner cache holds copies of the data in the farther down cache. And the external snoop axis only need to check into the outer cache, as we were talking about before. And we're going to call that an inclusive cache. And we're going to contrast that with an exclusive cache. So an exclusive cache, what you're going to have is the different layers of your cache. For instance, your level 2 cache is not going to have the same data, or may not have the same data that is in your level 1 cache. What does that mean? Well, it means if you evict something out of your level 1 cache, you probably want to put it back into the level 2 cache in an exclusive design. Because that's kind of the idea behind caches. You want to have a certain amount of working set in your cache. So if you evict something out of level 1, that's probably still a relatively useful thing. It still would probably fit in your larger working set of the level 2. So you just don't want to throw it away. You want to keep it around. So in exclusive caches, there's typically a swap operation that occurs. So you're actually going to swap lines between the lower level and the higher level cache when you move data. So the higher level cache, or the farther away cache from the processor, is going to go access main memory, and it's going to bring it into itself. And then when level 1 cache goes to bring it in, you're actually going to swap 2 lines. And this adds complexity to your hardware design. You have to add something which actually does the swap. It could potentially be bad for power. But people have actually built these. If you go look at the original AMD Athlon, they had a 64 kilobyte primary cache of a 256 kilobyte secondary cache, and they were exclusive. Now, you might say, this sounds like a lot of headache. Why would I ever go build an exclusive cache? Well, it has one really big benefit. You get more storage area. Because you're not keeping 2 copies of the same piece of data, you now can store effectively more data in your cache. So if we had this AMD Athlon here, we'd have a 64 kilobyte primary cache backed by 256 kilobyte cache. You have the sum of those 2 values to store data, and it's all unique data. In contrast, if we had the same sort of cache hierarchy, but we were an inclusive cache, you would only have strictly 256 kilobytes, the larger cache, or the farther away cache's amount of storage space. Because the lower level cache, or the primary cache here, only keeps copies of what is already in the farther out cache in the inclusive cache design. OK, let's take a look at a few examples of caches in modern day systems and see what sort of trade-offs people have made. So let's start off by taking a look at something like the Itanium 2 processor here. So the Itanium 2 processor, you're going to see we have our chip. And the first thing you're going to notice about this die photograph here is the level 3 cache is very large. So this has a very large level 3 cache. But this is a big iron processor. So the Itanium 2 was an Intel chip, or is an Intel chip, that actually it was Intel and HP together, I guess, because they were collaborating at the time on this project. But has a big level 3 cache, and it's kind of funny shaped. And the reason it's funny shaped here is they just took all the extra space they had in their die and filled it basically with cache. And this was good, but it didn't quite matter the shape and size, the shape, because it was so far away from the processor that it didn't have to be like a regular shape. But let's take a look at the different levels here. So we have a level 1 cache, small, 16 kilobytes, 4-way set associative, 64-byte line size. It's heavily ported. They can do a lot of loads and stores at the same time here. So it has 2 loads and 2 stores concurrently. And it's fast, single cycle access. So 16 kilobytes is relatively small by today's standards. In 2002, that was probably a little bit on the large side. This was a large processor, but in 2013 time, that's not that big for a level 1 cache. If we step up here, we can see that typically as you step up, you increase your size. Otherwise, what would be the point? but the latency also gets worse. So we have single cycle latency for level 1. We have 5 cycles worth of latency for level 2. And we're a lot bigger. We're at 256 kilobytes of cache. The associativity stays the same. It's still 4-way set associative. And as we get farther away here, we'll see we have a 3 megabyte cache with 12 cycles latency. So that's this big cache on the outside of the chip here. But we actually increase our associativity. So it's a 12-way set associative cache. And the line size in both the level 2 and level 3 cache is larger. It's now 128 bytes instead of 64 bytes. And that's pretty common. You'll see that as you get farther away from caches, people go and put larger line sizes and deal with larger chunks of memory at a time. And to some extent, this is because you have more capacity in these caches. So it doesn't hurt you as much if you call back to our earlier lecture where we plotted the capacity, or excuse me, the line size that you have, the block size versus performance. If you recall, it hurts you more for a smaller cache because there's just not that many lines you can fit into something, let's say, like a 4K cache. But as you start to get to something maybe like a 3 megabyte cache, you can be a little bit wasteful with storage if it helps you with your potentially spatial locality. OK, one point I wanted to make here is a rule of thumb that people typically use for cache design. And this is just an empirical rule of thumb. The empirical rule of thumb is usually when you go from one level of cache to the next level of cache, you want to step up by a minimum of a factor of 8 in size. Now, where does that come from? Well, it's totally empirical, but it's based on how much extra latency you have to add when you add another level of cache hierarchy. So if you add another level of cache hierarchy, it has some extra latency. And if it, while it's going to decrease your cache miss rate, it also is going to make your time out to main memory, let's say, a little bit worse. And there's a trade-off there of, does it make sense to add the extra cache layer and go check the extra cache layer, or is it better just to go out to main memory at that point? And the question is, how much benefit, how much larger does that cache have to be to have any useful benefit? And empirically, when sort of people have built these processors, usually you have to step up by something like a factor of 8. If you step up by a factor of 4, the benefit that you get from the cache due to the extra size does not outweigh the extra complexity and cost and time that is added by adding extra cache. But that's just an empirical rule of thumb. But if you go analyze enough processors, you'll see that basically every cache level steps up by a minimum of 8. So we'll call this the 8x, the 8 times rule, if you will. This cache here steps up by a factor of 16, so it's a little bit more than a factor of 8. But let's look at another little bit more modern processor here. So this is the IBM Power 7. So the IBM Power 7, this is an 8-core machine. There's private level 1 caches per processor, and then there is a big level 3 cache sitting in the middle of this processor. Well, what does this look like? Well, we have relatively small level 1 caches. We have a 32 kilobyte L1I, a 32 kilobyte L1D cache, and latency is higher than our previous example. It's a 3-cycle cache latency. And as we go farther out, we can see we actually have an 8x step up in cache size here from our at least a data cache size perspective. So we go from 32 to 256, and the latency is worse. So we have 8 cycles worth of latency to check on our level 2. And then finally here, we have 8 cores sharing this data, so it's a lot of cores sharing this cache. We have a 32 megabyte unified level 3 cache that's actually built out of embedded DRAM in this process. So IBM has some pretty impressive technology here where they can actually embed DRAM on a logic process. This is not common in most other processes. This is typically only an IBM trait, an IBM Foundry design sort of trait. But some other people do also have embedded DRAM now, but IBM is really the forefront leader in there. But the latency here is quite higher. So we have 25 cycle latency to the Power 7 level 3 cache. OK, let's pull up the scoreboard. So we've been building a scoreboard here throughout this and seeing how adding these different techniques, these advanced cache techniques, help with performance. So what is our scoreboard going to look like here? Well, we have a multi-level cache. And the first question is, what happens for the level 1 perspective? Well, the miss penalty. What does adding a level 1 cache do to the miss? Well, when you take a miss, you have to go out to the next level. And before, we had to go out to main memory, which could be far, far away. So the miss penalty was quite high. But if we have a multi-level cache, and let's say we have a level 2 cache, just a few cycles away, maybe 5 cycles away, your miss penalty now goes down as seen from the level 1 cache when we add this multi-level cache. OK, so that's the level 1. What about if we draw a box around all of the levels of our cache? So let's say level 1, level 2, level 3. What happens? Well, in aggregate, our miss penalty for each particular level is going to go down. So that's a plus. As you go to look at farther away, going to main memory, what you're actually going to see is the miss rate is also going to go down in aggregate, because you're not going to have to miss out of your last level cache as often. So the miss rate here goes down. So you're not going to have to go out to main memory as much, because now you have a larger, but not as big as your main memory or big as your DRAM cache sitting in front of there. So the miss rate goes down. So you have a lower overall miss rate. So let's go on to our next cache optimization technique. So we've talked about multi-level caches. Almost all processors today have multi-level caches. And this is good. It's going to reduce our miss rate. And for at least the lower level cache, it's effectively going to reduce the miss penalty, because it's going to be able to go to a closer cache versus having to go out to main memory. What's our new technique here? Well, the next technique I wanted to introduce is what we call a victim cache. And why do we call this thing a victim cache? Well, a victim is a cache line which is being evicted from your cache. OK, so this victim, or this evicted line, or evicted cache block, typically it's going, if it's dirty, it has to be written back out to main memory. If it's clean, you can just invalidate it and not have to write it back. But what the insight of the victim cache is that we're going to keep around the most recent victims, or the most recent cache lines that we've casted out of our cache, and keep them in a special little side structure that we're going to call a victim cache. And this side structure, this victim cache, is going to be very, very, very small. Now, why is this useful? Well, one of the things that is pretty common is that you're going to have a piece of code which, for instance, writes the same set in the cache. So let's say we have a let's say we have a two-way set associative cache. So there's only 2 sets per index, or 2 ways per index, excuse me. So we go look at the 2 ways. And let's say we have a loop where we read 2 values from an array, and we write it to a third array. So let's take a look at a piece of code that says something like the following. For I 0, I less than some big number, I plus plus. And then let's say we have 3 arrays, which are all large. So let's say we have an array, an integer array, A, and this is, let's say, 1 million, 1 million. We have an integer array, B, which is also 1 million, and an integer array, C, which is also 1 million. And we'll say that this is 1 million, the 1 million, which is basically 1,000 by 1,000. So it's a power of 2. OK, in our for loop here, we're going to have a simple loop. The loop's going to say C of I equals A of I plus B of I. And that's our loop. Now we have a two-way set associative cache. Well, that sounds like a problem here. So if you go look at this, what we're actually going to do is we're going to pull in A. We're going to do a load of A. And this is going to have, let's say, the same index in the cache because we have the same index into this array here. And if these three arrays, A, B, and C, are all aligned or naturally aligned, they're going to basically hit the same place. And you're going to have a conflict with B, which is going to have a conflict with C. So C of I, A of I, and B of I all want to fight for those two ways in our cache at the same index, at the same time, every loop iteration. Now, why is this bad? Well, we're iterating here based on integers, or our cache line is bigger than integers. So what we're going to do is we're going to pull in the cache line, let's say, that has A of I on it. Then we're going to pull in the cache line that has B of I on it. And then we're going to evict one of these two to fill it in because we need to do a write to C of I, which is in the same index in our cache. So we're going to fight there. We have three things trying to fit into two locations. And to make matters worse here, the next time we go around this loop, we could have actually just hit on that same cache line, A, B, and C's cache line, because an integer is smaller than, let's say, our 64-byte cache line here. The integer is, let's say, 4 bytes, and our cache line is 64 bytes long. We could have gone spatial locality and temporal locality here, but instead, we got nothing. We just lost because we have three things trying to fit into two. And even if you use something like least recently used, it's actually going to do the wrong thing here. Least recently used is going to continually kick out the least recently used thing. But the next time around the loop, you want that least recently used thing. So you could actually have done better here if you didn't use least recently used, but instead just, let's say, kept A and B and always cache missed on C or something like that, or pegged one of these three into the cache for a two-way set associative cache. OK, so how do we go about solving this? So let's go back and take a look at the slide here. And we're going to see that what we can do is we can have a victim cache which is hooked up to our level 1 data cache. And this victim cache is going to have effectively extend our associativity on a very limited subset of the lines, or a very limited subset of the indexes into our cache. So if we take a look at this, let's say we have a fully associative cache here for recently evictively lines, maybe 4 entries. And in fact, actually, the original paper which showed this, they had even, let's say, 1 cache line worth of victim cache, and it helped performance. But this relatively small number of entries here for victim cache can extend the associativity of any index in the cache line. So it's a fully associative cache added into our cache miss design. And how does this go about working? Well, now when you go to access the level 1 cache here, if you miss in your level 1 cache, you pull it in from your level 2 cache. But you first go and check the victim cache. Now, how do things get into the victim cache in the first place? Well, when you go and try to invalidate something out of your level 1 cache, instead of just taking that and throwing away that data, you transfer it over into the victim cache. So it's a little cache of most recently evicted lines from our level 1 data cache, or most recently invalidated lines from our level 1 data cache. So it adds some extra associativity. Now you can check this either in parallel or in serial with your level 1 cache. And there's a couple design questions that come up here is on a level 1 miss, and let's say it misses in the victim cache, what goes about happening here? Well, you're going to be bringing in a new line from the level 2 cache. You're going to take what was in the level 1 cache. You're going to move it into the victim cache. And you want to go check this on future cache accesses that miss in the level 1 cache. But the question is, what happens with the victim cache? Well, just like a normal cache, if it's dirty data, you probably want to go write that back to the L2 cache. Alternatively, you could make the victim cache effectively write through. And in fact, usually these sort of victim cache designs, they typically try to make the victim cache write through, because then you don't have to worry about when the victim cache something has to get removed from the victim cache where it has to go. You don't actually have to go and do the write back to the farther levels of cache. Instead, you can just basically throw it away. But that's a design decision. You can decide whether you want that level of victim cache to always be clean or dirty. Thankfully, usually if you're doing the evict, you might have enough extra bandwidth in your L2 here to actually just do the write into the L2 at that point and leave the victim cache completely clean. So to recap, the basic idea here is you can add a couple extra ways, if you will, or a little bit of extra associativity for a very limited set of the indexes in your cache here by adding this victim cache. The downside here is you might have to go check this victim cache. If you do this serially, it might add to your latency out to the L2, or you could think about checking it in parallel, which would potentially increase power or the energy used, but not hurt performance. OK, let's pull up the scoreboard and see how adding a victim cache helps. So first thing we're going to see is that the miss penalty to our level 1 cache is going to be decreased here, because we've effectively added an extra structure here, which is going to be closer, let's say, than our level 2. So our miss penalty is going to be lower. But the other advantage of a victim cache is that the miss rate out of the aggregate level 1 cache plus victim cache together is now going to be lower. So this is going to be better from a miss rate perspective. So last thing I wanted to talk about in today's lecture is prefetching, or the technique of prefetching. So what is prefetching? Well, you speculate that you're going to be using some, let's say, either instruction or data in the near future. So you can say, I think I'm going to be accessing some cache line in the near future. Now, you haven't accessed it yet. The processor hasn't gone to initiate this transaction yet. But because you have some reason to believe that it's a good idea to go do this, you speculatively go and fetch that data from either memory or a farther out level of cache and bring it into a lower or a nearer level of cache. So this is the basic idea of prefetching. Well, what does this look like? Well, there's a couple different varieties of prefetching we're going to be talking about today. So we're going to talk about hardware prefetching, which is a complete hardware-based solution where the hardware tries to detect what is a useful thing to go bring in. We're going to talk about software prefetching, where the compiler or the programmer decides what is a useful piece of data to go get early. And we can talk about mixed schemes, where it's software hinting to hardware potentially about when it's a good idea to go bring in data. OK, so important question that comes up on the slide here. What types of cache misses does prefetching affect? What does it affect? Well, we're bringing in data potentially before it's actually used. But, so that sounds good. That sounds all good. But we're actually polluting our cache potentially with data we don't know that we're going to need yet. So there can be downsides to this. So let's go through the 3 C's. Capacity. Does this affect capacity? Well, yes. It actually affects capacity was effectively a negative way. You've effectively polluted your cache because you've prefetched something into your cache, and you could potentially make the cache have a smaller effective capacity because of this. And this actually trades off, this is the sort of similar sort of thing with conflict misses. You're effectively putting data into your cache that if you have a really bad prefetcher, a prefetcher which actually goes and brings data in that is not accessed ever, we'll say, or not accessed in a short period of time afterwards, you might actually be both polluting the capacity and creating more conflicts. So you can bring it into a line, and because of this, some other piece of data that gets brought in has to go evict that now. It takes time to go evict it, or at least has to make some decision, and it might even mess up the least recently used policy or the replacement policy. OK, so why would we do this? We said this is bad for conflict misses, or increases our conflict misses. Where does prefetching help? Well, it can actually really help with compulsory misses. So misses where you just miss on effectively cold data. The data is just not in your cache. You have to go get it and bring it in. So let's say a first touch data or a compulsory miss. It would be really great if the prefetch system or either hardware or software prefetcher could bring that data into your cache preemptively. And by bringing that data into your cache preemptively, either reduce the latency or remove the latency completely of compulsory misses. So how do we reduce that miss cost? Well, let's say you go to take a cache miss on a line, and the prefetcher already has sort of started to go get that line from the main memory. The miss status handling register could detect that there's a miss already in flight for that line and not actually send out a subsequent request and just wait for that data to come back. And this can decrease the latency of a compulsory miss or decrease the miss cost of compulsory miss. Alternatively, the compulsory miss could just go away. If the prefetcher is really on its game, it can bring the data into your cache, and by the time you go to access that data, it is like it's clairvoyant, if you will. It already knows that the data that you were going to access in the future, and it's already pulled it in, and when you go to access it, it's already there. So prefetching can have some pretty big benefits there. But like all things, including caches in general, you need to make sure that what you bring in is used with high probability. Otherwise, you're just going to pollute your cache. One last thing I wanted to say is that we're going to see this is that instruction caches are usually easier to predict for prefetching purposes than data. Why is this? Well, instructions are very well behaved. Typically, you execute one instruction, then you execute the next instruction, then you execute the next instruction after it. And yeah, there's branches, and programs do have a fair amount of branches, but there's a decent chance you're just going to be executing straight line code, especially in something like a loop where you're going to be executing straight line code for a while, then hit one branch at the bottom and go back up to the top. So your prefetcher can many times be very effective for that. Data, on the other hand, usually data misses and data accesses are a little bit more randomized, but not always. Sometimes you're just going to be accessing, let's say, straight line data, something like a memcopy or something like taking an array and reading the whole array, and a prefetcher can be very effective there also. So let's take a look at some of the issues with prefetching. And we've already touched on some of these things. In order for prefetch to be good, it has to be useful. So it should produce hits in the cache. If the prefetcher is actually producing mostly misses in the cache or bringing in stuff that either instruction, if it's on the instruction side, it never executes, or on the data side, it never tries to go do a load or a store on, it wasn't useful. Now, things get a little bit more complex here when you start to think about usefulness. You have to start thinking about timeliness of the data. So what do I mean by timeliness? Well, if you prefetch a piece of data into your cache, but you do it too early, it's very possible by the time you go read the data, it might have gotten evicted from the cache. So if you bring it in too early, the prefetcher might have just wasted bandwidth and wasted energy going to the next level cache or going out to main memory. And that data may not end up being useful because it wasn't timely. You might have gotten the address right, but gotten it there too early. Or it might have figured out that it was too late. So how does this happen? So let's say you determine that this one line is really good, and you're with high probability you're going to need it. So you speculatively want to go pull it in, but the prefetcher decides this the cycle after the load happened to that line. Well, it didn't help. Maybe even the cycle before, it just wouldn't help because you're too late, effectively. And as we've already discussed, you can have significant cache and bandwidth pollution here. So you can pollute the pollute the capacity of the cache, and you can waste a lot of bandwidth. And this is a problem if, for instance, you're on a multi-core chip or a many-core chip, and off-chip memory bandwidth is really important, and it's a really limited resource. You may not want to actually have any prefetch turned on because you might just be wasting bandwidth. So it's a speculative execution sort of thing. So you're going to be trying to pull in data, but it's speculative. You don't know 100% that you're going to be using that data. And any time that you bring something in that you don't use, you've effectively wasted bandwidth. So this is a big challenge here. From the bandwidth perspective, usually a good place to put a prefetcher is maybe somewhere between, let's say, a level 2 cache and a level 1 cache, especially maybe on the instruction side. But you can think about this that you want to basically pull in data. And this bandwidth here is relatively inexpensive from your level 1 to your level 2 because it's an on-chip bus. It's directly connected. You can make it relatively large. Coming out of the level 2 cache, though, usually, or going out of, let's say, the last level cache out to main memory, that's usually expensive bandwidth. So sometimes people come up with prefetchers that only prefetch, let's say, from a level 2 cache to level 1 cache. But if it's not in the level 2 cache, the prefetch just gets dropped. So that's a pretty common strategy here. OK, so let's start off by looking at the simple case here of instruction prefetching in hardware with a basic example, something like what they had in the Alpha 21064. So it's a relatively basic processor. And we want to look at what they did for performance. Well, they actually added an extra little buffer here that they're going to call a stream buffer. And the stream buffer here is going to store the next line that is likely to be used. So if you take a cache miss, this is on the instruction side, for a particular instruction cache block, let's say block I in this example, you decide, the hardware decides with high probability block I plus 1 is probably going to be used. But instead of polluting our instruction cache in their design, what they did is the subsequent cache block is actually stored into the stream buffer. So they didn't actually pollute their cache. This is kind of like the a little bit of extra associativity here, but only for the next predicted line, if you will. OK. So in this example here, what would happen is you'd be executing out your level 1 cache. And let's say you fall through. The code just falls through. There's no branch at the end of the cache line, and you fall through. Well, the predictor actually did really well here, and it overlapped effectively the cost going out to either the level 2 cache or going out to the main memory for that subsequent cache line. So it hits in the stream buffer, and the stream buffer gets moved into the cache. And the hardware system says, the hardware prefetching system says, aha, I went and I'm now executing block I plus 1. Maybe it'd be a good idea to go and prefetch block I plus 2. And effectively what you're doing here is you're overlapping the execution of block I with the fetch of block I plus 1. So you can be doing two things at one time. You can be using the CPU fetching, executing from block I, and you can be using the cache moving data this way into the stream buffer for block I plus 1. And likewise, when you go to fetch, when you're executing, let's say, block I plus 1, you might be fetching block I plus 2. OK, so that's the instruction prefetch side of the world. Life gets a little more complex when we start to go look at the data prefetching. Now, why is this? Well, it's not as well structured as instructions. Instructions, you just typically blast through the code, keep falling through. In the data world, you don't necessarily know because you've went and accessed, let's say, address A, that you will go access some other address because of that. But you can try. So people have implemented a bunch of different prefetchers that help to some extent. The most basic thing you can think about doing is actually just doing something very similar to this we had in the instruction example. If you go and you take a cache miss on, let's say, block B, you go also fetch block B plus 1 into your cache. And to some extent, this helps. You have to be a little bit careful here, because you might be wasting capacity and bandwidth. But in some cases, this is helpful. So if you're streaming through an array, this helps. If you're doing a mem copy, this helps. This prefetch on miss. Now note, we say prefetch on miss here, but we don't say prefetch on hit, which is a little bit different than our example in the instruction space there. So prefetch on miss, it's only when you take a cache miss that you go, let's say, fetch B plus 1. Now, there's different strategies here. Prefetch on hit, prefetch on miss. You might think about doing either of these dependent on the heuristics of what your hardware comes up with. So that's prefetch on miss. Maybe you actually want to do one block look ahead. So this is much more, this is basically the same thing we were doing on the instruction side here, is if you go access, let's say, block B, and this means not necessarily a cache miss, you go and actually fetch from your next level out of cache B plus 1. OK, so a question comes up is this the same thing as just doubling your block size? Well, that's interesting. Because you effectively go fetch, whenever you touch B, you go prefetch B plus 1. This kind of looks like just making your block size bigger, because this is just doubling the block size. You'd always bring in 2 blocks. But it's only a prefetch operation. So you could think about having it, for instance, just load from your L2 into your L1 when you have this example, and not actually have to go out to your last level cache. So you could think about having different trade-offs there. Also, the downside of this is that it's not just making your block size bigger. You effectively have 2 sets of tags here. So that's a downside of having something like this one block look-ahead scheme. But you could think about taking this example and actually extending it to an n block look-ahead. So if you go to access block, let's say B, or cache line B, you go fetch a couple after that. And the name of the game here is you're trying to hide memory latency, main memory latency. So what would be really great is if you go to access, let's say, block B, and you know that the hardware somehow determines with heuristics. Typically, how you implement these things is little watchers that watch what accesses you're doing and then decide that it's fruitful to go and actually do a prefetch. You could say, I'm accessing block B. I should start trying to read from main memory block B plus 1, B plus 2, B plus 3, B plus 4, all the way up to, let's say, big N here. And by doing this, you can overlap the latency so that if you go try to access that next block, it'll have already been there. And you don't have to wait for the latency going out to main memory. This actually can increase performance significantly. OK, so that's the basic examples. But those don't always work well. Sometimes you might have something like an array access where you're not touching, let's say, every byte in the array. Maybe you're accessing every nth byte in the array, or some offset. Well, how does this happen? Well, this is actually really common if you're trying to access an array of structures, or an array of, let's say, class objects. Why is this? Well, if you have a structure, you have different fields in the structure, and they are at different offsets inside the structure. So if you have an array of them, they're packed densely. And if you are reading, let's say, some subfield of a structure, and you're reading every element of that array, you're actually going to have what's called a strided access. So you're not going to be accessing byte 1, and then byte 2, and byte 3, what's called unit stride. Instead, you're going to be having some offset as you move through the array. And if this structure is large enough, what might end up happening is you may not actually want to go and fetch the next line, the next line, the next line. Instead, you might want to fetch just the lines that contain the portion of the structure that you want to go access. So what does this look like? Well, you need something like a strided hardware prefetcher. So if you see a pattern happening, typically that's when you fire up something like a stride prefetcher. So if you go look at a modern day Intel processor, they actually have stride detectors. So there's little pieces of hardware which watch the cache access pattern or the processor access pattern and will say, aha, I see that the processor is accessing cache block B plus n, cache block B plus 2n, cache block B plus 3n. Maybe we should go prefetch cache block B plus 4n. So, but n is the stride size. So you may not be pulling in every block in series, but instead pulling out in blocks that are spaced out through memory with some spacing. But with everything, you have to be careful that this does not pollute your cache, both from a bandwidth or a capacity perspective. So let's take a look at an example here. We have the Power 5. The Power 5 has a pretty sophisticated hardware-based predictor, or hardware-based prefetching and prediction schemes. So they actually have 8 independent stride prefetchers per processor, which can each prefetch up to 12 lines ahead of the current axis. Wow, so that's pretty impressive. They basically have little pieces of hardware there seeing what is a likely thing to go access based on what the program's doing and try to bring it in early to improve performance and reduce the cache miss latency and reduce the cache miss time or rate, if you will. OK, so that's hardware prefetching. We can also think about having software-based prefetching. So the compiler can figure out, aha, or maybe the programmer who's running code can say, I know that I'm going to go around this loop many times. So instead of waiting to take a cache miss when I really, really need it, which is when I have to go do this add here, let's say of A of I and B of I, instead we can say, OK, I know the next time around the loop I'm going to be accessing A of I plus 1 and B of I plus 1. So let's tell the memory system that I'm going to be accessing A of I plus 1 and B of I plus 1 and get that operation out there early. So we can effectively have the software help the hardware here by doing a complete software prefetch. And there's sort of 2 ways you can think about doing this. One way is that these prefetches are basically just loads that'll bring the line in early. Alternatively, some architectures have a more hybrid hardware-software approach where you'll actually have a prefetch instruction. And the prefetch instruction will tell the hardware, or hint to the hardware, that it's likely that you're going to go be using this data, but maybe you don't want to waste off-chip memory bandwidth for this. So only pull in, let's say, from the L2 to the level 1 cache, but don't go take a cache miss for this because this has some probability of not being correct and shouldn't take priority over true cache misses. And if you had just a normal load and operation for your prefetch, you wouldn't be able to detect that case. So in some of the hybrid solutions, prefetches will actually turn into special instructions. Software prefetches will actually turn into special instructions. OK, so what are the issues with software prefetching? Well, software timing actually ends up being the biggest challenge here, not predictability. This loop here is very predictable. We know we're just going to stride through array A and array B. But what we don't know is we might end up being too late or too early. So you have to get sort of the right time. You have to get the time right when you actually go to access these different things. So what we're gonna do here is we're gonna say, instead of accessing I plus 1, we are gonna access maybe like I plus P here. And this is a settable parameter where you can say, this is a few cache lines into the future, we can pull it in. And we want to set that correctly so that we pull in at the right time so that we can cover the cache miss latency time out to either the next level of cache or maybe out to main memory, but not early enough that we actually pollute the cache and actually cause conflicts somewhere else. So if we set p here huge, we would be pulling in data potentially way too early. So if we set this to, let's say, bigger than the array size A and B, it's very possible that we'd actually be polluting the cache with wrong data, if you will. A few other things that come up here is, how do we go about trying to estimate p? Well, this is a tricky thing. Why is this hard? Well, we don't quite know what the latency is, and we don't quite know whether A and B are going to hit or miss, or whether the hardware prefetcher is going to fight against our software prefetcher, and things get a little bit complex here. And it's really just because you don't know the memory load, the actual congestion at the memory controller. You don't know whether lines miss or don't. So you effectively have a piece of dynamic number here, which is being determined at static compile time, we'll say. And then also, you don't quite know what architecture you're going to be on. So different architectures, let's say, or different microarchitectures for the same instruction set architecture might have different cache miss latencies. So if you want to write one piece of software that works on all of them, there may not be a correct value of p. So you have to think about that. Finally, I wanted to say is that you must consider the cost of the prefetch instructions. These are not free. You have to add these 2 extra instructions here. And if your performance benefit, if the performance benefit of having prefetch instructions does not outweigh the cost of adding 2 extra instructions, it's probably not a good trade-off. You probably shouldn't be doing something like this. So next lecture, we're going to talk a little bit more about different software prefetching issues and other ways to rearrange code in the compiler to effectively bring data in a more structured manner. But let's take a look at the efficacy of prefetching. So which of these things does this help or hurt? Well, what we're going to see is, first of all, we're going to actually potentially help the miss penalty. So when does the miss penalty help? When is the miss penalty made better? Well, if you have a cache, if you have a prefetch in flight to a piece of data that you then have a demand miss for, you effectively cut the latency for that demand miss, or the miss penalty, down to just finishing the currently in-flight prefetch. So you can take that cost and make it a little bit shorter. Miss rate. Miss rate also is better. Why is miss rate better? Well, if you had a prefetch occur and it brought it into your cache, and then you hit on that data, you just have fewer misses out of your cache. So your miss rate is better. A couple other things here. Hit time and bandwidth. Prefetching, if done poorly, might actually hurt your bandwidth. So there might be a negative here if done poorly. And hit time typically is not really affected by prefetching. OK, we'll stop here for today. Welcome to our next installment of ELE 475. Today we are going to be continuing our discussion of advanced cache techniques. And one of the big things we're going to get into is talking about how to build out-of-order memory systems. So what I mean by out-of-order memory systems, basically I mean you can have memory operations out at the memory system, but they execute out of order. And you can mix this with the in-order processor pipeline or an out-of-order processor pipeline. It's the designer's choice. Both sorts of designs have been built and have been successfully built. But where this is important is it allows you to effectively get more memory parallelism, because you can have transactions going out the memory system in parallel, and the processor could continue an overlap computation with the memory. So just to recap from last lecture, we have a revised agenda here, with all of our different cache optimization techniques or advanced optimization techniques. Where we talked about pipelining caches. We talked about adding a write buffer and a coalescing write buffer last lecture. We talked about the reason and the motivation for multi-level caches, so 2-level caches, 3-level caches, maybe even 4-level caches backed by main memory. We talked about having victim caches, which were extra little highly associative caches that you can put next to a low associative cache or something like a direct mapped cache. And effectively, this can increase your performance quite a bit. Because once you sort of miss in your direct mapped cache, you can go out to your victim cache, and if the victim cache may have the data you're looking for, and this gets over small numbers of lines which are highly contended and might blow out, if you will, the number of ways or the amount of associativity you have in your cache. We talked about hardware and software prefetching, and this is where we stopped last time. We stopped at hardware and software prefetching, and today we have a couple extra topics. We're going to talk about how to bank your cache as a technique to get more bandwidth. The easy technique to get more bandwidth is just to put multiple ports on your cache, but that gets quite expensive because you have to duplicate your possibly your sense amps. You probably have to duplicate the write logic, and in the worst case, you may have to duplicate the storage space. In today's lecture, we're going to talk about some software optimizations that the compiler can do. We're going to start off by talking about some software optimizations that are easy to do without transforming the code too horribly. And then we're going to talk about some that actually require some pretty heavy lifting with respect to code transformations and what you have to do to reorganize the code, still in valid ways, but by doing such, you can actually have better memory performance and better cache performance. And then we're going to get to the meat of today's lecture. We're going to be talking about non-blocking caches, or sometimes called lockup-free caches, or sometimes called out-of-order memory systems. Then a couple potpourri at the end here. We're going to have critical word first, which basically means that when you go out to the memory system, you ask for the word that you need most urgently, and the memory system will give that back to you first. And this allows you to restart quicker. And then there's a very similar idea, but possibly easier to implement, called early restart, which instead of asking for the memory system to return the data in a specific order and taking advantage of that, instead what you do is the memory system gives you back the data in order, or whatever the canonical order is that it expects to give it back to you with. But when the word shows up that you need or you're stalled for, you just restart the processor pipeline. So if you're asking for one word out of a huge cache line and it happens to be the second word in the cache line, you don't have to wait for the whole cache line to get loaded into the cache. But this has some extra complexity. And finally, we're going to talk about way prediction. Way prediction, we touched on it a little bit when we were talking about some of the instruction issues in superscalars. But we're going to talk about a little bit more in detail here, where way prediction allows you to predict where to go find either the next piece of data you're going to go access or the next instruction you're going to go access. And this is important if you have a multi-way cache. In a direct map cache, there's only one place to go find it. In a two-way cache, there's two places to go find it. And if you check both, you could try to do that in parallel. That probably wastes a bunch of power. Or we can do is you can predict that, let's say, it's in way 1. Or you can predict that it's in way 0. And using that prediction, if you have high prediction accuracy, you may only have to fire up half your cache. Or if it's on your critical path, you don't actually have to do 2 comparisons or 3 comparisons or 4 comparisons, however high the associativity of your cache is. So let's go take a look at banking strategy and multi-porting our caches. This is a little bit of recap. I think we talked about this briefly during last lecture, but we're gonna continue on with that. So here we have our two-way issue processor pipeline. You have program counter reads in the instruction cache. You have your instruction registers. And what's interesting about this is in this pipe, we can only execute one memory operation per cycle. Well, that's a limiter. Let's say you want to execute 2 memory operations, or 3 memory operations, or 4 memory operations that are all independent of each other. What do you go about doing? Well, in our 2-issue pipeline here, logically what you want to do is you want to somehow put the data path on both pipelines and remove this restriction of where you can execute memory accesses, in which pipe you can access memory accesses from. OK, that doesn't sound too horrible until we go look at the implementation of this. So we can go and have a true multi-ported cache. So if a true multi-ported cache, if you think about the decoding logic on a read, we're going to have to at least duplicate that decoding logic. Likewise, if we want to actually execute 2 writes at the same time, we're going to have to duplicate the row decoders for that logic. And a lot of times how people actually go to implement this is they basically duplicate the entire cache to get an extra port for a variety of reasons. It could, the area increase could be large, and it could even be double for a 2-port read and a 2-write port sorts of cache. So they don't even share the storage data. But that's like only a little bit of the problem. The other problem here is that it also increases your hit time in your cache. And no one likes increasing hit times in caches. Now, why does it increase the hit time? Well, unless you, for instance, duplicate everything, if you try to share some of the logic, you're basically going to increase the loading on the readout of the cache here. And by increasing the load, or this is going to have slower drive strains, you will probably increase the time. And you can go look in something like Cacti, which is a tool from HP, which has different cache configurations. And you can see that adding a second port is usually the last thing in the world you want to do when you're doing a processor design. It ends up being really quite expensive, mostly in terms of area and somewhat in terms of timing. So can we do better? Well, maybe yes, maybe no. So one thing you can think about doing is instead of actually having a true dual ported cache, can we have a pseudo dual ported cache, or a cache which has the same external interface? So if we sort of cut out here in the middle, we have 2 addresses coming in, 2 datas coming out. It looks the same. But instead, we actually put something else in the middle here. What do we put in the middle? Well, we actually put 2 banks, they're called, of our cache. And the first bank is half the size of our cache, and the other bank is half the size of our cache, and they're both single-ported. What this is relying on is if you have statistical memory accesses that have some good pattern to them, the probability that you'll actually end up routing 2 memory addresses to the same bank and get what's called bank conflict will be quite low. And instead, the probability that you actually go to 2 different banks will be high. Now, you might say, well, bank conflicts sound pretty possible to happen. This is sort of the naive drawing here. When people go to build these things for large caches, you'll actually have many banks. And then let's say and if you have more banks than the number of ports you have, you can make a decent argument that the probability you're going to get a bank conflict ends up being quite low. Or the probability that any 2 random addresses will end up going to the same bank will be low. Now, let's talk a little bit about addressing and how we do this assignment of addresses to banks. The most basic thing is you can just maybe low order interleave it. Or you could try to high order interleave it. So one of the questions that logically comes up here is, which is better, low order or high order interleaving our banks? Anyone want to take a guess on this one? So when I say low order, I mean use the low order bits to hash into which address bank or which bank you go into. High order leaving, you use some high order bits. Or maybe middle order interleaving, use some middle order bits. What would you choose if you were a designer? So this is a good insight. So if we think of something like we're accessing an array, and we're trying to stride through the array. So we're striding through the array. The high order bits of those axes are all going to be the same. So if we have high order interleaved bits, all the high bits are going to all be the same, and we're going to get bank conflicts. They're all going to go to, let's say, bank 0 all the time. And therefore, our cache, which we were trying to have more or higher throughput, didn't get any higher throughput. OK, now I'm going to give you a counterexample. Counterexample is, let's say you are striding through an array, and you have an array of structures. Pretty common thing to do. And the structure is, let's say, 120 bytes long. And we go and access the first byte in that 128 byte structure in a loop. Are the low order bits of the address the same between all of those? Yeah. So that can be problematic. Now our high order bits are the same, and our low order bits are the same. What's changing in that example? Some medium bits, some bits a little bit higher than the low order bits. So more of what I'm trying to get across here is that you have to be very careful about how you do the bank interleaving. If you have naive hash functions, or naive functions which assign address to a particular bank. And you may not want to even have, you can think about having more sophisticated hashing functions or assignment from address to bank. But if you go to do that, this is on your critical path of your memory load. So you may not want to have a complex hash function there. So you might want to just take some middle order bits. You might want to take some low bits and some high bits for your bank assignment. It gets a little challenging here. You probably don't want the highest order bits, definitely, because in most systems, all those are always, let's say, 0 or something like that. It's very unlikely that your higher order bits are something important, usually, unless you're sort of accessing the stack where those are usually 1, all 1. So I have another, I think we talked about most things on a slide. Benefit, we're trying to go for high throughput here. Bank conflicts, we talked about how you can get a bank conflict. We talked somewhat how you can avoid bank conflicts by having more banks than you have ports into the ported structure. And that's just from a statistics perspective, if you have, let's say, a 32, your caches, you have a 32 kilobyte cache, and each bank is 1 kilobyte or something like that, then all of a sudden you have the probability that you have 2 ports trying to access one particular bank. It's kind of like a birthday problem. So it's not, or it's the trying to find if 2 people have the same birthday, because it's not quite easy probability to go figure that out. But it's quite low because it's roughly, 1, what is this? It's probably 32 times 1 over 32 times 1 over 32. So it's not the lowest thing in the world, but it's possible to actually reduce the probability that you have a bank conflict with random accesses. And if you have a better hash function, of course, you can do better. Extra wiring. So what do I mean by extra wiring? Well, in our previous design, we didn't have these sort of crossover paths. So what this really turns into is a mux here, a multiplexer there, a mux here, and a mux there for the address paths. So this adds extra wiring, extra delay by banking. And one of the bigger challenges of the extra wiring for going to multi-banked memories is it'll shrink the bank size or shrink the memory size. And if you traditionally sort of look at memories, they like to be larger. You can amortize the overheads a little bit better of for instance, the sense amplifiers at the bottom of the memories and the row decoders and the column decoders if it's bigger. Because, for instance, the row decoders and the column decoders will roughly grow as the log of the size, or the log of the number of bits or something like that. But if you make each of your caches really small, and you have multiple of them, that overhead gets worse. So you have to have more sense amps, more row decoders, more column decoders. So it's something to think about. But usually that's relatively small, and you're willing to pay that, unless you get some really funny aspect ratios. So what I mean by really funny aspect ratios is if you want to have if you shrink the cache too small. So if you have, 256 byte caches, and the readout width is, let's say, a byte, you get this very long and narrow cache. And you can try to sort of use column addressing or something to sort of squish that into a more square form factor. But sometimes if you shrink your bank size too small, you get very funny aspect ratios or very long, skinny RAMs that don't fit well into designs. OK, uneven utilization. So what do I mean by that? Well, what I mean by that is just like you can have bank conflicts due to the addressing of the hashing scheme, you can also have a pathological case where all of the interesting data is stored in one of the banks. So let's say, going back to that example, you use low order interleaving to the lowest order bit of the address, which is not the offset, we'll say, to choose between bank 0 and bank 1. But it just so happens the program pads out all of its data structures such that that bit is a constant of 0, basically, for all the useful arrays you're trying to access. Well, what that'll do is it'll locate all of the data lines in bank 0. Well, we just took our big cache and cut it in half because we've effectively placed all of our data over in this bank. So we're getting uneven data utilization. So we get uneven bandwidth utilization and bank conflicts, but we can also get uneven data utilization. These sometimes go together, though, the bank conflicts and the uneven utilization. Because if you're accessing something a lot and it's in bank 0, that means it's probably stored there. So you have uneven storage patterns also. Questions so far about banking, why we want to bank? This is a pretty common thing to do. So a good example of this is if you go look at the Niagara processor, which is a Sun microprocessor that has, the first Niagara had 8 cores. And if you go look at their cache structure, they had 8 banks of the cache. So it was a relatively heavily banked cache in their last level of cache. If you go look at something actually like the multi-core Intel chips out there, they even have more banks. Actually, I think I saw one once where it was the 32 megabyte last level cache for the Intel Itanium 2 had some incredibly large number of banks. I think it was either 32 or 64 banks in their cache. And they were wide also. So they had lots of bandwidth going through that cache. OK, so if we go look at our cache banking, what this really, really helps here is we're increasing the bandwidth. We might actually be hurting some things. We might be hurting the hit time a little bit. Miss rate, miss penalty shouldn't change. The cache size is the same. We haven't effectively increased or shrunk the cache size. Even if you get lots and lots of bank conflicts or if you have poor utilization, that's still not actually affecting your miss rate because you would have been conflicting in the same size cache. Logically, you could draw a box around it. It would be the exact same thing. It's just that happens that, if you were to have it not be a banked cache, you would have every other line be in the contested ones or something like that. So just having better memory layout is good all around. OK, so now we get to what can software do for my cache? And what can software do for my memory system? Well, surprisingly a lot. And compiler people actually do spend a fair amount of time thinking about this. So one of the things you'll actually see is you'll see the compiler many times pad out data structures. So if you go disassemble a piece of C code that you have, you'll actually see the compiler many times will insert extra bytes, which wastes memory, but it's there to improve performance. And how this improves performance is it'll make the access patterns, for instance, either not conflictive in our cache or conflict in our cache in a strange way, which is beneficial, or will somehow exploit either temporal or spatial locality. So you can do lots of tricks here to either improve spatial or temporal locality. One of the things I did want to talk about is sort of a hybrid software-hardware solution here that you can actually add instructions to your processor to give hints, to allow the compiler to give hints to the architecture whether to pull something into the cache or not pull something into the cache. So many times the compiler will actually know, or the programmer will know, I need to use this data exactly once. Now, if you know you only need to use that piece of data once, should you pull it into your cache? No. You're never going to reuse it. You're never going to get a cache hit. You're just going to take the cache miss, and then at some point later in the future, you're just going to evict it, and it's going to hurt your miss rate. So instead, there's been an introduction actually of, sometimes people call this non-temporal hints or no allocate bits. So one way this actually works out sometimes is certain pages in our memory system are marked as being non-temporal and it won't be cacheable. You can do this on x86. Actually, there's non-cacheable bits in the page tables, for instance. A finer grained way of doing this is actually having special load instructions or special store instructions which say, do not ever bring this into my cache, or do not pollute my cache with this data, because I never intend to go read this again. And lots of architectures have started to include this now as an optimization. Another fun thing you can do is if the compiler or the software system or the programmer knows that you're never going to use the data again, why let it sit there and rot in your cache? Get it out. Get it out as quickly as possible. Now, there's a couple different ways to do this. So one of the instructions that you can add to the architecture and have a software-hardware approach to this is you'll actually add something that I think on x86 is actually called flush and invalidate. So the idea is that you may still have dirty data in that location, and you want to flush it out to main memory, or flush it out of my cache, and invalidate the data in the cache. And by giving the compiler or the programmer fine-grained control of this, you can effectively kill data that is in the cache and make it clean, or make it clean and not valid in the cache, that line. So when you go to bring in new data, you don't have to evict something. So you're effectively, it's kind of the inverse of prefetch. In software prefetch, you bring something in early. Here we push something out early. And that can be a pretty big benefit. One of the other things is that I don't quite have this on. I don't have this on the slide here, but there's a corollary to this. Lots of times architectures will have an instruction called. Basically, it's just like inval instruction. It'll invalidate the data. And the semantics of this are a little bit, you have to be a little careful with, because this inval does not flush the backing data out to main memory. You're changing architectural state with this instruction. So if there was dirty data, you're effectively deleting that dirty data. Sometimes people will actually use an instruction similar to that instead of a flush and invalidate if you know that you just have scratch pad memory, or you don't need the backing data. And that's a way to, you don't have to waste the write back bandwidth to your L2 or your L3 or your main memory. You can just say, this data is now dead. I never want to use this again. So that's typically an inval instruction. And inval instructions will lots of times take a cache line number instead of an address. Sometimes they'll take an address, and it will validate the entire cache line. Unfortunately, you need to take the entire cache line or cache block and throw it out. And finally, the inverse instruction of that instruction, which a couple architectures have. I know Alpha has. I think x86 has later added it. I don't know what's called in x86. On Alpha, it's called, it's like something called like write 064, I think is what it's called. Basically, what you can do is, if you have some data and you want to write some data to your cache, but you don't want to have to go pull in the backing data, because that will just effectively add bandwidth out to your main memory system or out to your higher levels of cache. Instead, what you can do is there's a special instruction which will just fill a whole entire cache line of zeros out of nowhere. And what's nice about this is now that you've filled an entire cache line of zeros, you can go do writes to those zeros and fill it in with useful data and never have to have gone and fetched the background data from main memory. So it saves bandwidth. So these are all different hardware, software techniques together that the compiler can use to optimize performance. But yeah, I do want to just finally one last thing about this improving spatial locality and temporal locality. If you ever go disassemble a C program, you'll definitely see structures. If you run a C program with feedback-driven compilation, you'll see that a lot of times they'll actually reorganize the data structure. And languages, so for instance, if you go look at the careful description of what C says about this, some languages allow you to insert padding or reorganize some of the fields in a data structure. And by doing that, you can get more performance by effectively reorganizing the data so you put all of the things that you access in a row right next to each other. And that'll get you, for instance, spatial locality. OK, so now we get to go to some of the fun software optimization strategies up here. So let's go to the first one here. I'm going to give you guys a second to look at this code. Look at the top example first, or the top piece of code first. We have a loop around a loop. For j is less than n, for I is less than m. OK. So it's a doubly indexed array, x here. We're effectively striding through this array somehow. And we're multiplying every element in the array by 2. Seems basic enough. So one of the questions that comes along here is, in C, the default layout of x, it's a doubly indexed array. And we're walking by the higher index is the inner loop here. So if we look what's happening here, this is a 2D array. X. And I goes that way, and j goes that way. Now we're walking through this array by I. So we're going to walk down, in that pattern. By default, in C, this array gets laid out such that the second index gets laid out contiguously. And the higher order index gets laid out non-contiguously. So this would be address, let's say, 0. This would be address 1. This would be address 2. This would be address 3, 4, 5, assuming these are all bytes. And we come back over here, 6, 7, 8, 9, 10, 11. Unfortunately, with the way that the top loop is written, we're effectively hitting, we're fighting spatial locality of the cache lines. That's not good. Well, lo and behold, if we do the exact same operation, and our compiler can easily detect this, and we just flip the order that we stride through the array, we'll take going this way through the array, and instead, we'll go that way through the array and get spatial locality perfectly. So by doing a simple loop interchange, life gets a lot better. Actually, before I move on here, I do want to say this brings up a good example of packing of data. I have something here which has 6 bytes in a row. 0, 1, 2, 3, 4, 5. Now, one optimization that compilers will many times do is they'll actually pad out this structure, let's say out to 8 bytes, because it makes the math a lot easier to go stride through the array indices. So that's an example of one of the things that I showed before. It'll also sometimes even have better cache performance, because you'll pull in an entire line at a time versus straddling different cache lines if you have a non-naturally aligned structure like we had before. That may not happen in this, it may not hurt in this example if you're striding through the entire array. But other examples, it could definitely be harmful if you are trying to operate a lot within one row, for instance. OK, before we move off of loop interchange, does that, actually, what type of locality does this improve? Spatial, yay, we drilled that one in down pretty well. OK, so let's look at our next piece of code here. For I less than n, we multiply b of I times c of I and deposit it into a of I. And then the next loop, we do something very similar. We take c of I multiplied by a of I and deposit it into d of I. Well, I'm going to say, how does this happen? This seems like a brain-dead way to write this piece of code. Yes and no. Maybe you do something in between here, between these two for loops. And it may not be readily apparent to everybody that you can actually do anything about this. Like, because you have some piece of code here which goes and reads, I don't know, all of A, for instance. Well, the compiler can recognize this and actually say, well, we just wrote this entire array. And now we go back and just read this entire array. And we read C before also. That's not very good. Because we're effectively, let's say these arrays are large. We're going to read in C an element of C, read an element of B, deposit an A, and we're basically going to stride through the cache. And all these 3 arrays are going to kick each other out. But by the time we get back to here, A of 0 is definitely not going to be in our cache. Maybe A of the last element will be in our cache, or A of n will be in our cache, or A of n minus 1 will be in our cache. But A of 0 is not going to be in our cache. So our compiler can think real hard about this and do what's called loop fusion and pull these statements apart, such that you take b of I times c of I, put it here, and then use that. You're probably actually going to do that in a temporary variable. You're probably not going to do that through main memory if you have a of I and a of I in statements right next to each other. But you still have to write a of I, we'll say, for program correctness. And you take a of I and c of I, multiply them times each other, and put them into D here. What's nice about this is you're actually going to bring in a cache line of b of I, bring in a cache line of c of I, do the multiplication. You're bringing in, well, you already have a of I because that's your destination, and you just have that in a variable. And then you can write it over into d of I and stride through all those cache lines together, and effectively you are not having to go refetch a of 0 multiple times. Instead, you've fetched it once. And what's also nice, you don't have to go refetch, let's say, c of I twice, or c of 0 twice. It's already there in your cache. OK, so question comes up here, what type of locality does this improve? Temporal, yes, because before we were bringing something into the cache, kicking it out of the cache, bringing it back into the cache. Both these actually exhibit decent spatial locality actually already, and we didn't really change the spatial locality of what's going on here. They're both striding through arrays spatially, but temporally, we don't have to kick we don't have to kick A and C out of the cache effectively twice, or we're bringing it into the cache twice. So we're able to exploit a bunch of spatial locality here. Or sorry, able to exploit a lot of temporal locality here. OK, so now we get to something a little bit more sophisticated. Matrix multiply. Common thing for computers to do. You want to take, at least in dense matrix codes or linear algebra sorts of codes, you take matrix A, you want to multiply it by matrix B. So this is like traditional MATLAB kind of code. You have some MATLAB, you have a big array, you want to multiply it by another array. And let's take 2D matrices. This applies to higher dimensional matrices also. But it's easy to draw two-dimensional things on a two-dimensional screen. It's hard to draw four-dimensional things on a two-dimensional screen. So we'll start with that. Here's our naive implementation. We got 3 for loops going on here. And what we're doing is we're doing the traditional way that you learn how to do matrix multiplication. You take a row, multiply by a column, and that's that spot. You take this row, multiply by that column, that's that result. This row by that column, that's that spot, this row by that column, there. And you just work through it. And you're basically, let's step through actually what the multiplication actually is. You take this value, multiply by that value, take this value, multiply by that value, and you continue going down and summing each of the multiplication results. And that's how we ultimately end up with this point here, or this value here. So this is the input, input, output. OK, let's think about what this does to our cache. OK, let's say our cache line, these elements here are bigger. They're not just 1 byte or 1 word. They're a couple words, or they're maybe like a long or something like that. They're a big data structure, or a big value. And let's say only 3 values fit in a cache block or a cache line. So when we go to this multiply, we basically have to bring in 2 lines for this 1 row. And then over here, if cache lines are arranged this way, as we go down this column, we're bringing in different cache lines and only using 1 value out of that cache line. Well, that's not super great. Make matters worse, let's go look at the output array. The output array looks relatively similar to the input array. We're writing here, writing here, writing here, writing here, writing here, writing there. So we're just kind of streaming through memory here. I don't know if we can do better. That's a good question. At least we're going, at least the way how this code is written, we're going from left to right. So we're actually taking advantage of spatial locality. We could be doing worse. But just to recap here, this is pretty poor cache accesses. We're bringing many cache lines. They're all going to fight each other, especially for large arrays. And over here, we're pulling in line after line, even though one of the interesting things is after we do this multiplication times that, we're going to do this multiplication by the next one, which sounds good. You know, this times this, this times this. We should be getting temporal locality here. But the downside is, for very large size matrices, as I said, this can be multiple blocks or multiple lines long. What's going to end up happening here is this may conflict with something else farther down if it's a very large cache in its own array. Or you're just increasing the occupancy into the cache. So we're going to talk about blocking, which will actually make it so that we can actually only read 1 block at a time and do the multiplication in multiple steps. OK, so the code gets a little bit more complicated when we go to blocking our cache, or blocking our memory multiply. Sometimes people call this tiling instead of blocking. I think tiling is traditionally sort of meant as a matrix multiplication specific term to a more general thing, which we'll call blocking. Code gets a little more complicated. But what we're going to do here is we're going to start off by here and multiply these three elements by these top three elements and deposit it into the result. Now, you might say to yourself, that's not the result that needs to go there. It's not. It's only half of the result that needs to go there, in fact. So you need to do something. You need to finish this multiplied by that and add what was here before with that new value. But the nice thing is addition is communicative, so we can reorder these steps. And in fact, what we're going to do is we're going to block or tile and have this block rotated, multiplied by that block, and deposit the results here. And then, in our next step here, if you see, we're actually going to sum into the same destination. So the first step is we're going to take this, multiply by that. And what we're going to see here is we're going to have 1, 2, 3 cache lines. And over here, we're actually going to have 1, 2, 3 cache lines. Even though we're accessing them this way, we actually designed this algorithm such that we reuse that other portion of the data we pull in here. And then we're going to do that and sum the partial parts of the multiplies into these 9 locations. And then we're going to do the second half of that. We're going to take this, multiply that, and accumulate them into there. As you can see, this actually is going to have some better locality, which we'll talk about in a second. And we have to bring in fewer cache lines at the same time and still get good performance. OK, so let's look at the, if you want to compute this part over here, because we talked about in this example here, computing this entire result array. So how do we compute that part over there? Well, it's the same idea. You're going to take this, multiply by that, deposit it there, and then take this, rotate, multiply by that, and accumulate it into there. So couple things just to recap here. Couple happy things about this. We're really able to shrink the working set in our cache. So our cache capacity is lower for what's really going on here. Or rather, our effective cache load is lower. The number of cache lines we need to keep in our cache is quite a bit lower. We also can have better, so that's going to be temporal locality. Because we're basically going to have the data in our cache, and we're going to be working on the data in our cache. Now, we also end up with, if you look at the input array here, we're actually going to have better spatial locality. Because before we were sort of streaming through all these different cache lines, and now we can work on one block at a time. And especially in our result matrix, because this and this reuse these entries in our result matrix twice. So we can get some benefit out of that. But so the answer is you get both temporal and spatial locality improvements here. But it's a fun software optimization you can do that'll improve your performance. OK, so let's go look at compiler memory optimizations and what we can get out of this. Well, we can get some different things out of this. If you do the cool tricks where you have non-temporal hints, to some extent you can use that to increase your bandwidth because you're utilizing less bandwidth. Hit time, I don't think we're really going to allow software to change the hit time. That's a hardware constraint, so we're not going to have anything to do about that. Miss penalty, we might be able to help out with. So how does the compiler help out with miss penalty? Well, it can schedule the data so that it's in closer, for instance, that blocking algorithm will actually use a smaller cache footprint. So it'll fit into a smaller cache, so we won't have to go out to the L2. So a good example of this is, let's say you have a matrix multiply. In your matrix multiply, it fits in your L2. The naive approach fits in your L2 but doesn't fit in the L1. OK, now we get to move on to the meat of today. We're going to talk about non-blocking caches, also known as out-of-order memory systems, also known as lockup-free caches. So I think the first paper that actually published on this called a lockup-free cache. Lots of people call these things non-blocking caches today. And if you think about it from a memory perspective, it's an out-of-order memory system. What does non-blocking cache allow you to do? Well, it enables you to have subsequent memory operations occurring from the main processor pipeline even when you have a miss that was earlier in your instruction sequence. So in all pipelines we've looked at up to this point, you take it, even our out-of-order pipelines, we talked about them as basically saying when you take a cache miss, you just sort of stop the pipe. Because we couldn't deal with having memory coming out of order, even to our out-of-order processor pipelines. We didn't have enough bits to track all that. Well, now we're going to talk about structures that allow us to track out-of-order memory. So two major things this allows you to do. It allows you to have a cache hit under a miss, and it allows you to have a miss under a miss. So what do I mean by miss under a miss? Well, what I mean by miss under a miss is you do an access, like say a load to some address, it takes a cache miss. And then you have a load, a secondary, but you keep executing your program. And you do another load, and that takes a cache miss also. And you're able to process both these things if you have a non-blocking cache, which allows you to have miss under miss. One of the big points I want to get across today is that this is not only for out-of-order processors. We talked a lot about out-of-order processors. Believe it or not, you can actually hook up a non-blocking cache to an in-order processor, or even a VLIW in-order processor. Now, how do you go about doing that? Well, two major ways that you can do that. One is when you take the cache miss, you mark the variable, or you mark the register as not being there. So when you go to actually read the data, you block. So we'll show an example of that in a few slides up from now. But really what I was trying to get across here is you can have in-order processors with out-of-order memory systems, and you can have out-of-order processors with out-of-order memory systems. Both these things are possible. OK, so challenge list. Couple big challenges here. There we go. Couple big challenges. If you have multiple out-of-order misses, well, the memory system is going to return data sort of out of order. You have to deal with this somehow. It's possible you might end up in a different memory bank, and the data comes back in different orders that you sent it out in. And this gets hard to deal with. You sent out a cache miss for X, Y, and Z, and they come back in Z, Y, and X order, or something like that. And you need to make sure you're delivering the right data to the right location in the cache, and the right data to the right instruction. So we're going to need some big associative table to go figure this out. Second problem, major challenge here, is lots of times you're going to have a load and a store to the address that you want to take a load and store miss to later. So what do I mean by that? Well, it's pretty common that you are going to be doing loads sequentially through memory. And if the first load in the cache line misses, the second load is also going to miss, but they're on the same cache line. You don't want to send two of those out to the memory system at the same time, because you might confuse the memory system. Worse, let's say if you have a load to one address and a store to another address, but they're both within the same cache line, the load might go out to memory, start getting the new memory. You do the store goes out to memory, and you actually store in the main memory somehow, but you bring in the original load data, and they sort of pass in transit or something like that. The load data passes the store data, and all of a sudden, you're going to have the wrong data in your cache. You don't have the updated data. And the reason that ends up happening is because that store didn't have any place to merge into. It couldn't actually go deposit its data into the cache, for instance. OK, so how do we go about handling this? Well, before we do that, let's look at a timeline here. Time goes from left to right on this graph. At the top here, we have a blocking cache. The blocking cache, you're happily running in the CPU. You do a load, we'll say, or a store. Doesn't really matter in these systems. And you take a cache miss. In the most basic blocking cache, you're going to wait for the cache line to get filled in. And then you can return the data, and then you can keep running the CPU. There's no overlap happening here. But we want to go fast. We want to go faster. If we have a non-blocking cache, we can take a hit under a miss. So what that means is we're running along, and we take a cache miss. This goes out to main memory, but we don't stop the CPU from executing. So let's say it is a load for register 5. Well, as long as no one looks at register 5, does the processor care that we took a cache miss to register 5? Probably not. Now, there might be some complexities around if that load to register 5 takes a trap or something like that, or takes an interrupt. Then it might care, but let's say it doesn't. One of the reasons that this is actually usually safe to do is that you've already done all the memory checks, and you're sort of past the commit point at that point of the processor. Because you're already pretty late in the processor pipe by the time you know you get a cache miss. So it's not too harmful. But then you keep executing here, and you access your cache again, you do a different load, and you get a hit. That's great. You can just keep executing. And it's only when you go to use the data do you stall. And effectively, we've overlapped computation with our miss penalty. And this is pretty nice. Now, something else we can do is we can do misses under misses. So a miss under miss, we're executing along here. We take cache miss, and we send out something out to the main memory system to go get the data. But we don't stop executing. We keep executing. We take another miss, and we send that out to the main memory system. At some point, maybe we actually go to look at the data. Or possibly, maybe we don't actually look at the data until here, and the CPU just keeps executing the whole time. It overlaps multiple memory accesses with computation. So this can be really powerful. And you can do this, as I said, with in-order processor. One thing I do want to say is, usually you have a limited number of outstanding memory accesses. Some small integer, maybe like 4 or 8. There's diminishing returns as you add more and more. But usually, this isn't sort of thousands of outstanding memory accesses. So let's look at the structure here. There's a couple different names for this thing. It depends what school of computer architecture design you come from. If you are from the Alpha or the Digital Equipment Corporation design philosophy, you're going to call this thing a misaddress file. If you come from the Intel school of things, you're going to call this a misstatus handling register. Misstatus handling register actually predates Intel and goes back to, I believe, Control Data Corp. There's a paper from Control Data Corp on misstatus handling registers back in the late 60s, early 70s. But let's look inside of this thing and sort of understand what's going on here. You're going to have some small number of misstatus handling registers, probably in a register file. And you're going to have a valid bit. And you're going to have a block address. Now, this block address is not the address of the load of the store. It's the address of the load of the store. It's the address of the cache line that aligns to that load in the store. Because What we're going to use this structure for is we're going to use this to check subsequent memory accesses or subsequent misses against previous ones that have been going on. And we may have multiple sort of in flight here, and we don't actually need the address of the load or the store. We need the address of the entire line, because we need to check the entire line, because that's what's in play. We have a bit here that says whether it's issued or not. Now, why we have that is just because you took a miss doesn't mean it's actually out of the memory system or going to the memory system yet. So you sort of fill this in, and it sits around there until you have some time to go talk to the main memory. And hopefully, that happens quickly. Some architectures that you may not even need this, because you might just stall until it actually goes out to main memory. But once it's issued, you tick that bit. And what this allows you to do is it allows you to have multiple misses which are not issued. So if you have a miss under a miss under a miss, then they happen really quickly, you can fill up this table quickly and not actually have to wait for it to stream out to main memory or all the requests out to main memory yet. So that's half of it. And then we have a bunch of load store entries. And with these load store entries, they also have a valid bit, and they have a pointer back to one of these entries here. So this just is a number which says sort of which entry you're in the miss status handling register file. And this is for individual loads or stores that are occurring. So what it allows you to happen is, let's say you have a load miss to address 0, and you have a load miss to address, I don't know, 10. And these both are in the same cache line. You can fill in this table with 2 entries, and they'll actually both point back to the same miss status handling register location. They'll have different offsets. And then in the destination field, you'll fill in which register on the processor they're destined for. So what we're going to do is we're going to use these tables such that when a load comes back, or excuse me, when a cache line comes back from main memory, we'll be able to check in these 2 tables and do 2 things. One, we'll be able to fill it into our cache somewhere. And 2, we'll be able to return the data to the correct destinations. And we'll be able to find which piece of data we need, given the offset in the cache line. Oh, that's a mouthful to say. So this is a little bit of a complicated data structure here to actually work out. Now, I wanted to point out where the associative matches versus indexed matches happen in these tables. So one of the things that you might notice is that this block address, we're going to have to check every subsequent miss against this block address. So we're going to take the higher order bits of the address, check it against this, and if it checks that, we don't add a new entry here. Instead, we just merge it into a currently pending one, but we do have to add a new load store entry for that, which points back over here. When a memory transaction comes back from main memory, we're going to look back in this table and say, oh, here's the one that I had issued. I need to clear it out of the table. And given the number of the location that I'm clearing out of the table, I'm going to associatively check that against all of the load store entries and wake up the ones that match. So if this is entry number 1, and there's multiple number 1s in here, all the ones that have number 1s in here, I need to return that data to the registers. Now, when I return the data to the register, I have to mark the register as being available again. And the type here basically just says, is it word, half word, byte, and is it a load versus a store? One other thing I wanted to say is the destination here for loads is going to be the register identifier. Now, this might be a physical register identifier versus a virtual register identifier or an architectural register identifier if you have a registry namer. So if you have an out-of-order processor here, this might get more complicated. This is typically a physical register identifier, not a architectural register identifier. For stores, you also effectively need to track something in this table, because you need to merge the store with the background data. So this is going to basically add an entry in here It's going to send out to main memory, go get the background data, and when that comes back, it's going to deposit that into our cache. And we need to point at some other buffer. This is very similar. We had that future store buffer. You can have an array of those, for instance, and it'll tell you which one to go play the store against our cache with. And you can merge the return data with the store data that we've stored locally. So this is kind of fun. We can have memory coming back out of order. We can have memory being issued out of order. Lots of fun toys here. And one of the fun things we can do is we have an ability, because of this associative check here, to check to make sure that the data coming back, or excuse me, subsequent requests hit or miss here and will merge, so we don't have to generate more memory traffic or cause strange things happening where you have responses coming back and new requests going out for the same line, and you might lose some data in flight. I should point out this is only one implementation. Lots of times what people do is in this misstatus handling register, there will actually be a tag field, because main memory will not necessarily keep track of the entire address when you get a response back from main memory. Instead, it'll just have a tag. So instead of checking against the block address, you might check against a smaller tag. That's one way that people sort of make this a little bit easier. Another way sometimes people do this is the tag, if you have a small number of cores, might actually be which entry you are in this table, so you don't have to do an associative check. That's sort of a optimization on this. You still need to do an associative check when future loads and stores that miss go out to memory, because you need to check in this table. I think I walked through most of this already. On cache miss, you have to check the table for the matched address. If found, you allocate a new entry that points to the misstatus handling register. If not, you have to make both a load store entry and a misstatus handling register entry. One thing I did want to point out here is if you run out of misstatus handling registers or load store entries, this is not the end of the world. You could just stop the processor. So if you have, let's say, 8 of them, and you run out of all 8, you have 8 outstanding memory transactions, you just stop for a while. It's going to come back at some point. One of the loads or one of the main memory accesses is going to come back. So you can just stall for a little bit. On data return, you need to find the load and store that's waiting for it. Going back to what Bertrand said, it's very possible that the load and store that was waiting on it might have actually disappeared in that time period, well, at least for a load, because you might have to write after a write occurs. That's OK. You still want to fill it into your cache at that point. And of course, you can have multiple loads and stores. When the cache line is completely returned and you've finished checking against all the load and store entries, you want to deallocate both the load and store entries and the misstatus handling register entries. OK, so a little bit of fun here with in-order machines. So you can sort of see how this relatively logically fits into an out-of-order pipeline. If you want to fit this into an in-order pipeline, you can, it's not too hard. You can actually add a scoreboard for each individual register. And when I say scoreboard, you're not tracking where the data is coming from. Instead, there's a special bit saying, this register is out to lunch. This register is out in the memory system. If you try to go access it, just wait, or just stall. And then when the memory, because it's a variable length sort of thing, so your scoreboard can't have, this will be ready in 5 cycles, because you don't know. It's out in the main memory system. On load miss here, you can mark the destination register as busy. When it comes back, you mark it as available, and you uninstall the processor. But if no one actually went to go use that register in the meantime while it was out in main memory, the main processor never stalls, and no one's ever the wiser. OK, so I wanted to, we're almost out of time, so I wanted to pick it up here for a second. So non-blocking caches, they can effectively increase the bandwidth to your lower levels of caches, your sort of L1s. The other thing they can do is they can increase the bandwidth because they can merge misses to your cache. Now, you probably would have actually gotten that anyway if you had a blocking cache. But the misstatus handling register basically allows you to have multiple cache misses merge into one transaction. Your miss penalty is obviously lower because, going back to this picture here, we've overlapped the miss penalty with other useful work. I'll just skip wave prediction because I don't think it's that important. But I did want to say one or two words about critical word first and early restart. So critical word first, basic idea here is that you can express to the memory system which word is the most important word. And usually RAM arrays, the buses are oriented in a way that they'll actually allow, it takes multiple pumps or multiple cycles to transmit the data across the bus. And usually these arrays don't care, at least like main memory, like DRAM arrays, big things on your chassis or on your system server motherboard. They don't really care if they return the data in this order, 0, 1, 2, 3, 4, 5, 6, 7, 8. Oh, probably 7, sorry. Or if you return it in a different order. Because they just want to use the bus as much as possible. So what you can do is you can say, address 3 is the most important one. Please return that first. So what can happen is it'll return the data, and right here, address 3 comes back, and it comes back first always, because that's the address that we're trying to access for this load miss. And you can start the CPU executing again while the rest of the cache line is filling into the cache. So you've basically done a little bit of overlapping, but this doesn't help that much, because usually there's not that many, a cache line is not that long. So it might help you a little bit. So if it takes 8 cycles to fill the cache, you might save 7 cycles if you were going to the last, if you were trying to load the last word in the cache line. But if you were trying to, let's say, load the second line in the cache line, it only saves you 1 cycle. And there is some complexity in actually building critical word first systems. Early restart is another way to do this, which a little bit less hardware. Instead of having the memory system rotate the memory that it returns back to you, it still returns the memory in the canonical order. But we just wait until, let's say, we want to address 3 here, it comes back, and then we restart there. So you can see there's a little bit of time here, which we can overlap the fill in with executing in the CPU again. In the canonical case, if we don't have early restart, what's going to happen is we have to wait for the entire cache line to come in, and then we can restart. So we lose these cycles there. We don't get that overlap. OK, let's stop here for today. And I'm going to remove the wave prediction stuff from material we're talking about, because this is not that important. Good afternoon. Let's get started. So today we are going to be continuing our quest into computer architecture, and we're going to be talking about virtual memory and address translation, together with how you do virtual memory protection on top of that. So this is a crossover between architecture and operating systems topic. So your operating systems many times has to worry about how to manage memory. Also, many times you have to worry about how to manage who can access memory. You have to worry about how much memory different users could possibly have. But even in a uniprocessor system, this becomes an important thing, that a uniprocessor system and a uni-user system, not a multi-program system and not a multi-user system, but just a single user system, also has to worry about layout of memory and worrying about running different libraries, different portions of programs, and how to lay that out effectively in memory. So we're going to continue videotaping our lectures today to put online that you guys can go look at later. And so let's get started by talking about memory management. And we're going to talk about a couple different schemes today, which aren't very popular. We're going to talk about some schemes that have some historical basis. that are still important and important to understand, and there's some vestiges in today's architectures. So for instance, one of the things we're going to be talking about today is called segmentation or base and bound registers, which still shows up in x86 processors today, but is not very common as a memory protection system. But it was designed as a memory protection system when it first got started. And then we're going to go, and at the end of today's lecture, we're going to talk about fancier virtual memory systems that are used in modern day computers, how your operating system goes about managing memory with that, how it provides efficient use of memory, and how it protects different accesses. So we can broadly separate memory management into three really important and orthogonal functions. First of all, translation. So in translation, what we're doing is we're taking one address and we're turning it into some other address. So we're able to remap addresses. Now you might say, why do we want to do that? Well, by doing that, we can have more flexible memory layouts and prevent things like fragmentation. So fragmentation, we'll talk about that more later in today's lecture. But fragmentation basically is the problem that if you have lots of little pieces of data or code that get loaded, and then some of them complete or go away, you're going to end up with holes in your memory space. And it's very hard to reclaim that unless you try to compress or relay out the memory. And lots of programming models don't allow you to go recompress the memory. This is familiar if you've ever taken a basic data structures course where you had to go deal with managing something like a heap. In a heap, you have it's pretty common to allocate different sized objects on your heap, and then you free up those different sized objects. And if you happen to free them in a bad order, you end up with little chunks of memory that are really hard to go use for something else. Especially if you want to go allocate something very large, you might have enough memory in your system, but it's just not contiguous. So one approach to this is to have things like garbage collectors, which is what Java and a lot of the managed programming languages do. But something like C or C++ does not have that notion of garbage collectors. So we're going to look at that more, not from a heap perspective, but from a perspective of the entire memory system. So sort of one level out from a heap. So inter-program fragmentation and inter-program garbage collection. The second important function of our memory management here is we want to restrict access or protect access to memory and allow only users who are supposed to be able to touch a certain piece of memory to be able to touch that certain piece of memory. And this is important if, for instance, you have one system which has someone's bank records on it. And on that same system, someone else can log in. They can telnet or SSH into it or remotely log into it. And you don't want one user to be able to go read some other user's bank records that just happen to be laying in memory. So we need some way to protect that. And memory protection gets us there. It allows us to have different users using the same system, different processes using the same system, and we can restrict the access to different locations in memory or protect the access to different locations in memory. Finally, memory management, one of the important sort of points of memory management is that you can actually think about having more memory than your machine has memory. Now you might say, well, that doesn't make any sense. No, it doesn't make any sense. But if you have a flexible enough hardware system, you can think about using other things to look like memory. So for instance, if you have a hard drive in your computer, you can use that hard drive, which is very, very large, to effectively increase your memory size by taking data, which is laying in memory, and put it onto the disk, and sometime later in the future, take it off the disk and put it back into memory, and trick the user into thinking that they have a larger memory space. And this is virtual memory. So it allows us to have transparent extension of the memory space using something slower. I mean, it could be disk. It could be, in the older days, some drum that spins where you sort of store things on the drum. You could even, nowadays you can swap onto flash. And if you ever go look in Linux or something like that, this is called your swap partition. Sometimes called a backing store, a couple different names it goes by, but it's a virtual memory storage location. Nowadays, most systems provide this with some sort of page-based system, which we'll be talking about. But these ideas are all orthogonal, and you can have different mechanisms to solve all of them in different ways. And we'll be talking about some of the historical aspects of that. OK, so let's start off in the beginning. Well, in the beginning, we didn't have fancy memory management. Instead, we had addresses. You want to go access some piece of memory, you come up with an address, and that directly indexes into our memory, and you get back the data. Well, that's OK if you're running one program at a time. So if you go back and look at EDSAC, which is one of the original, probably the second computer, I think, maybe the first computer, first sort of modernish looking computer, it only had physical memory addresses. So what this really meant is only one program could run at a time, and it had all of memory. And the addresses that were used basically didn't move around because there was only one program running, and it owned everything. And I/O could directly touch memory, main processor can directly touch memory, and life was simple and OK. But unfortunately, you couldn't really run multiple programs. You couldn't protect multiple programs. You could definitely not take memory off of disk and put it into memory, because you had no way to sort of remap things. So it did not fulfill those sort of three requirements that we were talking about. It didn't do any translation. It didn't do any ability to protect, and it didn't have any notion of virtual memory. One thing that did happen is that users still wanted to be able to write subroutines that were location independent. So what I mean by that is you write a subroutine, and this is back in the days when people were writing these subroutines in machine code or assembly code. And you still wanted to be able to write one subroutine and be able to use it and call it and use it in different portions of your programs. So one of the tricks that people sort of thought about is how can you still have location independence even when you only have one physical address space? So you can't remap things. There is no translation going on here. Well, in fact, you can actually use the linker or the loader to be able to go do this. So actually, quick show of hands here. Who knows what a loader is? Who knows what a linker is? OK, so we got a little bit of coverage with linker. Linker, what it does is it takes multiple different compilation objects or compilation units. So if you take a computer program that's made out of a bunch of little files, a bunch of different source files, you compile up each of those separately. And when you link it, you take them and you put them all together into one program, and you resolve all the addresses, all the jumps, and the data accesses across that one program. So that's linking. That's static linking. Now, dynamic linking, you guys might have seen DLLs, dynamically linkable, loadable objects. So what happens with DLLs is you'll actually do that linking step of resolving the addresses at runtime. So you can actually do either. You can either do it dynamically or statically. And the loader is the piece of code which actually takes a binary off a disk and puts it into memory somewhere. And typically, the loader will go and do a last level linking step at the end. So on a modern day Linux system, your linker, or excuse me, your loader, when you type up, when you go to execute a program, and you type, I don't know, you run ls or something like that on your Linux system. First thing it does is it goes and finds the ls bits on the disk, and it takes that and copies it up into RAM somewhere. So you could do this on this absolute addressing system. And then what it does is it goes and figures out all of the dynamic libraries that are needed. And it goes and takes those off disk and puts them into RAM somewhere. And then it's going to, the last step here is the original program had pointers to addresses that didn't actually exist yet, because it didn't know where the respective libraries were going to be loaded. So it has to patch the program up. It has to rewrite addresses to make sure that the newly loaded program points at the correct location. So that's a runtime linker doing its job. The static linker can do that same sort of thing, but at compile time, or excuse me, at assembly time or linking time in your program. OK, so that's absolute addresses. And if you have the physical hardware for an absolute address machine, it's simple. It's kind of what we've been looking at this point. You have your program counter, you stick it into your cache, instruction cache gets an instruction out. You take your address if you're doing memory access, you stick it into your data cache, and it gets some data out. If you take misses, everything's a physical address, it goes to the memory controller, it goes out to DRAM. Seems simple. It is. But like I said, it doesn't solve all the problems we want to solve. OK, so now let's start talking about stuff that's a little bit more complex, if we actually want to do address translation. So address translation, actually before we leave this, we're going to call addresses that touch main memory physical addresses. And we're also going to talk about this notion of a virtual address. A virtual address is actually just an address that the main processor uses, which might be translated somehow into an address which is out in main memory. So looking at our dynamic address translation slide here, well, what was the motivation for this? Well, we wanted to start running multiple programs. We wanted to be able to overlap computation with I/O. And this really leads us to some form of multi-programming here. So we're going to want to run 2 programs at the same time. Now, note these 2 programs might be run by the same user at this point. We're not really talking about multi-user multi-programming. That's well, you probably want protection to do that. But right now, we'll just talk about translation. And one of the big challenges here is, so you want 2 programs to run. What happens if those 2 programs were linked at the same location? So they both want to run at the same location in memory. Or the data they want to access, when you statically link these things, is at the same location in memory. Well, that's kind of inconvenient. So one thing you can start to think about is actually have some notion of relocation. And you may not do this on a sort of chunk-by-chunk basis, but instead you do it on a program-by-program basis. So what you can do is you can have a base register so that all addresses that come out of, let's say, program 1 get added a certain offset to it. All addresses out of program 2 get added a certain offset to it. And all addresses that come out of the operating system have 0 added to them. OK, well then we can just change this base register, and they'll effectively move where our programs are. And we're going to call the address that when we start out that comes from our program the virtual address. And the physical address is where it actually is in physical memory. You could extend this a little bit and even actually add some notion of protection. So you could add something which says program 2 here is only allowed to access up to this location, or this offset in itself. And past that point, it is not allowed to go access anything. Well, that's actually pretty easy to go do. And we're going to call that a bound register. Now, these base and these bound registers, we're going to look at it in more detail in a second. But you don't want the user program to go be able to change the base and the bound register. Because if the user program goes and changes the base and bound register, it can basically remap itself, or it can possibly make its bound big enough to go look at the other program. So let's go look at the hardware of a basic base and bound translation. So we have a program here, and it's going to do a untranslated address. That address is going to get added to it some base, and that's going to be the address you actually go to access your caches and your memory with. This address is compared to a bound register, and if it's bigger than some bound, it gets slapped on the hand or it gets killed. You get some sort of violation. Now, this actually still shows up in modern day architectures, yet it's not super widely used. But in x86, you actually have segments which have base and bound registers. So there's some problems with base and bound registers, which we'll talk about in a second. But otherwise, this works OK. You can have different segments. You can have programs that are basically relocatable by the operating system by setting this base register. You can protect memory by setting the bound register. And if the application tries to do anything outside of those parameters, it'll get killed. Questions so far? Sounds pretty good. One of the cool things you can do is you can have not only one set of base and bound registers, but you can actually think about having. Actually, before I move off the slide, I wanted to say something interesting here. What happens if you have two programs that want to share some data? Can we do that here? That's definitely an option. You might want to share data and not code, or you might want to go the other way, which is actually more common, is you want to share code but not the data. So for instance, if modern Unix systems do this. They don't necessarily use this. They use it more of a page-based approach. But if you launch 100 copies of LS at the same time, the code for LS will be the same between all 100 different versions. So what you can do is you can actually point the base register at the same location and use the same piece of physical memory. So that's a nice little trick here, is you can basically share the same code segments between all your programs. And modern day systems actually do this. They share the code segments between all the same versions of the program. Obviously, if you have someone who's running version 1.2.7 of something, let's say LS, and someone else is running version 2.3.9 of LS, you can't share the code segment. But your OS will know that those are different codes. But if it is the exact same code, you can save a lot of memory by just only having one copy of it in RAM and not, 1,000 copies of it in RAM. So that's the big advantage of this separation. And in fact, this is actually used pretty recently. This is still, to some extent, vestiges of this, as I said, is in x86. But the old Cray vector supercomputers actually did not have a more advanced memory system, but but instead just had base and bound registers. And this was actually, to some extent, OK for something like a supercomputer, because supercomputers don't typically run lots of programs at the same time. They typically run one really big program. So it was a little bit easier in that setting than using an architecture like this for something like general purpose operating systems like your Linux desktop or something like that, or Windows desktop. OK, so let's take a look at how this fits into the pipeline here. So here's our pipeline. We want to add base and bound registers. It's actually not so bad. We have to add an adder here to add in the base into the program counter. And we have to add an adder for the data base register into all of our loads and stores. And then we need to add a comparator here, a comparator there to check to make sure we don't fall outside of our bounds. Now, one of the interesting things about this, though, is we're adding an extra adder. So you think this would slow down our clock frequency a lot. We're adding a whole nother, let's say, 32-bit wide adder. But conveniently, we already have an adder in this path. We already have an adder in this path. So the adder in this path is basically our PC+4 calculation. So while we do the PC+4, we can overlap that with the next addition. And you can actually have the carries basically happening at the same time. And the cost of it is only one extra carry delay out of a full adder. Similar sort of thing, over here. It's kind of the same way that you would build a multiplier or something like that, where you actually overlap respective additions in the multiplier concurrently. So it's kind of nice that you can do this relatively low cost. To some extent, it just sort of melts away. You can even go faster. I think this note here, we talk about carry save adders. You can also do carry select adders, which are even faster, where you just have basically one bit that tells whether the last bit carries or not. But you can go quite fast here. OK, so let's talk about the challenges of base and bound. So let's say we have memory here. And we start off with 3 processes: user 1, user 2, user 3. User 1 is 16 kilobytes. User 2 is 24 kilobytes. User 3 is 32 kilobytes. And this is just some open space, free space here and here. So all of a sudden, more users show up, and they start to run some processes. User 4 goes here and fills in this space here. User 5 goes down there because it can't fit in this 8 kilobyte segment. So 8 kilobyte segment or 8 kilobytes free space here and has to go down here. OK, that's all well and good. 2 and 3 kill their programs. They stop running their programs. So all of a sudden, this goes away. Or excuse me, 2 and 5 goes away, and this one goes away. So we start to get some holes showing up here, and some small holes. And if you repeat this sort of thousands and thousands of times, at some point, with relatively high probability, you end up with lots of little chunks of memory, which are hard to go reclaim. And this is memory fragmentation. If you go look at something like a modern-day garbage collector, it'll actually try to re-squish all this data together. But that's hard to do when a program's running. It's hard to go take these other programs and go re-squish them. It's also possible that, depending on how the addresses are laid out, you just may not be able to go do that. If you have base and bound, it's possible that you might actually be able to go move the data, but you'd have to go copy all of the data. And that takes time. You have to copy your entire memory system. This is why something like garbage collectors can be pretty inconvenient, because some of the garbage collectors actually require you to go copy everything. There's a couple different techniques you probably talked about in your data structures class about how to go do efficient garbage collectors. But let's say we just want to avoid this completely. So can we go avoid this? Well, computer architects came up with something fun here and came up with this notion of paging. So instead of having variable size programs and have variable size segments or data segments, instead what you can do is you can take all of your memory and you can chunk it up into different fixed size regions. So for lack of anything better, let's say you have all of memory and you chunk it up into 4 kilobyte regions. And we call it a page. So what does this really turn into? Well, let's say we have the address space of a user here. And it thinks memory goes 0, 1, 2, 3. Over here, we have physical memory. And what you can end up with is a table which will map these different addresses into different locations, possibly out of order over there. And it's a chunk at a time. So if you go to access, let's say, address 0 to 4 kilobytes minus 1, you are accessing here. If you go to access 4 kilobytes to 8 kilobytes minus 1, you're accessing here. But this is a virtual address space. Once we go through the translation, if we go to access, let's say, address 4182, we're actually going to get mapped up over here into physical memory. And just to introduce some nomenclature here, if you take a processor-generated address or a virtual address, if we go to look at what is actually inside there, there's a page number, which is this number here, which is which page to go look at. And then there's an offset, which is the low-order bits of the address. And the offset says where inside of this physical page to go find the exact byte we're looking for. And it's pretty common for these page sizes to be in the sort of few kilobytes sort of range. If you go look at something, I don't know, we'll take x86 for example. x86 default page size is 4 kilobytes, but it also has a 2 megabyte option and like a 1 gigabyte option. Some architectures like MIPS actually has quite a few page size options. So I think you can go anywhere from 4 kilobytes by maybe powers of 2 all the way up to, I think, maybe 4 megabytes. So you can have different page sizes. But for right now, let's just abstract that and just say there's a fixed size of some small number of kilobytes. Actually, the first original machines actually had these even be smaller. They had them be maybe about 512 bytes. But as memory got bigger, page sizes could get bigger. We'll talk about why you might want to have bigger page sizes. But really what happens here, this page table allows us to take a contiguous memory, a set of memory addresses, and map them into a non-contiguous space. Now, this can really get away from having fragmentation. Because all of a sudden, the worst we can be, the most amount of memory we can be wasting is a size of a page. So let's say you have 1 byte on this page here, and we call that as used. Well, your worst thing you're using is 4 kilobytes here, if it's a 4 kilobyte page. And this page and this page, some other process can use. Because we have a very flexible remapping system. It's a complete mathematical map. So that's looking at if you have one program. We can extend this pretty easily to having multiple programs at the same time, where each program has a different page table. So if you have a processor, which is executing multiple programs, and let's say it's time multiplexing these programs, in physical memory, you can actually intermingle all the different pages of the different programs and do memory allocation where you try to pack the memory as tight as possible or reuse the memory as much as possible. And these really flexible page tables here will allow the remapping to be arbitrary. So you don't have these, at least you don't have an external fragmentation problem. You may still have what's called internal fragmentation, where you're just not using the pages very effectively. So this is interesting up here. This figure here, we have OS pages. So what are OS pages? Well, the OS itself needs its own code and its own data. And many times in a paging system, the OS itself may not use a page table to go access memory. Because it needs to go, let's say, start up another program, so it needs to be able to touch these bytes here and go kill a program or load some data from a particular application. So many times the OS is, to a large extent, held to a higher standard here. And the OS can actually go and touch all physical memory and not have to go through a mapping layer. OK, so here we have private address spaces per user. So something we have not addressed yet is, where do we store this stuff? And how big are these page tables? Well, they can get pretty big. If you want to basically have a program that can address 4 gigabytes of RAM, you're going to need a page for each 4 kilobytes of those 4 gigabytes, that's a lot of pages. So you need to store this somewhere. So the naive approach is you just have specialized register files in your processor that hold the entire page table. Unfortunately, that ends up being, well, for a 4 gigabyte space with 4 kilobyte pages, ends up being something like, with I think a 32-bit page table entry, we end up something with like 4 megabytes. And if we have 100 processes running, that's 400 megabytes that we have to store somewhere. Well, it means we probably don't want to keep it in registers or register files in our main processor. Now, conveniently, as we have more and more RAM, this allows us to have more and more processes to run. It allows us to use more memory because we have more RAM in our machine. But also, we have more places to store page tables if we want to put them in RAM. OK, so maybe we want to put our page tables in RAM because as RAM goes bigger, we might need more page tables, but we have some place to go put it. And it's always the case that, well, if we design this correctly, if our page table entries are designed correctly, that the size of a page table to represent a certain amount of RAM is going to be less than the amount of RAM that you have to store in. So some fixed overhead. So let's take, for example, a page table entry which takes 4 bytes to represent 4 kilobytes of memory. That's 1,000 to 1 compression. So as you get more RAM, you're guaranteed to always have some place to put it because your RAM size will grow 1,000x faster than your page size. OK, challenges of storing this in RAM. If we want to go access a page, when we go to access a page here, we have to index this table. So every load we do before was just a single load. But now we're going to have to do a load to go read the page table and a load from the actual physical memory location. Well, we just doubled our number of memory references that we have. And that's kind of a bummer. So what do we do about this? Well, before we talk about that, let's talk about where to store the page table and the size. And then we'll talk about some techniques to speed up the access. So here, let's take a look at where to store a page table. If we have our linear page tables of what we've been talking about up to this point, you can actually just go store them in RAM, and they'll map down to different points down here. And this works decently well. Unfortunately, these still have to be contiguous themselves. So we might get fragmentation problems in the page tables themselves, or different page tables fighting with each other for memory. They're hard to move. So we would like to think about some way to go solve this. We'll hold off for a second on how to solve that. But this is something to think about. It's kind of unpleasant here to think that your page tables themselves cause fragmentation. So I just wanted to sort of recap and show the mechanics of this, of what's in our page table. So in our page table, what we're going to store is we're going to have, well, first of all, we're going to have instead of having a base and bound register, like we had in the base and bound architectures, we're going to have a base that points to the base of the virtual, points to the base of the page table. And then we're going to have some structure in RAM, or structure in the page table here. And what does this structure look like? Well, there's probably a valid bit. There's a physical page number, which points to some place over here. And maybe there's some status bits also. we'll talk about those more in a minute. But you probably want some status registers there. Could track some information like how often a page is being used, which pages are used, maybe some statistics. Maybe you want to know whether you can read the page or write the page. Now, this last note here is sort of the key to time multiplexing a processor between different processes. As different programs execute, and you time slice or preemptively multitask between different operating systems, or just different applications on one operating system, what you're going to do is you're actually going to change this base register to something else. And effectively what this does is this completely changes your entire map of memory as you're executing. And this is pretty fancy if you think about it. You can just one write to one register, and all of a sudden all of memory looks different. And the protection is totally different for the application. Now you might be thinking to yourself, if I'm running in the operating system and I change this register, all of a sudden it changes the entire map of memory. How do I not crash the operating system instantaneously? Because all of a sudden the operating system's code just got remapped to some other location. Well, there's some magic behind the scenes here. This is what I was saying, is that there's a couple different approaches to this. The basic approach is the operating system will not use paged memory for its own purposes. It just uses physical memory for everything. And there's some special bit that says you're in operating system mode, and what you're doing basically doesn't have to abide by the paging system. That's one approach. Another approach is you'll have entries in the page table here that are all the same in every process. And it always maps the operating system in at a certain location. So you can change this willy-nilly, but all the things you go to change it to will have the operating system mapped to the exact same location. That's another approach that people use. And there's some things kind of in between those. Just to flip back here, one thing I did want to point out is it's important that an application is not able to modify its own page table or modify other applications' page tables. And hence, this application here tries to go access something. It looks up in the page table and it says, oh, that's down there. It's important that this does not overlap with someone else's page table. All of a sudden, you'd allow an application to go be able to change its own memory mapping. And that would be quite dangerous. OK, so far we've talked about, actually, before we move off this, let's talk about the exact mechanics of this. So you have a virtual address. It has this virtual page number and an offset. This is actually an index into this table. It's just a basic index. It's one huge table. And it just indexes into here. And it gets some bits. And those bits get basically replaced, to take a virtual address into a physical address. We're going to take the virtual address, and we're going to take the virtual page number, and we're going to remove that. We're going to use that to index into here. And then what comes out of here is going to be used to be the new high order bits of this address. And we're going to call that the physical address. One last note about this. We talk about here a disk page number. We're going to be talking about this more at the end of today's lecture. But it's possible that you might want to use this location here to say the bits for that page are not here right now. They may be on disk. We're going to talk about more advanced. This is the virtual memory subsystem. But a lot of times, a convenient place to locate that information is in the page table itself. OK, so let's crank through some math very quickly here. This page table is relatively large. So let's take an example here, a 32-bit address space. It has 4 kilobyte pages, and each page table entry, PTE, is 4 bytes. So there's 2 to the 20 page table entries. Each of those is 4 bytes big. This is a megabyte times 4. We end up with 4 megabytes. OK, so that's 4 megabytes for this table per user process. And this assumes that we only have, let's say, 4 gigabytes worth of address spaces, or address space, 4 gigabyte address spaces. That's not too horrible. If you have 1,000 processes running, that is pretty bad. And if you go type top on your system and you go look to see how many processes are running, you probably have a few hundred running. So if we use this linear page table notion and you had 1,000 processes running, all of a sudden you'd be using 4 gigabytes of memory, which is your entire address space on a 32-bit machine, just for the page tables, and have no place to put actual data. So I'll give you guys a hint here that people typically don't use linear page tables because it's not very storage effective. Now, what are some approaches to make it more storage effective? You can go to larger pages. So instead of having 4 kilobyte pages, we have 1 megabyte pages. So that would take the number of page table entries and dramatically shrink it. And it would also dramatically shrink the linear page table size. Some downside is you start to have some more internal fragmentation. So if you use 1 byte onto a new page and the whole rest of the page is empty, you'll be wasting a megabyte minus 1 versus 4 kilobytes minus 1. So you have a higher amount of internal fragmentation. Another challenge is that on a page fault, you're going to have to pull in a lot more data. Instead of pulling off of disk, we'll say 4 kilobytes of memory, you might have to pull a megabyte. It's just bigger numbers to deal with, and this could be painful. So let's think about actually let's move from a old computer to a more modern computer. So a more modern computer, we have much larger address spaces. We want to access larger amounts of memory. So my laptop has 6 gigabytes of RAM. Well, 6 gigabytes of RAM, that's bigger than 2 to the 32. We can't address that in a 32-bit machine. And in fact, my laptop is a 64-bit machine. So let's crank through the math now for, instead of having a 32-bit machine, having a 64-bit machine. Well, if we have relatively large pages, let's go for a megabyte page. And, well, a megabyte page is going to give us 2 to the 44 page table entries. And these page table entries themselves are probably bigger because the output of them has to be, let's say, 64 bits instead of 32 bits because the page address is larger now. Well, all of a sudden, one process page table is 35 terabytes. Well, my laptop is a 64-bit machine, but I don't have 35 terabytes of RAM in my computer. Won't physically fit in my laptop. It can't lift up 35 terabytes in today's technologies. Well, that's a bummer. So can we just not go to page systems with 64-bit address spaces or larger address spaces? Well, no, the world's not that unforgiving. We do have some saving grace here. We can think about going to different arrangements of our page tables. And the other nice thing is we can go to more space-dense arrangement of our page tables, or we can go to the notion that our page tables don't always have every single page being used. So for instance, in this linear page table here, I have some slash locations. And what this means is this is some location in memory which doesn't have anything mapped there. So if this is not mapped, why do we want to store or use the storage for that space? So we can actually go up with a sparse representation of our page tables that only have the portions of the page table that we actually need. And it's possible that if every single page in your page table is filled out, you may not be able to get away with a sparse representation, and you might need all 35 terabytes to map one process. That's just one process. If you have 1,000 processes, multiply this by 1,000. Well, the saving grace there is, by definition, if you're going to have one process which is going to map 2 to the 64 locations of memory, that means you have 2 to the 64 locations of memory probably in your address space somewhere. And that's a much larger number, or in your physical machine, rather. That's a much larger number than 35 terabytes. So this compression of the page table entry always being smaller than the page itself allows you to always store the page table entry into the memory that you have, because it always grows to be able to fit inside of the amount of physical memory you have. So how do we go about doing this? Well, one representation that we can think about is having a hierarchical page table. So instead of having one big table that is linear, we have a table that we index into, which tells us where to go look for more data. And then we look in that table to look for even more data. So here we actually show a 2-level page table. And what's interesting is if we have an address here, we index into here, we can actually rule out huge portions of the address space very quickly by just leaving this particular entry in the higher levels of the page table empty. And then as we go drill down a little bit farther, we can also have empty entries. So with this, if you go look at our virtual address here, we're actually going to use different portions of the virtual address to index into other structures. And we can take this sparsity into account. Another cool trick we can do is we can actually reuse, if you have a hierarchical page table like this, you can actually reuse sort of middle-level page table entries between different processes if they're mapping the same space. So for instance, if they're mapping the same instructions, you can actually just reuse all these page table entries between 2 processes and have multiple pointers coming into here. One thing that this does not change is you still have one page table base pointer per process or per user. You don't need to have bases over here, because the bases of the second level come out of the first level. So it's a tree. And here, this is just a 2-level, but there are plenty of architectures that have more than 2 levels of page tables. So if you go try to build a 2-level page table, which is relatively unsparse, on something like a 64-bit machine, it still becomes very large. So as you have more and more address space, your address space, by definition, has to be less sparse if you have a sort of fixed amount of memory in it. So what people will do is they'll actually go to maybe 3 levels or 4 levels of page tables. Now, some downsides of this is we just took something that was, we took a load, which took 1 memory reference, and we had to add an extra memory reference to go look up in our page table, which was in memory, to go find the actual address of the physical address. And all of a sudden, we turned it into 3 memory references, 1 to do the actual load, 1 to look in here, and 1 to look into here. So every level of page table that we add could potentially add another load. Ugh, that's not very pleasant. But before we get to that, and ways to fix that, let's look at how this gets laid out into memory. So before, we had all of the page tables sort of up here, and we had to deal with fragmentation between the different page tables. But now, because we have a multi-level page table, we can allocate it out of our physical memory addresses sort of in an ad hoc manner. And one of the cute little tricks that most operating systems do, and most systems do, is they make the size of one of these levels of tables to be the exact size to fit in a page. Because then you can locate it easily inside of a page. And you can allocate it like a normal userland page and just sort of mix and match it somewhere into the different locations and intermix it. So that's pretty convenient. This solves our external fragmentation problem for our page tables themselves. And we can use sparsity in our address space to use less space for our actual page table. So page table itself is smaller. Downside is we might have to do multiple memory references to be able to resolve a page table address. OK, so now we have to look at the hardware we have to build in order to do this. Just to recap, we have our virtual address. The offset just goes straight through. The virtual page number goes through some sort of address translation through our page table. Then we come up with a physical page number, and this is our physical address. Just like with the base and the bound register, we have a bound. We want to actually take the virtual address number and stick it somewhere into something which does a protection check. So what do we want to check in our protection? Well, we want to check maybe whether it's a read or a write, because you might want to have some pages that are read-only or some pages that are write-only. You may want to have some pages that maybe only the kernel can access. This is what I was saying about how you can map all of the kernel into your address space that's at the same location. But maybe you don't want the user to be able to access that unless you're in kernel mode. So a lot of times there's a bit that says, is this a kernel access, or is this an OS access or a user access? And one of the challenges here is that you really want this address translation to go fast, because you don't want to take every single load and store and turn something that was a 1-cycle operation into a 10-cycle operation, or however many levels. Unfortunately, you could cache miss on your page table access and have to go out to main memory. Could even make it worse. So we came up with a nice little structure to be able to solve this problem. And this nice little structure here is a translation look-aside buffer, or a TLB. And what this is a cache of page table translations. So you shove into it a virtual address, and out comes, or excuse me, you shove into it a virtual page number, and out comes a physical page number. So it is the direct map, but it's a small set of these, instead of having the entire all of memory. So the most recently used, you might write in some sort of most recently used algorithm, or maybe some other algorithm on this, that when you have a hit in your TLB, all that happens is it's a single cycle. You stick an address in, an address comes out. If you have a miss, then you might have to go to some sort of slower case, which has to, let's say, go walk the page table, or multi-level page table, for instance. Let's look at what's in this structure. You have a valid bit. You typically have a bit that says whether it's readable. You have a bit that says whether the page is writable. This allows you to have read-only memory if you, for instance, only have the read bit turned on and the write bit turned off. It allows you to have write-only memory. Now you might say, write-only memory, is that possible? Well, yes. Actually, this is a thing. If you have, let's say, 2 processes that are communicating, and you want to have one process be able to communicate and only write to the other process, but not have the other process communicate back the other way, so a one-directional channel, you can do this with write-only memory. Sometimes these are merged, different architectures. Not all architectures have write-only memory, but for completeness, you want to have that. You have a D bit here, which is the dirty bit. Yes, this is like the song by the Black Eyed Peas, dirty bit. Yes. So there's a dirty bit here. The dirty bit allows you to know if the page has been accessed or not. So let's say you have a writable page, and you want to know if that page has been accessed or written to. You can use this bit. So this is similar to the dirty bits in caches to know whether the data has to be written back to a higher level of cache or not. Well, if you think of memory, or excuse me, what we have mapped into memory as a cache of stuff that could possibly be on disk, we have to know whether to write it back out to disk. So we can use a dirty bit to do that, and that's usually in the TLB structure. Now, there's different ways to go build these caches. The most common way is to actually have them be fully associative. So if they're fully associative, you have to do a tag check. There's a tag in here, which gets matched against the virtual page number, and it's associative, so it can be in any location in this TLB. And then finally, this is the data payload, or the physical page number, which comes out. So this is our base translation look-aside buffer. And it's basically just a cache of the page table. And what we want to do is, at some point, when you take a miss in here, so the opposite of our hit, we're going to pull in a page table entry from our, walk the page table, possibly do that multi-level resolution. We have to go do multiple loads at a time, and take that data and put it in here. And now, the next time we go to access that same page, it hits in here and doesn't take any more cycles. So these are usually fully associative. They're usually relatively small, 16 to maybe 128 entries. Sometimes you'll see multi-level versions of these, where you have a fully associative one at the lowest level, and then some sort of level 2 TLB that backs it. That's a lot bigger and possibly not fully associative. Couple different designs in here for how to go about replacing. Having something like true LRU can be hard if this gets large. And it's possible that LRU is not even a good approach. Unlike caches, this is a very different access pattern. It's not necessarily spatially, there's not necessarily any spatial locality really going on here. You probably have temporal locality, so that might say that LRU might be good, but it's not like there's spatial locality of, because you access one page, there's any probability you're going to go access the page after, the page before it. So lots of the techniques from caches, prefetching, et cetera, doesn't really work here. But from a replacement perspective, people have tried lots of different things. Something that actually works surprisingly well is just random. You just randomly choose an entry, kick something out, and you replace it. Random is actually hard to do sometimes, believe it or not. So a lot of times what people will use is what's called a clock algorithm, where you basically have a free-running counter which says where to go access in your TLB to go evict. And every cycle, you go and you somehow change this counter, or maybe increment it by 1. And there's a little hardware counter there that will actually do this. And that's not quite random, because it's correlated somehow. And that's actually can be a good thing, because that actually can make it so that you can somehow test your processor. Having something that's truly random, if you're trying to pick up like random noise from the atmosphere or a true random number generator, that can be very hard to test. So instead, what a lot of times people will do is they'll use a clock algorithm such that on every instruction that executes, you increment the TLB replacement location by 1. And it rolls around when it gets to the full size of the TLB replacement size. And what's nice about this is if you reset that register to, let's say, be 5, and you execute 100 instructions, you know what it's going to be 100 cycles in the future. So you have some predictability in that. But it looks like random, because it doesn't increment, let's say, with every memory reference. Instead, it increments with every execution of an instruction. First in, first out has some notion of locality that works OK. True LRU, some people actually do here. So one of the good questions that comes up is, if we're trying to access a big array, can we map enough memory with our TLB to access that big array without having to take a TLB miss? So we'll call this the reach of the TLB, of all the things you can map with the TLB. So let's say we have a relatively decent-sized TLB here. We have 64 entry TLB, 4 kilobyte pages. how much can we go access? Well, we can go access 256 kilobytes. You know, that's not small, but it's not huge. So this actually does bode for having more TOB entries. It also bodes for possibly having larger page sizes. Now, this is the traditional sort of trade-off here for caches with block size, that having a larger page size makes you have larger reach, makes you have fewer TOB entries, but it can increase your internal fragmentation, and you might have to pull more data off the disk if you go to sort of start up a new process and has these large pages, and you don't have to use all of it. And you don't want to use all of it. So something to think about is that the reach of the TLB is important if you don't want to get the OS involved. So a couple extensions to the TLB. Something we haven't talked about up to this point is what happens when you have multiple processes running at the same time, or time multiplex between them. What do you have to do to the TLB? So we talked about changing the page table base pointer when you change to a new process. Well, the TLB is a cache of the page table. So when you go to change the page table base pointer, you're going to have to invalidate your entire TLB. And if you're doing this, let's say 100 times a second, like you do on modern day Linux, this can be pretty painful. Or maybe 1,000 times a second on some faster systems, you're going to be trashing your TLB pretty quickly. So that could be quite painful. So a solution to this is you actually add extra bits into your TLB, which say which process a particular entry in your TLB belongs to. And we're going to call this an address space identifier. So we're going to be a little bit more general than a process identifier here. Sometimes some operating systems will actually use the same, some bits of the process identifier as the address space identifier. Some people don't. But you can think of this as something which will uniquely identify the address space. So now what we can do is we can commingle different processes' TLB entries, and this address space identifier takes part in the associative lookup in the TLB. So our match operation checks the tag, and it checks to make sure our address space identifier is equal to a special register which is on the side, which is added, which is the address space ID for the currently running process. So we're actually going to check this and that. Now sometimes you do want to actually ignore the address space identifier. So a good example of this is like operating systems pages. So if you have the operating system mapped into every single process out there, you don't necessarily want to be polluting your TLB with separate copies of the page table entry for all the different operating system pages. So a lot of times if you add an address space identifier, you also add a global bit that comes into the match. And the global bit basically says, ignore the address space identifier, and turns it back into the case we had before. This is traditionally only used for operating systems pages. And then finally, something I wanted to say is a sort of a neat extension here is to have variable size pages. So instead of our basic TLB, which has, let's say, one page size, 4 kilobytes or 1 megabyte or something like that, you have some bits in the page table entry which actually say, this is not part of the match. Well, actually, this is part of the match, I guess. You do have to look this up, because this is going to change how many bits of the tag to look at. But you're going to use this, and you're going to say, oh, the output is a different page size. So we can have 1 megabyte pages and 4 kilobyte pages at the same time in our page table. And you can use the large pages for large pieces of memory that you know are going to all be there, and then small pages for something where you're worried about internal fragmentation. So you can think about having the page size. Most architectures do have page size. A lot of architectures have something like an address space identifier these days. And some architectures will actually have an address space identifier that's hidden from the operating system or hidden from the programmer, and it tries to figure it out itself. So it's not architecturally visible, but the microarchitecture effectively has address space identifier. So if you hit in the TLB, life is good. You get the address you need. If you miss, there's two major approaches to figuring out where to go look for the data, or where to go look for the page tables. The approach that something like x86 uses is to use a hardware page table walker. So there's a little state machine in the main processor which says, oh, page table miss happened. It stalls the whole processor, and then what it does is it, in physical memory, will walk that multi-level page table for you. And we'll do index into it, and another index, and another index if it's a multi-level page table, and finally come up with the actual address. It'll refill the TLB. And this is like the miss case of your cache. Another common approach, which is what MIPS and Alpha do, is they'll actually use software to do that walk. And effectively what this is similar to having the miss case of your cache be done in software, or it's done in the operating system here. And why this can work out and not be too horrible is because TLB misses are relatively infrequent. So because the TLB miss is relatively infrequent, you can try to do it in software. Something I did want to say is that you can also, because it's being done in software, you can have different layouts of your page tables. You don't have to have one very rigid page table layout. Because if you do it in hardware, that means the layout of your page table has to be known between the hardware and the software, and they have to be agreed on. And that can cause challenges. Let's see, one other thing I wanted to say. PowerPC is actually a little bit interesting here. We have it put under hardware, but it, to some extent, can sort of straddle these two a little bit. Some implementations of PowerPC do this completely in hardware, and some actually have some software assist for the harder cases. And you could also think of the software ones sometimes having a little bit of hardware to assist. So for instance, in MIPS, there's a special hardware register that gets loaded with the address of the first level page table index if you're doing a multi-level page table. And the software can elect to use that register or not. So it's like a little bit of hardware boost, but it doesn't do the actual cycling of the page table in hardware. Instead, it's done in software. Just want to briefly show an example here of real page table structure. This is the Spark page table structure for their 32-bit Spark. They actually have 3 levels of page tables. Something to think about. You can have, and the memory management unit will do the walk-in hardware. So it will index and then index into it again and index into it again based on these different indexes to come up with the physical page number if you have a TLB miss. OK, now we get to put it in the pipeline. So here's our 5-stage pipe. We want to be able to access our caches. And accessing our caches with virtual addresses could be problematic. We'll talk about that in a second. But it'd be nice to be able to access them with physical addresses. So we want to go through our TLB to be able to access these caches. Well, all of a sudden, we've added something to our miss path, or excuse me, to our hit path, actually, of our cache. We put something in series with it. This can slow down our cache access. That's not great. I wanted to show something else being drawn here. Here's the hardware page table walker. So if you have a miss, it stalls the whole processor and fires up, and it'll actually use the page table base register to walk around in main memory and figure everything out. And usually, the page tables are held in untranslated physical memory. Because if you have to go through virtual memory to go touch your page tables, to go manage your page tables, it's a real big headache. But this makes life a little bit easier because the data cache and the instruction cache and the memory is all physical addresses. We don't have to worry about any of this virtual memory stuff. OK, that's not so bad, except for I don't like how this slows down my processor. OK, so let's look at big, putting it all together here, perspective. You have a virtual address that comes in, goes through your TLB. If you get a hit, you check to make sure you can read it or write it, or you have access to it. If you do, you just access the cache, and life is great. If you don't, you trap into the operating system, and you with a protection violation or some sort of segmentation fault. Your TLB lookup here, let's say you take a miss, you end up with the page table walker. Now, this might be a hardware page table walker or a software page table walker. And this is where we start to see virtual memory showing up. So I said we would go back to memory on disk. Well, this is where it shows up. In the page table, the data could be in secondary storage. It could be on disk. And we can figure that out right at this point. And the operating system will be notified if it's not in the page table. So if the page table entry is invalid, you end up in the page fault handler. If it is valid, if you have a hardware page table walker, the hardware page table walker will update the TLB, and you go to re-execute the exact same instruction that you just faulted on. Or if you're a hardware page table walker, you're not even going to take a fault here on this path. It'll just stall the pipe for a bit. If you have a software page table walker, you'll actually have software doing this little part here. Now let's say the page exists, but is on disk. We somehow moved it out onto disk. Well, the page fault handler will actually load the page into memory, read it off a disk, patch the page table such that it now points at the correct place in memory, and then re-execute the same instruction, so return from interrupt at the instruction that took the original page fault. So this turns into, if we put this all together, we end up with our modern virtual memory system here. And our modern virtual memory system allows either memory to be in memory or memory to be on disk. And one of the cool ideas that people came up with is some fancier ways to manage this. So we can end up with what's called demand paging. So in demand paging, we don't load anything when we start a program. If you go run a program on Linux, believe it or not, all it does is it maps in the first page of your executable and just starts you executing. It doesn't pull in the entire executable. If your executable is 5 megabytes, it pulls in 4 kilobytes worth of that on x86 and starts you going. And just you start executing. Now what happens is when you go to run, let's say you're executing, you execute off that 4 kilobytes, you end up in this page fault handler. Now the OS has a table. It might store it inside of the page table, or it might store it in a side structure. It knows, oh, well, the rest of that executable is still on disk. So it goes and it grabs that bits off disk and puts it into memory, maps the page, and restarts the load that missed, we'll say. And this works not only for portions of the executable that are on disk, but this can also work for things like your heap. So if you go to try to access off the end of your heap, and the OS knows that you actually allocated that space, it can just actually create new space for you and go find some page in memory for that space. So believe it or not, on a modern day x86 processor on running Linux, when you go to call malloc and you allocate a bunch of space, that space does not get created for you. Nothing happens. This is why malloc happens is really, really fast. The page does not get created until you first touch that page. So it's just smoke and mirrors in the meantime. And this is called demand paging. So during that first time when you call malloc, it just does nothing. The OS keeps track that, oh, it should have given you some memory, but it didn't. And then when you go to actually go touch the piece of memory that it was supposed to give you, At that point, it goes creates memory for you. And the reason it does this is because it decreases the memory pressure. You can actually run more programs if the programs are not executing the memory. So let's say you have a program which just allocates mallocs a lot of space, but then does not go to access it. Well, it didn't have to go allocate memory for you. This causes some challenges on the flip side, though, of all of a sudden, let's say you have 100 programs running, and they all alloc, I don't know, a gigabyte of space. They all call malloc of a gigabyte. The OS will just say yes, 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 yes to everybody. And then everyone goes and tries and access that gigabyte of space, but your machine only has, let's say, 4 gigabytes of memory. But all of a sudden, it promised 1,000 gigabytes of memory. Well, when your programs go to actually go access that 1,000 gigabytes or that terabyte of memory, which it doesn't actually have, at that point, one of them is going to crash, basically, and you get an out-of-memory error. So this is the flip side of this demand paging scheme, is that your OS has to be very careful not to run out of memory, but sometimes it does. So we're going to let's stop here for today. And next time, we're going to finish up this lecture and move on to some other topics. But I just wanted to, I think we're running a little bit late today. But next time, we're going to talk about how to integrate translation look-aside buffers with caches and how to integrate them into the pipeline. So there's a lot of complexities in doing that. It's very possible that you don't want to actually access the TLB first before you go to access the cache. And we're going to talk about how to do that. I mean, the main reason you don't want to do that is it increases your time through here. OK, let's stop here for today. OK, so we'll get started. It looks like we have a quorum today. So we're going to be continuing, wrapping up what we were talking about last time, which was about address translation and virtual memory. So we had like about 2 or 3 slides left over. And mostly what we were trying to talk about was how address translation and virtual memory influences the design of caches. But let's go back and briefly recap here what we were talking about last time, just to put it back in everyone's memory. So we were talking about memory management and different ways to do memory management. And we had talked, and some of these orthogonal concepts and functions that memory management is trying to do. Mainly, we're trying to translate addresses so that we can move around data and remap data. We were talking about protection, which would allow us to run multiple different operating systems or multiple different applications at the same time on one chip. And we also started to talk about virtual memory, but this is kind of where we were left off last time. We were talking about, we talked about paging, and we briefly touched on demand paging. So we want to continue on that today and then look at some of the implications of the design issues of virtual memory and the ability to have lots of different address spaces intermixed at the same time with different mappings, and how that intermixes with having lots of memory or very large amounts of memory, even though your system may have a very small amount of memory. So it's a very large amount of virtual memory, as the name implies. So if you go look at a modern day virtual memory system, so if you're going to run Linux on your desktop these days, your desktop, let's say, has a few gigabytes of RAM, has some small number, probably 1, 2, 3, 4, maybe even 6 if you have a really good desktop, of gigabytes of RAM. And one of the things you may want to do is run applications that use more RAM than that. And we have this big storage device plugged into our computer, which has lots and lots of storage, namely our disk. Now, the disk is not the only place you can actually try to swap memory out over. you can actually use other things. So people have built virtual memory systems that swap memory across the network, for instance, to another computer. This was actually found to be fast in the original network of workstation days. So this is a project at Berkeley where they had lots of computers, lots of old Sun computers on a network, and they were actually able to swap memory across the network to the neighboring computer and use the neighboring computer's RAM, effectively to make the RAM size bigger of the machine that they were using, or effectively swap out. Now, one of the key things to making all this work is having this notion of demand paging. And demand paging basically is around this idea that the operating system only maps a page when it absolutely has to. And the operating system can also decide to kick things out and put that memory, let's say, on disk. If the memory is clean, what I mean by clean is it's not dirty relative to the process. So the processor do not go write any data to that memory. And there's exact same blocks on the disk. When it goes to kick it off, it doesn't have to go save that dirty data and can just mark it as saying, oh, it's on the disk already over there. So don't worry about this. If you go take an operating systems class, you're actually going to implement a demand paging scheme. I know they do that here at Princeton's operating systems class. So you can try out some different algorithms on how to pull data in and not out, because there's different management algorithms you can use to do this demand paging. But if we went back and looked at sort of how address translation works from the hardware level, because that's what we're focusing on in this course, you take an address and you run it through a translation look-aside buffer. If you have a hit, this is the everything's going well case. You have a hit, so the address is in your translation look-aside buffer cache of the page table. You also probably want to check some protection bits, so to see if you can do a read or a write, or if the process that is reading or writing the data is in the correct address space. So for instance, you don't want to have an application trying to read or write the address space of the operating system or something like that. If it's permitted, the translation comes out of the TLB, everything's good, and you just go access the data. If not, you're going to end up here in this protection fault case. And this protection fault case is going to be in the operating system, and the operating system will probably try to kill the process or have some sort of segmentation fault. Alternatively, if you're up here in the TLB lookup and you take a miss in the TLB, lots of interesting things can start to happen now at this point. If you have a hardware page walker, so what that means is a little finite state machine which will walk through the page table, walk all the way to the end of the page table, find the mapping, and install it into the TLB, this and this is all done in hardware. Hence, it's speckled. If you are on an architecture or something like MIPS or Alpha or Telera, that's all done in software. So this page walker and updating the TLB is actually done in software. So we'll have some software going and walking it and doing a bunch of memory references, and you have a little piece of software there. And then there's some hybrid approaches. So for instance, even on MIPS, there's some special hardware that helps the software walk the page table faster. If the memory that you're trying to go get at is not in the page table already, then you sort of fall over here in the operating system line. You take an interrupt into the operating system. The operating system then has to go look through all of its structures and see, oh, is that data on the disk somewhere? Are you just accessing some piece of memory that doesn't actually exist? If that's the case, then you're actually going to be sort of going over this segmentation fault or bus error world also, because you're basically going to be trying to do a memory reference to some piece of memory which isn't there. But if, let's say it's on disk or it's in the swap memory or the backing page cache on the disk, you're basically going to have the OS fill in everything, fill in the TLB, and just return. And life is all good, and you continue on. So now that we have decided that we want something like virtual memory, and we've decided that we want to have translation look-aside buffers, let's look at how this influences the design of our hardware pipelines. So here we have address translation shoehorned into a 5-stage pipeline here. As some of you may notice, here and here, we just added to the delay of these stages. We just sort of shoehorned it in. We didn't add an extra stage. We just sort of put it in there. And it's serial is the naive approach to go do this. Well, that has some serious latency considerations. So if your instruction memory is on your critical path of your processor, and all of a sudden you put something else in serial with it, your processor gets slower. Or if your data cache is on your critical path of your processor and you add something in it, that's going to also slow down your processor. So we want to look at techniques where we can actually move those two structures off the critical path. Alternatively, we can start to think about having something where we could pipeline the TLB in the cache and have one stage for TLB lookup and one stage for the cache. It gets a little hard, and that mainly over here in the data side of the world, it gets a little hard because that's going to increase your access time to your data memory. So when you do a load, it's just going to push out that load an extra cycle if you put another pipe stage in there. And in the instruction side, this could also hurt your branches. So if you add an extra cycle out, and if you put a pipeline stage something like here, then your PC+4 loop gets a little bit harder. Not from a timing perspective, it probably doesn't get harder, but from a if you have a branch perspective and you take a branch in there, you're going to add an extra cycle to your branch, mispredict latency. And also, it gets a little bit weird here that you can't access your instruction memory effectively in one cycle. Having said that, it's usually easier to take the instruction TLB off the critical path because you don't really change the high order bits of your instruction that often. You really only change that, you only cross page boundaries when you do like a far jump or if you happen to fall through off the end of a page. And both those are relatively rare cases. So people have found that it's pretty easy to sort of take that off the critical translation path. So we're mostly going to focus on the data side of the world here. OK, so one technique to do this is to, let's say, take the TLB, and instead of having the TLB in front of our cache, put our TLB, let's say, in parallel or after our cache. So what this means is the addresses that go into our cache are virtual addresses. And this has some pretty big implications. Lots of processors are doing this these days, where they will actually put the TLB in parallel with the cache. And this picture is a little bit confusing because it looks like this is after the cache. To some extent, it is and it isn't, depending on how you sort of squint and look at this. If the cache is completely virtually indexed and virtually tagged, it would look something like this, because you only go fire up the TLB when you take a cache miss, and you have to go out to farther out layers of memory. Now, if you have a virtually indexed but physically tagged cache, what that means is the address that goes into the index of the cache array is a virtual address, but then you do the TLB access in parallel, and out comes a physical address. And then you do the compare, the tag match on the physical addresses. That makes a lot of things a lot easier in life, and we'll look at that in a second. So one of the major challenges that you end up with here with virtually indexed caches that I wanted to point out is you start to get some aliasing problems. What do I mean by this? Well, before, when you were to go put something in the cache, it could only be basically one place in a direct map cache. In a n-way associative cache, it could be in the n different places. So a two-way set associative cache could be in the two ways. But you knew where to look for it, at least. But all of a sudden, if you start to have bits above the minimum page size in the address feed into where it is in the cache, it could actually be in multiple places in the cache. So brief example here. We have a 32-bit address. We have our cache offset here. We have, let's say, a page size of 4 kilobytes. So that's going to be, what, 12 bits? And let's say our cache index, or our cache rather, has, I don't know, more than 4 kilobytes in it. So all of a sudden, we have a direct mapped cache which has 8 kilobytes. Uh-oh. So this bit here, so this is our index. Sorry. Our index into our cache has 1 bit here above the page boundary. And the OS could elect to have this bit here be a 0 or a 1. So what that means is all of a sudden, when we go to index into our cache, the same physical piece of memory might be in 2 different locations. Or depending on how the operating system sort of lays out memory, you might look in the wrong spot, or you might need to check both places. So we have to start thinking about this, that the bits above the minimum page size, if our cache is bigger than our minimum page size, the bits are not going to match. And we'll walk through an example of that in a second. Also, virtually addressed caches have some other challenges here. Because 2 applications can have the same virtual addresses, and let's say your time multiplex between application 1 and application 2, all of a sudden these 2 applications are going to go into your cache, and you might have one application hitting on the data of another application. So if 2 applications are trying to go access address 5, and they have different values stored at address 5, in our virtually indexed cache, all of a sudden you might start to get something weird here. You might actually end up where if you don't protect against this, one process is reading another process's data out of the cache. So you need to protect against this. And there's a couple different approaches. One approach is actually just to flush the cache on every context swap. So every time you change processes, flush the whole cache. That sounds really expensive, but believe it or not, that's actually done with non-trivial probability, or that actually is done in some actual real systems out there. A little bit nicer way to do this is to have address space identifiers. So you actually tag the cache with an address space ID, and it's part of the tag information. So it's not just the virtual address that matters, but it's also which process ID or which address space ID. So it's another sort of thing, but that increases your tag bits. So you got to be a little bit careful about that. So this is mostly about having a virtually indexed, virtually addressed cache. Or virtually indexed, virtually tagged cache. And if we look at this, how this fits into the pipeline, life actually gets a lot better from a hardware perspective. This is sort of summing up what we saw before. You really only have to do translate on cache miss. So your main processor pipeline looks the same as what we've been drawing up to this point. But on cache miss, you have to go through either your instruction translation look aside buffer or your data look aside buffer, or data translation look aside buffer. So to sort of sum up this a little bit more pictorially here, what's happening with virtually addressed caches, let's take a little bit of a gander at this example here. So we have 2 virtual addresses, virtual address 1, virtual address 2. And the operating system elects to map those to the same physical page in memory. This is something that virtual memory systems do many times. Sometimes you want to have a memory hole where you have memory mapped twice, or you want to have a piece of memory mapped between 2 different applications to share data. Pretty common thing to have happen. So you want to share some physical memory. Unfortunately, if you go look at our virtual addressed cache here, we actually end up with it in 2 different locations. This is going back to that example there. You have a first copy here and a first copy there, and it depends on where it actually was located in the virtual address space, which has no mapping to where it actually should be located in the physical address space. So the bits don't match. The bit of the virtual address here and the bit of the physical address in this bit here does not match. And that causes a a world of problems, because all of a sudden you can have, let's say, that even the same application write to address, let's say, 10, and write to address 4096 plus 10, and they're supposed to be mapping to the same location. It's supposed to be the same address, but you can write 5, and then the other, using the other name for that same location, it'll read, let's say, 1,000 or just some random number out of there. So there's a couple techniques to deal with this, and I don't want to go into too much detail. Your book goes into some more detail, but just to give you a little bit of an insight on how to go about solving this. There's some systems out there which actually require that the virtual indexed piece of memory resides in the same location as another page of that same address in the cache. Now, you sit there and you scratch your head, and you might say, well, is this effectively decreasing our associativity of our cache or moving things around in our cache? Well, a little bit is the answer. But these are sort of the trade-offs, and the OS can, to some extent, manage this different layout. And that's what I was saying here. And early Sparks actually used a system like this, where it ensures that the virtual addresses accessing the address in the PA will not conflict in the direct map cache in a bad way. So you're going to guarantee you'll always go to the same location. So that's sort of the beginning point. If you have virtually indexed and virtually tagged, but you can have other mixes of these things, and not all of them make sense. You can have physically indexed, physically tagged. That's what we've been talking about at the beginning of last lecture. That was the sort of the simple case. Virtually indexed, virtually tagged. That has lots of challenges, we'll say. Virtually indexed physical tagged. Now, this is actually a really good trade-off here. So you do the translation in parallel with the cache access, and then you do the tag check. You don't actually need to have ACIDs in this case, address space identifiers, because you're guaranteed to have the correct physical match. You might be accessing, let's say, the wrong location in the cache, or you might be accessing the wrong location. So we don't get around this virtual physical problem and being in 2 locations. We'll talk about that in a second. You still need to handle that sort of in the Spark way, but at least you don't have to have address space identifiers, and at least you don't have to flush your cache on every process swap, because you're guaranteed that the check that you do on the cache miss or hit is exact, because you're doing a physically indexed, a physically tagged cache. And then you can have something what we'll call both indexed and physically tagged. This is a cute little trick that a lot of architectures play, is they just want to ignore all these problems. And they want to make something that looks like a physically indexed, physically tagged cache, but they still want to have a cache that's bigger than their minimum page size. So you have a 4K minimum page size, and you want to have an 8 kilobyte cache. If you have a direct maps cache, this bit here, the one above the page size, is going to be part of your tag index, but it's not, it doesn't fall into, so it's part of your tag index, but you're not going to be able to control it. But what you can do is, let's say you take your 8 kilobyte cache and you make it two-way set associative. So all of a sudden it's 8 kilobytes, but it reduces the number of index bits you have. And it fits within your index into the cache. So it's a cute little trick here that you have. It's virtual and physical. The virtual and the physical addresses below the page size are the same. So the index into the cache doesn't get changed after you go through address translation. So you'll see this where people actually add associativity to their L1 caches just to avoid having to do address translation. And then you do address translation in parallel, and you do physically tagged and do the tag check physically. There's this other one down here that I had to have a X through. I don't think I've actually ever seen one of these built. Because it kind of doesn't make sense. Having a physically indexed, virtually tagged cache. Yeah, not sure why you'd want to do that. Because usually the hard part is generating the address to stick into the cache. So I've never actually seen one of these, but it's always possible to go build something like that. But it's something to think about, that if all of a sudden your cache size or the amount of index bits that go into your cache is more than the amount of bits in your minimum page size, your addresses are going to show up in multiple places. And you have to either deal with that or at least understand what's going on there. And it's usually done by the operating system. One final note, we've mostly been talking about multi-level page tables where you sort of index in and then you have a tree of pages that come out of it. This is only one approach. People have built stranger things out there and still implemented paging. That's only one structure to hold all the pages in. So one thing you could think about is if you have lots and lots of page tables, and they're all mapping, let's say, to the same, they all look similar, you can try to share different portions of the page table, and many times the operating system does that. But another way to look at it is you can try to have a table which takes a physical page and maps it backwards to a virtual address. These are actually usually called inverted page tables. And on first appearance, this sounds weird because it's the map in the direction you don't want, you would think. But to make up for it, what usually architectures do to solve this problem, the architectures that have had inverted page tables do to solve this problem, is they have a fast hashing function and a really small hash map, which does the correct direction. And then if they have the slow direction, they basically sort of walk the page table and it's a complicated hashing scheme, but basically it's kind of one of those linked list hash functions. So you check one location in the physical to virtual table. If it's not there, there's a link to another location, and if it's, it actually ends up working out not too bad. But that's not very common today. So I just wanted to put out there that you can actually have the idea, or you can have different arrangements of pages, and the canonical page table we talked about today, or in class last time, was only one way to go about doing it. Okay, so questions on virtual memory caches before? Yep. That's a good question. So when you say page relocation, you're saying that the operating system takes a page and decides to move it in physical memory someplace else?
Maybe if it's addicted and then put back in a different location.
So you're saying because, yes, you're saying the cache could get stale. Yeah, so the problem is that, let's see if we draw this. Here we have a linear page table. We put in address 5,000 hexadecimal, and that maps to some location in our physical memory. Let's say, to make life easy, it maps to address 8,000 hexadecimal. Now, the OS comes along and swaps this page out to disk. Sometime in the future, it decides to pull it back in. And it pulls it back in down here at A00 hexadecimal. 8000 hexadecimal. And it updates the page table to point to there. Now, what Govan was trying to say is, in our cache, we had some data that pointed to this physical memory that was in the cache. Now, all of a sudden, we go and we move everything around. Is this a problem? Because we're basically going to do index, and the physical address that comes out is not going to match what was in there for that data. That's actually OK. We're just going to get a miss on that location. So we're just going to get a miss. And then it's basically going to evict it, and then go pull in that exact same piece of data. That's actually not so bad. Now, there are other more subtle challenges with these virtually indexed, virtually tagged sorts of things that will many times require you, when you go to do this remapping, to actually invalidate all the memory that you kick out. Because you actually might get a hit, even though it's pointing to the wrong location. So let's say the other case is you're in a virtually indexed, virtually tagged cache. And we did this remapping, this exact same remapping here. Well, there's different physical memory underlying address 5000 virtual now. And we want to make sure we don't take a hit on the old data, which is still in our cache. So typically, the scheme to go handle this is you actually have to invalidate all that memory out of your, actually it's typically flush and invalidate operation out of your cache. And depending on what architecture you're on, some architectures actually have instructions that flush the entire cache. So x86 has something called write back and invalidate, which will actually flush the entire, it'll write back all the data and it'll flush the entire cache. Other architectures, so something more like MIPS, does it on a line-by-line basis. And it's basically an operating system only instruction where you can actually access an address, and given that address, or excuse me, you present an index into the cache. And given that index, it'll flush that data cleanly. Now, then there's something sort of in the middle. If you want to actually have the user be able to do this sort of flushing, you need to think a lot harder about this, because you want some way for the user to be able to present a virtual address but have that name something about the cache. So there are some ways to do that, but it's kind of, the corner cases there get pretty tricky. But so yeah, does that answer your question? So you get a miss when you go to access it someplace else, and that's actually OK. Now, trickier thing is, let's say the OS decides to point at this some other way. And let's say DMA or use another processor or something to go overwrite this piece of memory. Now your cache is stale. But this is sort of a more involved question going to, if you have multiple processors, how do you keep memory from multiple processors coherent, which we're going to be talking about in 2 lectures about cache coherence between different processors. If it's on the same processor and it's accessed the same way, the cache is going to pick up that change. If it's accessed, let's say, some other way to that same address, the operating system's going to have to be very careful. And this is why these virtually indexed, physically tagged caches usually require some way for the operating system not to have those bits differ. If the bits match, you know you'll kick it out. So, and because it's physically tagged, even if you have a, let's say, 4-way set associative cache, you're going to get a hit on the physical address bits after the translation. So it's not like you can actually have, let's say, way 0 and way 1 having the same piece of physical address data in it. That just can't happen in a cache, because on a physically tagged cache, because the physical tagged information is going to be the same. Today we move on to our new topic, vector computers. So a little bit of introduction on what a vector machine is, or a vector processor. Broadly, it's a way to get at having data level parallelism. Many times for, let's say, array operations, you're going to want to take one whole array and add it to another whole array. And let's say these arrays are large. Does it really make sense to have a processor sit in a tight loop doing load, add, store, load, add, store, load, add, store in a loop. And that's the insight that comes out that if you have computations that work on vectors or matrices or even multidimensional matrices, you can think about building an architecture where you don't have to have as much instruction fetch, instruction decode bandwidth, and you don't have to sit there and fetch new instructions and continually operate on those new instructions. You could just have an instruction which encodes some large amount of computation, because it's all the same, is the insight. Also, in today's lecture, we're going to be talking about single instruction, multiple data architectures. This is kind of a degenerate case of vector architectures. And a good example of this is something like multimedia extensions, or MMX, in the Intel processors, or AltiVec in the PowerPC architecture. The newer thing that Intel has added, and they all call SSE, streaming something extensions. I actually don't know what the second S stands for. And then they also now have something they call AVX, which is even wider. But they can basically have continually added more instructions to make the short vector nature better. And then finally today, if we have time, we'll be talking about graphics processing units. So I have some examples here. This is the ATI FirePro 3D V7800. And then we have the NVIDIA equivalent, or the NVIDIA competitor here, which is the NVIDIA Tesla. I think this is a C075. These are both very fast processors. And what's interesting is these started out as graphics processors. So they started out to play video games effectively, or to do some sort of rendering of three-dimensional data. So you take in some data, you operate on it, and there's massive parallelism there, lots of different triangles in a three-dimensional image, for instance, in three-dimensional rendering. And people had this insight that that same processing architecture that is good at rendering triangles might be good at doing, let's say, dense matrix operations also. And we've seen this outgrowth, and we've seen a whole programming model come up around this. And this is very recent. To some extent, these architectures don't come from the same lineage as in sort of normal processors. They really come from fixed function hardware that was there to render video games and three-dimensional sorts of scenes. So the architectures look quite a bit different, and the naming is very different. So if you go pick up the manual that tells you how to program one of these things, and you come from a computer architecture background, you're just not going to understand any of the words. Your book, actually, the Hennessy and Patterson book, has a very good table which translates from sort of traditional computer architecture words to GPU words. And that makes life a lot easier. OK, so let's get started looking at vector processors. And let's look at the programming model first before we look at the architecture. So this is the software model, not what the hardware looks like yet. So to start off here, a couple things to note is in a traditional vector architecture, you're going to have some scalar registers. And these are the registers like in a normal microprocessor. They just hold one value. And they're maybe, let's say, 32 bits or 64 bits in width. And then you have a second register file which holds vectors. And when you go to access one of these vectors, it's the same thing as a register file here. If you go to access, let's say, vector register 3 or something like that, that doesn't denote one value. Instead, it denotes many values at one time. And typically, we have a fixed width here drawn, but typically these things have very long widths. So for instance, something like the Cray processor, the Cray 1 processors, had a maximum vector length of 64 elements, where each element was 64 bits. So it's a lot of data that you're sort of moving around at one time with one operation. And an important piece of sort of architectural, or at least programming model hardware here is the vector length register. The vector length register says how many of these elements are actually populated. And we'll see why that's important. But for right now, let's just think of having the vector length register be equivalent to the maximum number of elements in the vector. So think of it as having 64 elements, and the vector length register just says you're always operating on all 64-bit entries of data in parallel. Now, if we go look at the programming model connected to this, we need to add some extra instructions now. In our scalar processors, or all the processors we've been talking about up to this point, it operates on one register with one other register. And that still exists in this model, but